Hi everyone, and welcome to our first lecture, the lesson on real numbers. I know we're all here for algebra and to get better at basic math, but it's really important that we start off with what goes into these variables, what goes into these functions, and that of course is real number. In my experience, people come from different backgrounds with this. They have different definitions, they have different terminology, so it's extremely important that we all sort of start off on the same page. And one thing I want to show you is that the real numbers, often if I ask people to like draw this and represent this, they draw a number line. And that is perfectly fine for most purposes. You put 0 in the middle, and you have infinity off on the right, and negative infinity on the left. But I think this diagram, this picture, hides so much information and really doesn't get into the subtle nuances of what different kinds of numbers are out there. So I'd like to sort of walk through and talk about different kind of numbers. So treat these as almost definitions. You don't need to memorize these right now, but keep them handy. I'd recommend taking notes as you go. For new definitions in particular, always think about referencing them later and also examples of things that are and are not those terms. So let's start off first with something called the natural numbers. Here's my exercise to you. Pause the video and count to 10. I am very serious. Pause the video. I'll wait. Count to 10, even if you don't want to say it out loud. Here's my guess. No matter where you are in the world, you started at 1, 2, 3. I have a small son. He can count to 10, skip 7, but we're working on that. So he starts at 1. So there's no real reason to start at 1. Would you be wrong if you said 0, 1, 2, 3, or 7, 8, 9, 10? I didn't really specify a starting place, but it's a very natural place to start and go sort of 1, 2, 3, 4, and count your way up. These numbers are called the natural numbers. If you think about it, and we're counting with our fingers, of course we start at 1, 2, and 3. If we're cavemen and we're counting how many woolly mammoth we killed this day, and we take our rock and we etch it into the cave, we go 1, 2, 3. This is a naturally great place to start. So these natural numbers, 1, 2, 3, 4, 5, we denote this by an N with a double bar on the left. Now, fast forward from caveman time to sort of ancient India, and think about nothing. The next number that entered the number system was 0. Now this is not an obvious jump, and it took a very long time to get there. It's a little difficult to symbolize, formalize, and conceptualize nothing. So we have 0, 1, 2, 3, 4, and off we go. When you add 0, you have created the set of whole numbers. I remember whole because of the O in whole, and of course 0 looks like an O, so we have the set of whole numbers. That set is denoted as W with a slash to denote the set of whole numbers. Now fast forward throughout human history and start trading with different civilizations, and all of a sudden you owe me money or coins or whatever it is back then, rocks that they traded, who knows. So if you owe me something, you can have a debt, and after 0 came negative number. Now there's no limit to how much you can be in debt, so we go ... -3, -2, -1, 0, 1, 2, 3. You can certainly have profits. And now we have sort of to start to form the larger system of numbers that we know as integers. So this set of numbers is called integers. Now be careful here. For different reasons, we don't denote this set with the letter I. We denote it as Z. If you speak a little German, if you sprechen a little Deutsch, sorry, I don't, but one of the ways to say number in German is Zahlen, Z-A-H-L-E-N. So the Z comes from German for Zahlen. A lot of math, the first math textbooks, a lot of universities that had a lot of mathematicians were in Germany and France, and so you will often see a lot of German influence into the symbols that are in, or the language or descriptors, vocabulary of math. So here's the first one, Z for Zahlen. We don't use I. We tend to save I for interval, a little interval around the number. So I does get used, but just not here. So this is the integers, and this is Z. If I want to talk about a particular element, I'm going to use some symbols here, by the way. So if I want to say 1 is an integer, but I wanted to remove the English sentence look and feel of this, and I wanted to write this in symbols, I'd use the symbol that looks like a little e, but it's not an e. I'd say 1 is an element of Z. 1 is a member of the set of Z. This symbol, you can think of this as is an element of. And certainly you can write things that are not an element of. So I could say, for example, that 0 is not a natural number. And you start to get into more of the symbolism of math than writing out full sentences, which is a bit more common. Now, after integers, fast forward to Egypt or Greece or some ancient civilization and start thinking about architecture and beautiful buildings and ratios, and you get yourself into the set of rational numbers. Rational numbers are ratios, or sometimes called fractions, of integers. I write it as a over b, and then I write a couple things. This bar, by the way, means such that, so the way that we have this so far is the set of all numbers a over b, such that a and b are integers. I'm allowed to pick any integer I want, 2/3, 1/2, 3/5, pick whatever you want, as long as, of course, and I think we all know this, you can't divide by 0, so you're not allowed to pick your denominator to be 0. Any other values are fine, as long as your denominator is not 0. These are called your rational numbers. The symbol to denote these ratios is not r. Why can't we use r? We're going to save r for the real numbers, so I have to come up with another clever way to say ratios or fractions. I can't use f, because I can use f for functions, so I look up other words in the thesaurus, and I come up with q for quotients. When you write a number as 1/3 or 2/3, remember you're dividing 1 divided by 3, 2 divided by 3, and so you get quotients. So Q is our set of rational numbers. It's a very famous result that not every number is rational. You may know that pi cannot be written as a fraction. So we'd say, of course, that like pi is not rational. When you are not rational, something like this, you're called irrational. It's a nice, so pi is irrational, e square root of 2. There's all these numbers that cannot be written as fractions. Once you have all your rational numbers, though, when you start to want to talk about the more complicated numbers, pi, square root of 2, e, pick your favorite, scary number, then that is when you get to the real numbers. So the real numbers is our big world, our universe. This is where we're going to hang out for the most part, but I want to show you the structure that happens inside of this universe that's not obvious from the number line. Real numbers is a little difficult to define. If you ever take a more advanced course called Real Analysis, they'll do this officially. I'm going to sort of hand wave a little bit and say any number with a decimal expansion. That allows me to talk about 7, right? Because 7, of course, is like 7.0000, or I can certainly talk about pi, which is 3.14159, ... So everything is a real number. I want you to stare at this for a second and realize that as I've developed a larger set, I haven't lost any numbers along the way. This is extremely important. I want to keep all my previous contributions to the number system. So when I went from natural to whole, it's 0 plus everything I had. When I went from whole to integers, it's negatives plus everything I had. Rationals, I can think of every integer as a rational. How do I do that? How do I think of 2 as a fraction? Well, that's just 2 over 1. How do I think of a rational number as a real number? Well, I would take out the calculator and figure out its decimal representation. So 1/2 is 0.5, 1/3 is 0.3 repeating. So I can always, again, assuming I'm not dividing by 0, turn a rational number into a real number, and you get everything along the way. What I like about the number line is that it's short, it's sweet, it's simple to think about, and it's definitely useful at times, but I don't think it gives the true picture. Let me draw you a different world, a different universe of numbers, just so you can get a feel of like the structure of the real numbers here. We said the very first level, the simplest level, are the natural numbers. And inside the natural numbers, remember we start at 1, 2, 3. When I add 0, I get this extra layer, which are my whole numbers. When I start to add negatives, I get another layer, which is my set of integers. Keep going and form fractions or ratios or quotients of integers, and you get rational numbers. Finally, add numbers like pi and e or any other decimal expansion that's not a fraction, and you get the set of real numbers. And these delineations, these lines, these separations are non-trivial. There is a reason why we draw the line. So for example, what is a whole number? That's not natural. What's some number that lives in the second layer? Well, 0. What's an integer? That's not whole. So over here we have like -1 and -2. These are different layers where different numbers live. What's a fraction, quotient? That is not an integer. How about 2/3? How about -5/2? Something like this. Of course, there are infinitely many choices and fractions I could pick. What's a real number? That is not a fraction. Pi is a famous example. How about √2? How about E? If you've seen E before, this is like 2.718. This is Euler's number. It's on the calculator somewhere. There are lots and lots more of these. So there are definitely levels and layers to the structure of real numbers that are certainly not obvious by just drawing the number line. If you want to write this in set notation, we tend to write this, if you want to be a little more formal about it, using the subset notation. So we say n is a subset of w. Natural numbers are a subset of the whole. W is a subset of z. Z is a subset of q. Q is a subset of r. This is the world, this is the universe that we will be focusing on in this class. This is what I want you to know. So if I start talking about integers, I want you to have in mind what they are and what they are not. If I talk about rational numbers, or if I want to show you y squared of 2 is not rational, I just want you to have in mind what these definitions are and the symbols that I'll use to talk about these sets or subsets of numbers. Now, I'm not supposed to tell you this, of course, but there's more out there, and maybe you know this, but this is a big secret. We don't really talk about them in this class, but there's one more layer, at least one more layer we could draw. Okay, you can in theory keep going, but the next layer out would be your complex numbers. I'm just going to mention this here just in case you've seen these before, but these are complex numbers. This is the set of numbers like a plus bi, and this is I, the imaginary number. So sometimes complex or imaginary numbers are called the same. A and b, you can pick any real number you want. And I, here's the thing that I think, maybe you've seen this, maybe not. If you haven't seen this, ignore everything I'm saying right now. But I is the square root of negative 1. In particular, I squared is negative 1. So it's some imaginary number that when I square it gives me negative 1. This notion of squaring something to get a negative, you can't do that with real numbers. There's no real number, that if I square it gives me negative. So the next layer out, if you did want to keep going, becomes your complex numbers. These are your complex numbers. It's denoted with a C with a bar on it, and if you've seen complex numbers, they look like 3 plus 2i, or you can get, 7 plus 0i. Of course, this is just 7. So you still get everything you have. Pi plus 0i is just pi. So you don't lose anything prior. You just get the ability to get new numbers now. I is in there, 3i, 7i, whatever you want. Then you get a whole another layer of numbers. We won't talk too much about complex numbers in this class, but it's great if you know what they are, and if you take more advanced classes, you will certainly see them. Okay, keep this sheet handy. We're going to build off of this. Great job in the first lecture, and we'll see you next time. All right, hi everyone, welcome back. So now our job today is to figure out a little more about the real numbers, what they are, and of course, because the real numbers encompass all the other kinds of numbers, we will be studying all numbers at once and talking about their properties. First, though, let's dive into the real numbers. As a review, remember that the set of real numbers, we denote this with an R with a slash on the left. This is any number with a decimal expansion. Now, if you think about what that means, there's really two options when I write out a number with a decimal. Option number one is that I have some repetition. So, for example, if I take 1/3, this is 0.333, and it goes on forever and ever. And you may be more familiar with writing this with a bar over it. So you can certainly have a repetition in your decimal expansion. That also counts if I have a finite decimal expansion as well. So for example, if I take 1/2, I can write this as 0.5. Now you may say, like, where's the repetition? We tend not to write these, but of course I can certainly write many, many zeros, as many as I want after. Now you don't write this as 0 bar. Once you have hit the zeros and they go on forever, you tend not to write it, but we're going to think of this as having repetition. So really in the case where 0 repeats, you have a finite decimal expansion, so just good old 0.5. And where you have actual repeating numbers that are not 0, this still would be infinite, but would be repeating. Depending on the number, it doesn't have to have just one number repeating. You could certainly have 0.25252525 or 789, 789, 789. You can have whatever, how big you want it to be. That doesn't matter as long as you have some repeating part. The other option, the second option for your decimal expansion, was that you have no repetition. And numbers of this form tend to be like pi, which is 3.14159, and this goes on forever. Square root of 2 is another kind of these numbers that go on forever, 1.414213, ... Another kind of these numbers is square root of 2, 1.414213, ... Or even E, which is 2.718, ... Goes on forever and ever. These decimals do not repeat. You can go out forever and ever and ever, and you won't find any sort of pattern. There are many, many types of decimals that repeat and many that don't. These two classes, these two sort of subdivisions of real numbers have a name. In particular, if you have no repetition, you are called an irrational number. And if you have some repetition, you are called a rational number. The reason is because if you have repetition, I can always write you as a fraction. And of course, we saw these numbers to be q. Irrational numbers don't actually have a nice, pretty set name to them, but you think about them as all the real numbers that are not q. You can write that as like a subtraction sign I've seen, or you can write that as like r, real numbers that are not q. There's lots of different ways to write this or just say irrational, but you can certainly use set notation. So the real numbers are really split into two kinds, rational and irrational. And of course, inside of the rational piece as well, maybe we'll draw like a little family tree here. We have our reals, we have our irrationals, we have our rationals. And then of course, on the rational side of the family tree is certainly the integers and your natural numbers and your whole numbers. So this is another way to sort of think about the real numbers. And of course, living above the reals are complex, but we don't talk about that. One thing that comes up often, and you already saw it, is the square root. It's kind of hard to talk about real numbers and not really talk about square roots. So I just want to remind you what a square root is, just so you know. So first, let's define this. So we're going to define the square root for a to be any non-negative real number. So you can be 0, you just can't be negative. That's fine. Then we'll say that the square root of a, which we will denote as the square root of a, with the square root symbol here, is the non-negative number b, that's a real number, such that b squared is equal to a. I want to define these things formally, but I think you know these when you see them. If I said to you, let's give some examples here, what's the square root of 4? You think in your head, what number squared is 4? What number squared is 4? And here's the key part though. You could say -2. Technically -2 squared is 4, but we always want the non-negative one. I want like the positive or 0. So a lot of people get this wrong. They say, is it plus or minus 2? What's going on here? No, if you take a square root, it's the positive number. If this symbol, you think of it as like, it's the positive number. And so, some of these So square root of 2, square root of 4 is 2, square root of 25 is 5. Some of these are just more well-known than others. Square root of 16, of course, is 4. Notice it's +2, +5, +4. Some of the ones that trip people up a little bit are square root of 1. So what number squared is 1? Well, that's just 1, so it's itself. And here's the other one that's okay as well. What's the square root of 0? Now be careful. A lot of people say undefined or something weird, but no, that's not true. What number squared is 0? Well, that of course is just 0. So this is why we allow things to be non-negative. Notice all my answers are positive or 0. To say that in one term is non-negative. So I say the two to watch out for that I think everyone else, might get confused on are these two here. I've just seen too many mistakes here. And of course saying like plus or minus or something weird like that. No, square root is always, always, always positive. Always, always, always positive. The ones that are not immediately obvious to us, of course, are things like square root of 2 or square root of 3 or square root of 5. For these, if you want the decimal expansion, you should just have an idea what they are, give or take. But on a computer or a calculator, I would say don't hesitate to look these up. This is 1.41421, etc., 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 and round to whatever number you want. I just want to caution you against one thing, though, because these numbers are irrational. If I write 1.732, again, get the calculator and check me on this, 1.732, and I say the square root of 3 is equal to this number, this is not super great. It's a little bit of abusive notation. The square root of 3 goes on forever and ever and ever and ever. I've seen this written all the time, though, where they say round to 3 decimals. Technically, just remember, if you round, you are approximating. You are saying square root of 3, I can get it to as accurate as you want. If you're building a bridge or some building, like, go out and get 8 decimals if you need. Get whatever you need so the structure stands. But just remember, even if you chop it off after the 100th decimal, there's always a 101st. You're always rounding. So take a second, pause the video, and tell me what the first 4 decimals are of square root of 5. See if you can beat me to it. Square root of 5, maybe even know this somehow, I don't know. But these are things that are not well known to humans, but definitely well known to calculators. So it could be 23606. Of course, if you round 6 to 7, just because the next decimal is a 9, that's fine too. As long as you get close enough, that's excellent. If you put the dot, 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 you get equality. If you start cutting things off, if you just put a period here and end it, just remember you are approximating. So square roots will come up a lot as we talk about real numbers. They're a nice way to generate irrational real numbers. Now that we have these set of numbers, rational and irrational, we want to do things to them. We want to start building our vocabulary and our terms of real numbers. So the first thing I want to talk about is the closure property. So the closure property says that if I let a and b be any real numbers, so let's use our math symbols here, a and b are elements of R, that says they're any real numbers, then the set of real numbers is closed with respect to addition and multiplication. So let me write this out. So a plus b is always a real number, and a times b is always a real number. This property is called the closure property. Let's just talk about this for a minute. This might be new to some folks. Closure property is a way of saying, like, think of a box, like it's closed, right? There's an open box and a closed box. Closed says, I can't leave the set I'm in. So if you think about, this is why I have to mention complex little bit numbers, is there any way to add two numbers that are real and get a complex number back? And the answer is no. The answer is no. If you add or subtract or multiply, do any operation you want inside of the real numbers, I promise you'll get back another real number. There's no way to leave your set. Just to show you something that's not closed, like what's an example of a set that is not closed, let's take whole numbers for a second. So let's look at whole numbers, and we'll do 0, 1, 2, 3. That's enough. And now let's look at the operation under subtraction. So if I said to you, my universe is the whole numbers, I can only use whole numbers and nothing more, and let's talk about subtraction. So there's some things that I can do, like 3 minus 2 is a whole number, sure, right? 3 minus 2 is certainly a whole number. This is 1. I have not left my set of whole numbers. But now let's consider, let's grab any, remember I'm allowed to take any two numbers I want and subtract them. How about 2 minus 3? If my universe is whole numbers, and I look at 2 minus 3, I don't know what a -1 is. Nobody knows. It's a mystery, right? So the point is I've left my whole numbers, whatever this is. Even if you want to say this is -1, the point is it is not an element of the whole numbers. I've left my set. I need to consider more numbers somewhere out there. The real numbers being closed says you got them all. There's nothing else we really need to talk about until you start doing more complicated things. Now there are, things that we will need to talk about complex numbers for, but this is why we don't need to talk about them in this class. If I just stick to basic arithmetic, addition, multiplication, subtraction, division, I promise we won't need any other numbers. They're all in our set of real numbers. The set of real numbers is closed. That's kind of nice. It says we don't have to talk about complex numbers at least for quite a while. All right, so now this subtraction example talks about another point. The order mattered here, right? 3 minus 2 was 1. And 2 minus 3 was -1, the order matters. The fancy way to say that order matters is called the commutative property. COMMUTATIVE, the commutative property. Commutative property is commutative, say it right, commutative. This says that if I take any two numbers a and b, and I add them, a and b will always equal to, or a plus b will always equal to b plus a. And a times b will always equal to b times a. The informal way to say commutative is order does not matter. This is, you know this, right? If I take 2 plus 3, this is equal to 3 plus 2. I don't care if I take more complicated numbers. Pi plus 7 is equal to 7 plus pi. Does not matter. If I add, if I multiply, same thing. If I take 2 times 3 and I switch the order, it does not matter. Pick your favorite real numbers. I don't care if they're positive, negative, square roots, pi, e, who cares? I promise you if you add and multiply, order does not matter. This is important to realize though, I am only focusing on addition and multiplication. Why do I care about that? Because, when you have a new property, I want you to think about what is and what is not commutative. So the fancy way here, we say addition on the reals is commutative, and multiplication on the reals is commutative. But I just showed you subtraction is not. So subtraction is not commutative, right? 2 minus 3 is not equal to 3 minus 2. The other common operation, addition, multiplication, subtraction, and here's division, Think about it for yourself. Pause the video. Is division commutative or is it not commutative? And that's saying, does order matter? And hopefully it doesn't take too long to come up with an example. Division is also not commutative. Pick any two numbers you want. How about 2 and 3? Again, 2 divided by 3 is not equal to 3 divided by 2. 2/3 is not equal to 3 over 2. One is less than 1, 2/3 of a pizza, and the other one, 3 over 2, is like 1.5. So they're just different numbers. So the real numbers, some operations are commutative, some are not. What's nice about this is we tend to just focus on addition and multiplication. You'll see, or you'll think about it as subtraction is really just addition of negative numbers. We'll deal with that later. But we tend to focus on the properties that are nice. If you master addition and multiplication, you kind of get really good at subtraction or division. Let's talk about another property that we like. We have the associative property. The associative property says that if I have 3 numbers, I can put the parentheses wherever I want. So a plus parentheses b plus c is the same as a plus b in parentheses plus c. Does not matter. So again, just note that this is for addition. And I can also have the associative property for multiplication. If I have a times b times c, and I put the parentheses around the bc, this is exactly the same as if I move the parentheses around to a and b. So you have it for addition and for multiplication again. I leave it as an exercise to show that subtraction and division are not associative. The associative property is once again similar to commutative. Addition and multiplication have this property. Subtraction and division do not. Come up with some counterexamples. Pick it out. This says that when you start introducing more numbers, like 3 in a term or 4 or whatever, it doesn't matter the order at which you sort of start the problem, just the associative properties. We also have identities. So we have that the 0 is the additive identity. If I take any number and add it to 0, I get itself. And if I have 1 times any number, I get back itself as well. So this is your additive identity is 0. Your multiplicative identity is 1. And then since we have addition and multiplication, we tend to talk about the distribution property. This will be the last one. The distribution property, this talks about how does multiplication and addition play nice together. So if I have a number and I multiply it by some addition, b plus c, well, we know this is sort of bringing in to both. You're certainly allowed to go AB plus AC. This just formalizes that process, makes sure that nothing bad can happen, and guarantees that all the steps that you know and love will work out quite well. With these definitions of properties, if you want to get more fluent in a language of math, yes, start talking about the commutative property, the associative property, the identity property. However, most people just reference these as needed. If you see a direction or someone's talking about it, I want you to kind of keep in the back of your mind what these are and what these are not. And just remember that addition and multiplication tend to be the nice ones. Subtraction and division tend not to be the good ones. Let's just talk about order of operations for a second. Now this is important. Order of operations can really mess up your numbers if you don't use things correctly. In the States, when I was a kid, man, we learned this acronym PEMDAS. I think it is still taught, so I'm going to mention it. It breaks my heart to mention this, but I'm going to at least mention it because I think it's pretty common still. I think most people have seen this, maybe not. Maybe they're getting rid of it. If you haven't seen this, consider yourself lucky because it is not the best teaching tool. Of course, it stands for parentheses. So you have parentheses, exponents, multiplication, division, add, and subtract. Please excuse my dear Aunt Sally. That was the mantra we would say as kids to try to help us out and try to remember what to do first. It tells you what to do first. You read this thing left to right and says if you see an expression with parentheses, then of course you're going to do this first. Exponents come next. Multiplication, division, addition, and subtraction. The problem with this is that while it's got a cute little acronym and you can memorize it, it leads to some confusion if I give you, and once in a while these go like viral on the internet, let me do 4 plus 7, I don't know, divided by 5 or something like that. This is not a great way to write any expression, but you know, what do you do first? Maybe let me do one more, minus 2 times 3. How do you handle this thing? Well, according to PEMDAS, you would sort of go left to right and you would do the parentheses first. So this becomes 2 plus 4 and 7 is 11 divided by 5 minus 2 times 3. So let's clean up the parentheses. That's fine. There are no exponents, so don't have to worry about that. Now here's where the confusion happens, and this is why this is not a good teaching tool. The next thing in the list is multiplication. So one might be tempted to sort of do the multiplication first. I guess it's okay, but the point is, like, you can also do division. The multiplication and division go together, and you do them in any order. So there's no right or wrong order to do division. As you move from left to right, you do division. Maybe let me change this to a plus just to stress this point here. Change this to a product. So I'm going to do 5 times 2 minus 3. I'm going to change this up just to make a point here. So here's my question to you. So what is the point? What's the next right move here? You might be tempted to say, well, multiplication comes first in PEMDAS, so I have to do multiplication, but that's not true, and this is why this is a bad teaching tool. The right way to think about this is multiplication and division are to go together. So you would really do 2 plus, you do 11 over 5, 11 divided by 5, and then take that whole thing times 2. It would be wrong if you did 11 divided by 10, and from that you do 3, subtract 3. This is why PEMDAS is a bad tool, because these two can go in any order. You can do either one of these, and same for addition and subtraction. This is the part that most people don't realize. They think PEMDAS tells them what order to go, and so I'm starting to see an effort to get rid of PEMDAS. I think it's even like removed, but just because the teachers grew up with this, they're still saying this. So I don't love PEMDAS. What I like now is to think about the operations triangle, the pyramid, however you want to call it, of order of things to do. So this is the old way of doing things. Let's talk about the new way, the preferred way. People realize this is bad, and you sort of work your way as a pyramid top down. And this puts different operations on different levels. So sure, your parentheses come first. They also realized they completely forgot about brackets, so all of a sudden you start seeing like brackets appear as well. So any sort of parentheses or bracketing goes first. There's your P. Then of course they do exponents. Yes, that's all fine. Then you do, and by the way, exponents also go with roots. So they also realize they left roots off this thing. So if you see any square roots or something like that, you do those there. And they're equal in weight. And that's what this pyramid structure is trying to tell you. If you see one or the other, it doesn't matter, but you just do both. And your second pass through and your second cleanup, you do both. Then you do multiplication or division. They're equal as operations. So as you move left to right, you do either one. The order doesn't matter. And last but not least, you do any addition or subtraction here. So this is the pyramid, the triangle, that comes up with different names of it, but they're trying to get rid of PEMDAS and think of it as more of a pyramid with different operations on the same level, where you would do multiplication and division at the same time as you work through the equation left to right. Okay, so just to finish this guy up over here, this is really 22 over 5 minus 3. Just to clean this up, let's put this over a common denominator. So I'll put a 2 over 5. That just becomes 10 over 5 plus 22 over 5. No change there. And 3, let's write it as 15 over 5. You could, of course, grab the calculator here if you want. But 10 plus 22 is 32 over 5 minus 15 over 5. And then 32 minus 15 is 17 over 5. So final answer here is 17 over 5. If you want to think of this as a decimal, this is just 3.4. So however you present the answer, I don't care, as long as you get the right answer and understand the order of operations and sort of realize the weaknesses of PEMDAS if that's how you were taught. And again, if you never saw PEMDAS, consider yourself lucky. I want to just talk about rational numbers. Again, these are just a fancy way to say fractions. I want to show you some ways to do this. In particular, when you add or subtract fractions. You saw me do it last time where they do common denominators, but just a review. I don't actually want you guys to find common denominators. If you add and subtract a fraction, we're going to do a method called the bow tie method. This is equivalent. You'll get the right answer. It's just a different way to do things. So for example, if I have AB plus or minus C over D as fractions, I want you to do a bow tie. Now, if you've never gotten all fancy and formal, a bow tie is the thing that you put around your neck, and it has it's not a full-length tie, it's a little shorter. I don't know if you've ever worn one, but you'll see why it's called the bow tie method in 1 second. You take the top left times the bottom right, and then you grab whatever sign you're doing, adding or subtraction, put the plus or the minus, and then you do the top right times the bottom left. So C over B. That is, you can see the bow tie looking thing coming in here. That's the image. That's your numerator. when you add and subtract these things. Your denominator then, if you've ever tied a tie, the last step is to tie it tight, like you pull the bows out. That is corresponding to your product, BD. This fraction is your answer. Notice that I never found a common denominator, and I don't want you to either. You will thank me later when you do this. Finding common denominator is fine, but it's more steps. So for example, let's just do a quick example. Again, no calculator here. I want you to get used to sort of doing these things without a calculator. Again, we're trying to become fluent in math, and this is like if you're trying to have a conversation in another language, I don't want you to have to look every single word up in the dictionary. So let's do 1/2 plus 3/5. We're going to do this using bow tie. You can check it later doing common denominator, but just bear with me for a second here. Here we go. 1 times 5. You multiply the top left and the bottom right. That's 5. You grab the sign. That's plus. And then you do the other diagonal, so 3 times 2, and you get 3 times 2 is 6. That's your numerator. That's just good old 11. Then you tie the tie. Multiply 2 times 5, and you get 10. And of course, you get 11/10. Done. Done, done. Done, done, done. Just put a box around it. Works for subtraction as well. Let's do 4/3 minus 1/8. Why not? And let's do bow tie. So here we go. We do 4 times 8. 4 times 8, of course, is 32. Let's grab the sign. That's a minus. Let's multiply the off diagonal here, the top left, the top right and the bottom left. That's just 1 times 3. That's 3 over, now tie the tie, 3 times 8 is 24. So we'll put that together. 32 minus 3 is 29 over 24. Much faster, easier way, and here's where this is going. Eventually, we're going to replace these numbers with variables, and when you find common denominators with variables, it gets a little messy. This method is shorter. There's really no difference, honestly, but it's just this way will pay off when we do algebra and replace some of these things with x's and y's and all this stuff. So we just want to save this method. Keep this in mind. If you've never seen this before, again, this is called the bow tie method. That's how you add and subtract. It is only used for addition and subtraction. I'll put these down here, but just as a friendly reminder, if you multiply two fractions, I don't have any cute shortcuts and little stick figures with bow ties on them, you literally multiply across the top. So this becomes A times C, and then you multiply across the bottom, B over D. It's short enough already that you don't need a shortcut to do it, but I just want to remind you what it is. And last but not least, we have division. If you have a complex fraction, so this is AB like divided by CD, you tend not to see this division sign as you do more advanced math. So we'll do AB divided by CD as a fraction. This is like fraction over fraction. The rule for this, we say keep, change, flip. We keep the numerator, we change division to multiplication, and then we flip the denominator. Keep, change, flip. This turns division into multiplication. So if you've mastered multiplication, you know just to multiply across the top and multiply across the bottom. So your final answer is AD over BC. I'm not going to do some examples here, but just pick some numbers and check up with the calculator. Make sure you can do these. There's no cute shortcuts to this. The one that I do want you to try is bow tie, but just remember that it's only for addition and subtraction. All right, I want to show you a very classic proof, I don't know what to call it, but a very classic argument that -1 equals 1. Okay, so we all know this not to be true, but let's see if you can find the argument. Here goes. So I want to say that the square root of A times the square root of B is the square root of AB. If I multiply square roots together, then I can combine them under the radical. That's all fine. So now let's let A equals B equals -1. When I do that, I get the square root of -1 times the square root of -1, and that's going to equal the square root of -1 times -1, which of course -1 times -1 is the square root of +1. Two negatives make a positive, and that's equal to 1. Okay, so far so good. Also, here comes the second part of the argument. The square root of -1 times the square root of -1, by definition, this is the number squared that equals the thing under the radical. So this is -1 as well. Like square root of 4 times square root of 4 is 4. So hopefully everything on here looks okay, and therefore I just did things two different ways. If I compare the last line and the line above it, put these two together, therefore -1 as a number has to equal +1. There's something fundamentally flawed and wrong with this example. This is like if you were a teacher, you put a big red X on it and say no. Here's what I'd like you to do though. Pause the video and see if you can find it. Find where you can find the spot that there's a mistake. Ready? It happens right here. I'm not allowed to talk about the square root of negative numbers. The algebra here, this line's fine. That's true. But I'm talking about square roots. And so when you talk about square roots, remember I'm allowed to talk about only non-negative number. This implies that A and B are both non-negative. Otherwise, you go to the land of complex numbers, and we don't go there. We have a definer for that. So just remember, when you talk about square roots, under the square root can only be non-negative, which means 0 or positive. So I can't let A and B be -1. Anything after the wrong statement, I don't even look at. Once you make a wrong argument, everything's wrong. So the first piece is here. You can't let A and B be -1. Square roots are only defined, in our case, for positive numbers, for real numbers. So you can't make claims about the reals. All right, so hopefully you caught that. I just like this little one. I've seen people make really weird arguments and show me 0 is 1 or something like that. There's lots of these all over the internet. But I just want you to think about why these things are true or not true and start to get good at like realizing a lot of this depends on the definition. This is why we're stressing definitions early and often, so we get really good at working with real numbers. All right, great job on this video. We'll see you next time. All right, welcome everyone to our lecture on variables and equations. We're going to start replacing some of these numbers with letters. Of course, these letters can be good old letters A, B, C, D. We could do X, Y, Z, W. We could even do Greek letters, alpha, beta. It doesn't matter. But we're going to use these variables to sort of solve equations, and that's what we're after. And so before we start getting into like the technical aspects of it, I want to talk about the more theoretical aspects of it. Like if I write some expression, I don't know, W plus X equals 7, what does this mean? How are we supposed to approach this thing? Like the idea behind this for true equality is that equals really does mean equals. The two values on the left have to be the same as the value on the right. This is like the golden rule of equality. When you start treating and manipulating the left side, you have to do the same thing to the other side. Back in the day in school, the common picture that they used to give you was like a scale. Used to give you a scale, and whatever you put on the left side, however W and X were defined, whatever it would have to do would have to balance. This notion of balance, and you put a big block over here that's 7, and the scale can't tip, it has to be exactly equal. This notion of equality of these two scales balancing out is what we want to keep in mind as we go through the algebraic manipulations. What happens to students when they start seeing equations and equality is they become symbol pushers. You're not thinking about why you're doing what you're doing. Instead, you just know that I move this line over there or I do some algebraic notion. I really want you to think about like one side of the scale tipping up in one direction and then you adjusting to balance it back out. So we're going to go through some of these properties, and of course, I'm just going to list a couple down. Like if I start with something like 7 equals 7, well, you're certainly allowed to add or subtract things to both sides. So you're always allowed to manipulate the equation by adding. Let's take 7 plus x. Now I just added plus x to one side. The scale has tipped in one direction, so I have to add plus x to the other side. You can certainly subtract as well. No harm, no foul. Do whatever you need to balance this out. And of course, you can multiply. If I had 7 equals 7, I could do 7x equals 7x. I can multiply these things, multiply both sides by x. And of course, you can divide. Just make sure you're not dividing by 0. So let's divide by like 2 or something like that. You can divide by 2. Each one of these expressions is not because I'm writing the thing on the left, I'm writing the symbol on the right. It's I'm unbalancing the equation temporarily, and so I have to equate the equation. I have to solve for the equation. I've seen people do beautiful algebra on one side of the equation, and then all of a sudden they leave the other side blank. So we're going to work with lots of variables and play around with these things, and I just want you to be comfortable with any variable. X is obviously pretty common, but it doesn't have to be used. They call it, of course, dummy variables. So we can use anything we want, and I'm going to intentionally mix it up just so you don't get too comfortable with one. As we play around with equality, just keep in mind that not every equation has to be equal. There's also, coming our way, is inequalities. These are greater than, less than, strictly greater than, strictly less than. So equality is just one way to do things. When I have two numbers, let's say A is equal to B, I can play around with equality, and we can always write it backwards. So you always have three properties. And the first one is that you can write it backwards. So if A is equal to B, then you're perfectly allowed to say B is equal to A. We're kind of writing the rule book here so that you know what rules you break in case you get like a wrong answer or something like that. So we have if A is equal to B, then B is equal to A. This is called symmetric. Another property is if A is any real number, then of course it is equal to itself. A is equal to A. This is called reflexive. And last but not least, if A is equal to B and B is equal to C, then A would be equal to C. I don't want you to think about these just as numbers. I want you to think about these as really expressions. Think about simplifying. Maybe you know a little bit of algebra already, factor, foiling, but you're manipulating expressions. It takes, multiple lines. So if you have the first line and you start doing intermediate steps, this last property gives you that the first line will always be equal to the last line after you do all your work. The fancy way to say this, of course, is transitive. So here's a couple more definitions or things that I just want you to be aware of that you can do. Nothing perhaps surprising here, but I just want to write the rule book out so that we have it and then we know what to do as we go forward. Let's do just a couple of simple examples as we go through this. So if I tell you that 3x plus x is the square root of 10, let's solve for x. Okay, so we're going to try to look for things here. We have a nice equation. I have numbers, same degree, like terms as they call it. So 3x plus x, well, this becomes 4x. Let's combine the expressions. And this becomes square root of 10. Now, square root of 10 is a nice irrational number. Don't get scared by the square root of 10. I don't know what it is. I don't really care to get the calculator at this point. I'm just going to leave it at some number. If I need to work it out as a decimal, then I'll grab the calculator. But for now, square root of 10 is square root of 10. I have 4x equals 10. I want to get rid of this 4. I want to undo the process of multiplication. So I divide by 4. Whatever I do to one side, I must do to the other side. So x then becomes, cancel the 4's of course, square root of 10 over 4. It's some number. You're going to get to questions where the answer is not always so pretty like x equals 2. Be ready for numbers that look funny. And if your calculator has no problem, if you can go over to a calculator and compute square root of 10 over 4, then you should have no problem with it either. I don't really care for a decimal at the moment, so I'm just going to box this one up and say good enough for now. I care more about the steps just to solve for x and play around with this. Let's do another one. How about 4x plus 5x is 99? Add like terms. 4x plus 5x, well, that would be 9x's. And remember, that's still equal to 99. Don't lose the right side. Now we're going to divide by 9. When I do that, I get x is 99 divided by 9. Better way to say that, of course, is 11. So this one's a little nicer than before. We're just playing around, reviewing some basic algebra skills, making sure we're all on the same page. We're multiplying, adding, subtracting both sides. Let's do another example. Feel free to pause just to make sure you're on board. Again, it's early in the course, so nothing too crazy so far. But make sure you know how to do these. X plus 3, using all our properties. Solve for x. All right, there's a lot going on here. There's a few ways to do this one. I'm going to take the long road for a minute. 4 times an expression by the distributive property allows me to bring in the 4. For all the same reasons, I'm going to bring in the 5. This becomes 4x plus 4 times 3 is 12, plus 5x plus 15. And that is still 99. Notice I haven't changed the scale on the left side. I'm just simplifying the expression on the left side. 4x plus 5x, let's combine some like terms. Those are like terms. They both have a number, the coefficient, times the variable x. That's, of course, 9x. 12 and 15, well, that's, of course, 27 is 99. Now, there's a few things we could do here. We could subtract 27 from both sides. Maybe we'll do that. But I want to show you another thing we could do. 9, 27, and 99, they all have a 9 in common. 9 goes into all these things. So maybe what I'll do is I'll divide both sides by 9. You may not have done this step. I would imagine most people subtract 27. That is perfectly fine. Let's just see a different way. Let's get the right answer. I want to divide everything by 9. That means I have 9x over 9 plus 27 over 9 equals 99 over 9. I'm intentionally being non-traditional just to show you some alternatives of things you can do. Now the 9's cancel, and I get x plus 27 over 9, well, hey, that's 3, and 99 over 9, well, that's 11. Now I'll subtract the 3 to the other side. When I do that, of course, I get x equals 8. There's more than one way to do this. I could have subtracted 27, or maybe you realize you could have even factored out the x plus 3 at the top. I don't care how you do it. There's no right way or wrong way to sort of pick your method. Pick the method that's the most comfortable for you And as long as you get the right answer, we're fine with it. By the way, for all of these, at least if the numbers are nice enough, you can always go back and sort of check your work. This is a really good skill to develop. As the questions get longer and you do more steps, it's very easy to make small algebraic mistakes. Miss a minus sign, say 2 plus 2 is 5. It's a very human thing to do. So I don't care if you make mistakes, I just care if you go back and fix them. So I got x equals 8. I filled up, half the slide here. Let's go back. Is it really true that 8 plus 3 plus 5, 8 plus 3 is 99? I'll put a little question mark over the equal sign just to see if that's true. Then let's check. So we have 4 times 8 plus 3, 9, 10, 11, plus 5 times 11. Is that in fact equal to 99? Let's figure it out. Well, that's 44 plus 55. And of course, that is equal to 99. So that does work out. If I didn't get it to work out, I would go back and try to solve for my mistake, go back and fix the problem. These problems here, where an equation just appears and there's no backstory, there's no reason why we're doing it, we're just practicing. In the business, we call these a little bit of naked math. Naked math, like the numbers are just there. There's no reason, there's no rhyme or reason. Of course, as you specialize and go into some degree program or do these equations then pop up in applications based on whatever it is you're studying. So now let's look at actual word problems to prepare you for that moment. So here's the problem. Nico has 5 outstanding bills from a recent home renovation project that are each accruing late fees at $10 per day. The bill for the cabinets was due 1 week before the other bills, which were all for utility work. If his total fine was $870, how long was each bill overdue? Pause the video, read this again, go slow, and let's go through and see if you can solve it. Pause the video. Okay, you ready? The question that they're asking for, why this is harder, is because they don't give us the equation. They're asking for how long. So that's the unknown. Let's call that x. We could certainly call it any other variable you want. If you love y, then call it y. It does not matter. So I have 5 bills. 4 of them are for utilities. So I have 4 utility bills. And I have 1 for a cabinet. And they're accruing $10 per day. So the 4 utility bills, so I have 4 bills at $10 per day. What I don't know is the number of days. That's the how long each bill was due. So at $10 for the mystery amount of days. The 4 is there because there's 4 utility bills and then $10 a day. That I don't know. Now I have this cabinet, the 1 cabinet bill. The cabinet came in 1 week before the other bills. So whatever the days of the utility bills are, I have still $10 a day, but I have x minus 7. It's an additional, I should say x plus 7, sorry. It's an additional 7 days. So x plus 7 to the fee, the fine on the cabinet. And I know that when I add these up, when I add up the total, I get $870. My total fine is $870. All right, let's play around with this and solve this here. So let's simplify this a little bit. The first line for the 4 utility bills becomes 40x. The cabinet bill, we can bring the 10 into both pieces. This becomes plus 10x plus 70. All of that is equal to 870. It's all dollars here, so I'm not forgetting that, but I'm going to stop writing the dollar sign and I'll clean up the units at the end. So it's the skill, of course we're after now is solving for how long each bill was due. We have 40 and 10. Add them up, like terms, you get 50x plus 70 is 870. Let's subtract 70 from both sides, and we get 50x equals 800, and therefore x is 800 divided by 50, which is 16. Now be careful here. It's very easy to answer the question but then sort of forget about why you're doing this. This is the challenge of word problems. What does this mean? What's the units? When students leave off the units, I come in and put cats per donut, ? Just to pick some ridiculous unit. What does this thing actually mean? How long? With our time here, our units of time are days. So x is in 16 days. Now we got to answer the question. They asked how long was each bill overdue. So the 4 utility bills, they were each 16 days overdue. And the 1 cabinet bill, remember that came in a week earlier, so that's 16 plus 7. That's 23 days overdue. So the answer to this is not actually 16, it's 16 for the utility and 23 for the cabinet. They're asking for all the bills, so make sure you answer the question using the units. Let's do another example. Marco is 10 years older than Ralph, and 2 years ago Marco was 3 times as old as Ralph. How old are they all now? All right, so I have some information. Hidden, a little cryptic, but I can find their ages. So let's introduce some variables. We'll let m, of course, be the age of Marco. So this will be age of Marco. I have to be careful because we're talking about the present and the past, so I'll just specify this, but it's today's age. And then Ralph will be the age, so we'll use r for that. I could call it x and y. It doesn't matter. Again, I want to introduce new variables so you don't get comfortable just only working with x and y. So I have my m and my r. So Marco is 10 years older than Ralph. Whatever Ralph's age plus 10, that's Marco's age. This is my first equation. Now, 2 years ago, be careful, m minus 2, right? That's in the past. Whatever his age is today, he was 2 years younger. And they are telling me that he was 3 times as old as Ralph. So he's 3 times as old as Ralph. But be careful, Ralph, when in the past 2 years, this is also r minus 2. I have 2 equations, and I really need to solve for both variables now. So what I'm going to do is I'm going to use my first equation, m is 10 plus r. I'm going to take this entire equation and just substitute it right into the second equation. When I do that, I get 10 plus r minus 2 equals 3 parentheses r minus 2. This is a nice equation. I can solve for r. Let's go ahead and do that. So we have 10 minus 2, of course, is 8 plus r. And this is 3r. I'm going to bring the 3 into both pieces. 3r minus 6. I have an r on both sides. When you have that, you want to simplify and combine like terms. Let's subtract an r from both sides of the equation. When I do that, I get 8 equals 3r minus r, of course, is 2r minus 6. Now let's add 6 to both sides. We're going to isolate that r, and I get 8 plus 6, which is 14, is 2r. Divide both sides by 2, and you get that r is 7. Marco, who's 10 years older than Ralph, with Ralph 7, well, that puts Marco at 17. You should absolutely check. We just did a whole bunch of work. I really love to guarantee that this is correct. So why don't we just go off on the side here and check. Is Marco at 17 10 years older than Ralph, who we're claiming is 7? Is there a 10-year difference? Yes, so that's good. And 2 years ago, so what would their ages be 2 years ago? Well, Marco would be 15 2 years ago, and then Ralph 2 years ago would be 5. And so would Marco be 3 times as old as Ralph? That works out as well. So I can feel pretty good about my final answer, that Ralph's 7 and Marco is 7. So hopefully you got that as well. Before we move on to just other things, you're going to see once in a while this notion of absolute value. I'd like to remind you what it is. When I write down for any real number x, the absolute value, I put these bars next to it. And there's a couple ways to think about it. I think the wrong way to think about this, and this is like the way that I've seen people be taught, is it's not a magic eraser. It's not this like eraser of minus signs. It is the distance. I want you to think about it as a distance. You'll thank me later. The distance from x to 0. Why? Watch this. So here's our number line, and I put 0 on here, and let's put like 5. And if I want to ask you what the absolute value of 5 is, so you say, well, how far away am I from 5, from 0? What's the distance? Well, of course, that's just 5. I don't think the right way to think about this is to say, well, like, oh, it's positive, so erase the absolute value. It's really doing something. It's calculating something. It's not a magic eraser, because that also helps explain why, if I have negative 5 and I ask you, well, what's the absolute value of 5? 1, 2, 3, 4, 5. This would also be 5. So distance is always positive, or non-negative, I should say. It is perfectly fine to ask what the absolute value of 0 is. That, of course, is just 0. Why? The distance from 0 to itself is 0. So if you think about it in terms of a distance, this will help later if you go off and do geometry or you're trying to find distance formulas or something like that. It all makes more sense when you understand the absolute value as a distance. That'll also help you to answer questions about it, to solve expressions or equations using it. We'll do some of those in a second, but I really want you to think about it as a distance and not a magic eraser. The way that it works, in addition to just calculating things like, so if x is non-negative, then the absolute value of x is always itself. That's why we got the absolute value of 5 is 5. Absolute value of 10 is 10. Absolute value of pi is pi. If you're giving me a non-negative number, positive or 0, then the absolute value of x returns itself. And if the absolute value is negative, negative 5 or whatever, the absolute value, how does it work? Yes, it could sort of hop and count distances, but we want an algebraic way to do this. We're here to learn algebra after all. To turn a negative number positive, again, don't think of it like a magic eraser. When I learned this as a kid, like the teacher brought in this novelty, enormous eraser and was like, erasing negative signs. Not the right way to think about this. The way that it works is it actually multiplies by the number, it multiplies by negative 1. This is multiplication by negative 1. So why is the absolute value negative 5, 5? Because it's a distance. And what does the absolute value do? How does it turn negative 5 into positive 5? Well, it takes negative 1 times negative 5. That's the algebraic idea behind it. The geometric reasoning is just because it's 5 units away from 0. But as a negative number, it multiplies it by negative 1. So keep that in mind as we go through. Let's do a couple here. So let's simplify some of the following. So let's do one. Let's simplify. I'll give you 3. You pause and see if you can do it. Okay, so actually let's do 4. So I have the absolute value of negative 5, absolute value 10, negative of the absolute value negative 5, and negative the absolute value of 5. Take a second, go through them. Just remember how this works. I'm inputting a negative number to my absolute value. So as we saw before, this is negative 5. Of course, this is 5. How do I get there, though? I multiply by negative 1. Absolute value of 10. 10 is positive. I just keep it as is. No change. You get 10. Now be careful. We're going to start to put these inside of other operations. So now I'm taking the absolute value negative 5 and negating it. So I take my 5 from part A and I negate it. And so the answer here is minus 5. And one more time, if I negate the absolute value of 5, I'm negating 5 again, and I get just back negative 5. Let's do a couple more. Hopefully you went 4 for 4 on that one. I'll write them out, and then you pause the video and see if you can solve them. Give you some varying difficulties. Okay, pause the video, try to work these out. The first one is absolute value of x minus 6 is 6. B says the absolute value of x plus 2 is 10. C says the absolute value of negative x is x. And last but not least, D says the absolute value of x is minus 3. Pause the video, see if you can solve some of these. Ready? All right, let's go ahead and solve some of these things here. So we have absolute value of x minus 6 is 6. Now remember, there's really 2 ways to look at this absolute value. If x minus 6, let's think about this for a second. If the thing inside, if x minus 6 is non-negative, say like x is 7 or something like that. If it's all positive, so or 0, then the absolute values do nothing. They're just the same thing. X minus 6 is equal to 6. And of course from that, move the 6 over and you get x is 12. So that is a good answer, but that's not the only possibility. So the other way to think about this is if x minus 6, well, what if it's negative? What if the thing going inside the absolute value was negative? How does the absolute value work? It doesn't erase the negative sign, it multiplies it by minus 1. So I take the whole thing and I negate it, and that's going to still equal 6. And when you clean that up, you get negative x plus 6 is 6. Subtract 6 from both sides, you get negative x is 0. And then x is equal to 0. So you actually get 2 answers here, and that is not surprising. Why is that not surprising? If you think about it in terms of a distance on the number line, if you put 6 right in the middle, you could say, well, if I subtract 6 from any number, from what numbers do I get the number 6? It's a little weird because they're both equal to 6 here, but 6 on the outside is saying I want the distance to be 6, and 6 on the inside is where I'm starting. So if you sort of jump 6 to the right or jump 6 to the left, subtract 6, what numbers do you land at? Well, 12 and 0. So that's why it's 12 and 0 in terms of a distance. Let's keep going and solve some of these things here. I think the rest are maybe a little simpler. If we do B, we have the absolute value of x plus 2 is 10. Subtract 2 to both sides, and of course you get absolute value of x is 8. Now be careful, for all the same reasons as the other one, there are 2 numbers that have distance away from 0 to be 8. So when you do that, you get x is 8 or minus 8. You could write this, of course, as plus or minus 8 if you want to be concise, but really just recognize there are 2 answers. Let's keep going. For C, if I want negative absolute value of x is equal to the absolute value of x, I'm asking what 2 numbers give me the same. One way to look at this is sort of break it up into both pieces and say, well, what if x is positive? So if x is positive or non-negative, what happens to the absolute value? So imagine x is 7 or something like that. The left side becomes, what's the absolute value of negative x? Well, that's just going to equal x. And on the right side, we have x. So if x is positive, these two things turn out to be the same. What values of x are equal to itself? All values. Here we have infinitely many solutions. That's kind of nice. Every single non-negative number is an answer to this. You can test it. Plug in 2, plug in 3, plug in 4. They all work out. So the absolute value here is really nice. You get all of them. And you can check if x is a negative number, say like -2, then the absolute value of -2 becomes positive. So you get x on the left, and the absolute value on the right is also positive. So the answer to this one is all reals. This, I think, is our first example of an equation where we have infinitely many solutions. Infinitely many solutions. So it's good to point out that some equations can have one solution, as we saw. Some equations can have two solutions, as our A, B, and our A and our B showed us. And then some solutions can have infinitely many. So the answer here is all real numbers. All real numbers satisfy this equation. Pick any number you want, plug it in, and I guarantee that it's going to work. That's really neat to see. Last but not least, if the absolute value of x is -3, just in the interest of time, we're going to get to this one quickly. What values can I plug in absolute value? Remember, it always outputs a 0 or non-negative, positive. Can I get 0? Can I get a -3? Never going to work. There are no solutions. No solutions whatsoever. So we saw a couple of types of equations here in this video. One solution, two solutions, infinitely many solutions, and of course, no solutions. So all of these are possible. And so sometimes when students get these as answer choices, they think that something went wrong. Oh no, I got no solutions. That's okay. Assuming all your math is right. I got infinitely many solutions. That is also okay. So just be confident with your work, check your answers, and then, it's okay to get these different types of answers. All right, great job in this video. We'll see you next time. All right, hi everyone, and welcome to our lecture on linear equations in two variables. We're going to start off with equations, but of course we're going to visualize them and graph them, and I want to give them a home. So before we do anything with equations, I really want to talk about the Cartesian plane. Just a reminder what this is. The Cartesian plane, sometimes this is just known as the XY plane, and this is probably something you've drawn a million times. We draw two perpendicular lines. We put X on the left-right line, and Y labels are up down, and we have very nice Cartesian plane. Where the two lines meet is a very special place. We call that 0, 0. That is the origin. So the point corresponding to 0, 0 is the origin of any plane, of any Cartesian plane. In addition, these two axes, the x-axis and the y-axis, they partition the plane into 4 quadrants. The quadrant on the top right is called quadrant 1. The quadrant on the top left is called quadrant 2. And you work your way around going counterclockwise to get quadrant 3 and quadrant 4. So whenever we have points and we want to talk about what quadrant they live in, 1, 2, 3, 4, starting on the top right and going counterclockwise. The beauty of talking about the Cartesian plane is that once I pick some point, I can count over how many spots on the x-axis it is, I can count up and over how many spots it is on the y-axis, and I give that point a number. So we'll call point P, I give it 2 numbers, its x-coordinate and its y-coordinate. It'll be pretty clear from context which one it is, but in this particular example that I drew, this point is 2, 2. So you label points with the x-axis first, coordinates on the x-axis, and then the coordinates on the y-axis go separate. And our goal, of course, is not really to study points, but we're interested in lines. So I'll have some line that I'll be interested in, or perhaps I'll have more than one line, and our goal is to get equations for that and talk about things. The problem with drawing pictures by hand, of course, is that it's not as accurate as we want. If you use a computer to get it, well, then that's going to have limitations as well if you're trying to zoom in if the point isn't pretty. So we want some sort of algebraic way to study these things. Just to let you know, we might have more than one line. It's very possible that we have parallel lines, of course. Parallel lines are things that don't touch. And we might have perpendicular lines. So perpendicular lines are lines that intersect at right angles or 90 degrees. And we're going to be interested in all sorts of lines. And not every line is parallel. Some just intersect normally. Here's a nice line that's not parallel. Maybe it doesn't intersect either at 90 degrees, so it would be neither parallel nor perpendicular. So lots of lines to talk about, and that's what we're after. Let's do some quick examples just to kind of get a feel of where we're going. Draw the xy plane, draw the Cartesian plane, label, of course, your x and y axis, and let's do a couple of graphs. So if I said to you, part A, let's graph the line x equals 2. What does that mean? X equals 2. Think of all the points with x equals 2. You have 2, 0, so let's come out 2 spots on the x-axis. We have 2, 1, 2, 2, 2, 3. Hey, look at that. You can see the pattern happening. Of course, it goes in the positive and negative direction. That is the nice vertical line at x equals 2. We'll also label it as well. Get some brownie points there. What if I had the line y equals 3? What does that look like? So we go up 1, 2, 3. The height is fixed at 3. There is no particular x value for this. X is a free variable. It can be whatever we want. And so this, of course, is the line y equals 3, a very nice horizontal line. All right, so let's look at a couple examples here of different equations of lines. Pause the video for a second if you can and try to graph these lines on your own. On the side, draw your own xy coordinates, label x and y accordingly, and do a sketch. I don't need the world's most accurate picture, but do a sketch of the lines. In addition to the graphs of the equations, to the lines on the plane, I'm also interested in the x-intercepts. So this is where the graph crosses the x-axis and the y-intercept. So for each one of these, find the x and y-intercept. Okay, ready? Here we go. Y equals -2. What's that? We come down on the y-axis, -2 units, and that is a nice horizontal line right through y equals -2. We'll graph that, of course. Where does this graph cross the x-axis? What are the x-intercepts? There are no x-intercepts. Where does it cross the y-intercept? Oh, it does cross right there. This will cross at the point 0, -2. Let's get back the point itself for the intercept. If I wanted a coordinate of the point, I would ask for the x or y coordinate respectively. Let's do another one. Y equals 3x plus 1. The way I'm going to think about this is first I'm going to think of y equals 3x. That is a line through the origin. It has slope 3, so it's some positive sloping line. Again, this is just a sketch, so I don't need the most accurate thing. But then -1 translates this graph down. It's like grabbing the line as a magnet and pulling it down 1 unit. So in particular, when x is 0, it's going to go right through 1, and then it's going to be some line with positive slope. Not the best line I've ever drawn, but picture not drawn to scale, just drawing some sketches here. What's the general shape? If someone's talking to you about this line, you should have this image roughly in your mind. What are the x-intercepts here? What's the x-intercept? So the x-intercept is where the graph crosses the x-axis, but slowly, slowly, slowly crawling up, definitely less steep than our last example. So y equals 120 over x. Just the ballpark is all we're looking for here. If you drew the world's most beautiful picture and pulled out the ruler, good for you. But as long as you have something that sort of looks like this. In terms of its x-intercept, where does this graph cross the x-axis? Remember you set y to be 0. You get 0 is 1 over 20x, but that of course just implies that x is 0. And so the y-intercept and the x-intercept here are the same. Y-intercept let x equal 0, you get y equals 0. So both of these correspond to the origin at 0, 0. So again, the x-intercept and y-intercept can be the same. In this particular case, goes right through the origin at 0, 0. Now let's talk about linear equations. I think most of us have seen this before. If I asked you what is the equation of a line, I would imagine most of us would say y equals mx plus b. You've heard this before, I'm sure, for many, many, many years. Friendly reminder, what are all these things? M is the slope. This is the slope of the line, and b is our y-intercept, the y-coordinate of the y-intercept. And because when you look at a line in this form, you can look and read off the slope and the y-intercept, they call this the point-slope equation of the line. As an example, let's take y minus 3x equals minus 6. Let's do a couple things about this. Let's sort of say all the important pieces. What's the slope? What's the x-intercept? What's the y-intercept? Maybe we could even graph it. I want you to realize, though, in this point-slope equation, it's always y by itself on the left. You may not be handed that form, but that's okay. Let's add 3x to both sides, and we get positive 3x minus 6. So it is okay to do some algebraic manipulation to get this into point-slope equation of a line. And now we have y equals 3x plus 6. Now I can look at this and say that the slope is 3. Be careful. A lot of students will get this wrong and say the slope is -3. I can also say that the y-intercept is at -6. So the point would be 0, -6 would be your y-intercept. Once you have all this information, you're ready to go for the graph. If I ask you to graph this piece, you draw your xy axis. Again, just a sketch is fine. I don't need the most accurate drawing. I'm going to go down to 0 minus 6. That's somewhere down here. I'm going to graph this thing. This is a slope of 3. So I'm going to sort of crawl up as I go. A nice positive slope. And there we go. If I wanted it more accurate, I could find some other points. But for now, just this sketch is good enough. Something like that. Now, this is a great answer. If I said to you, what is the equation of a line? And you said y equals mx plus b, that's a really great answer. However, just realize it is not the absolute correct answer. If you want to see why that is, we need to move over to the standard form of a line. So let me graph a line first. Let me graph a line. Here, I'll put a 1 on the x-axis, and I'll draw a line right through it. So this is the line x equals 1. Take a second, pause the video, and try to put this into slope-intercept form. If you know how to do it, if you think you know how to do it, pause the video and do that. You'll see very quickly that you can't do that. This is the equation of a line. It's x equals 1. There is no slope for this. There's no slope for this. This slope we say is undefined. When I want something to allow for these vertical lines, I have to put a new form of a line on the map. ax plus by plus c is 0. This is our most general form. This is our absolute most general form of a line. This general form is called the standard form. You should know it's out there. There aren't too many things that we study that are like vertical lines. Are vertical lines a thing? Yes. Are they out there? Yes. Do we use them a ton? No. However, they're out there. The reason why you see things not in vertical form is because often you want to work with functions, you want to solve for y. Solving for y here is pretty quick. You take by and you move everything to the other side. So you move ax to the other side, you move the c to the other side, and then you divide by b. So minus a over bx minus c over b. And all of a sudden, you're back to, this is slope-intercept. So slope-intercept form falls out of standard form, but you got to remember, you got to be mindful of the steps you're doing. When are you allowed to actually do this? What would be the problem if b is 0? b is 0, I can't divide by 0. That breaks all the rules of math, so I have to be careful. b is 0, which means there's no y term. If there's no y term, I'm never going to get a slope-intercept form, because b is 0, and that would require that I divide by b. I can't solve for y if there's no y to solve. So in this particular equation for a vertical line, x equals 1, you're in that form, you're done. This is the equation, x equals 1. So just be mindful that the standard form is a more general form, and it captures vertical lines, whereas point slope is more useful, but it doesn't actually capture every single line out there. Now let's find the slope of a line. So let's say we're given a line, some line, and I have 2 points on the line. Let's say x1, comma y1, and another point, say x2, comma y2. I'm going to define a formula for the slope of a line, which we denote as m. This is the slope of a line, and we've seen this before. This is good old rise over run. Of course, this is all very informal intuition to it. It's really the change in y over the change in x. The change in y over the change in x. That triangle, by the way, is Greek letters called delta, and it measures the change in y. So this is how we measure change. And this is going to be y2 minus y1 over x2 minus x1. Let's see why that this is the formula that we're going to use to find slope. If I draw the point right at the sort of base of the triangle here, the right triangle, this point becomes, it has the same x value as x2 and has the same height as y1. So if I want to measure the change of y over the change of x, the change of y is my change of height, that's y2 minus y1, and the change of x's, the right side minus the left side, is x2 over x1. So you're measuring the rise over the run. The rise would be your change of y, your run is the change of x. A couple things that sort of fall out immediately from this formula. I'm going to leave these as exercises to you. Here's my question. What is the slope of a horizontal line? Take a second, draw a horizontal line, plug in some numbers and see what you get. I want you to check that the answer is 0. And here's another question for you. What is the slope of a vertical line? Now this one's a little trickier. If I have a vertical line, so think about the other equation we had before. If I have a vertical line, let's just put x equals 1 on the map. Pick any 2 points you want. How about 1, comma 1, and let's say 1, comma 2. The change in y over the change in x, you can see why the formula breaks down. The change in y is perfectly fine. This is 2 minus 1. But if I divide that by the change of x, well, there is no change of x. X is held constant, and all of a sudden you get 1 minus 1, and that's 0, and like all this breaks down. So when you have a vertical line, we say that the slope is undefined. There's no definition for it. That's because division by 0 is undefined. Let's work through an actual example where I find the equation of a line given 2 points. Let's pick a line that contains the points 1, 2, and 3, 4. Find the equation of a line through 2 points. So you can imagine you have your graph at 1, 2, you have a dot, and at 3, 4, and up here you have another dot, and so we're after what is the equation of the line through them. First thing first, I'm going to need the slope. Slope is the change of y over the change of x. So this is 4 minus 2 over 3 minus 1. That is 2 over 2, which is just 1. Very nice. Now, I know the equation is y equals mx plus b. I can tell by my picture that I don't have vertical lines, so I can start with that. And I know my m is 1, so let's plug that in. I get x plus b. So all I really got to do is find b. Well, how do I find b? I need to know x and y. Pick your favorite point. Doesn't matter if you pick the first one or second one. Let's just pick the first one. And you get 2 equals 1 plus b. Well, hey, we can do that. That's just b equals 1. So now you bring it all home and you get y equals, my m was 1, times x plus 1, better known as just good old x plus 1. Let me show you one more way to do this. It's perfectly fine to do it that way, but there's another version. If you know the slope, which is easy to calculate, you can rearrange the equation for slope and get something called the point slope equation. This is y minus y1 is m, x minus x1. Why is it called point slope equation? Because you know a point and you know a slope. If you know a point and you know a slope, you can plug it right into this equation and skip a few steps. In our particular case, we know 2 points. Again, we'll pick one. We'll pick the one with the smallest numbers just because it's easier to work with. And then we'll pick the slope, which we found. So let's plug it into this equation. I take y minus the y value of my point, so we'll work with 1, 2, is the slope, that's just 1, times x minus 1. Clean this up. The 1 distributes, the 2 gets added, and once again you get y equals x plus 1. You'll get the same answer, of course, either way, but I think you can see the steps here a little faster. So if you have a point and you have a slope, keep in mind this, what is now our third formula, third and final formula for the equation of a line. When we work with two parallel lines, you can draw these out together, they rise at the same rate. The way to say that officially is that parallel lines have the same slope. Hopefully that's obvious from the picture. Just draw your favorite set of parallel lines and it'll be the same. What is not immediately obvious, but you can try to work it out or take my word for it, if you have perpendicular lines, so lines that meet at 90 degrees, lines that meet at a right angle, their slopes, whatever the slope is here, this slope will be the negative reciprocal of that slope. So perpendicular lines have slopes that are negative reciprocal. So flip and negate, flip and negate. As a quick example of how you can use these things, let's find the equation of a line containing the point 0, -2 and parallel to the x-axis. So think about what we have. We have a point. If I had a slope, I could find the equation. I could use point slope. Parallel to the x-axis. What does that look like? Parallel to the x-axis. Well, if I'm parallel to the x-axis, I'm a horizontal line. That's a fancy way to say that my slope is 0, that m equals 0. So now I have everything I need. I have a point and I have a slope. So let's use point slope. I'll write it down one more time just so we remind ourselves what it is. But it's y minus y1 is m parentheses x minus x1. M is 0, so this whole right side goes to 0, and you basically get y equals y1. y1 is the y value, you get y equals -2. Let me do one more. Same thing. Find the equation of a line through -1 and 1 and perpendicular to the line y equals 2x plus 1. I think I can squeeze it here on the slide. Let's see if we can do it. Okay, so I have a point, once again, -1 and 1, and I want a line perpendicular to the line 2x plus 1. Remember that perpendicular lines have slopes that are negative reciprocal. So the slope of the given line is 2x plus 1. The slope that I want to work with is then negate and flip. So -1/2. Now I have a slope. Now I have a point. I'll use the point slope equation one more time to get y minus 1 equals -1/2 x minus -1. Watch out for that double minus, that turns to a plus. You get my y minus 1 is -1/2 x plus 1. Oftentimes when you're doing point slope, you can leave it like this. It's perfectly fine. If they ask you to put it in a certain form or put it into slope-intercept form, sure, clean it up, distribute however you want. I care more about right now that you can look at a line and know to grab either the same line if you work with parallel lines, or the same slope, or negative reciprocal slopes as you work with these things. Okay, so our goal here is to find equation of lines. We're going to see in the next video how to use technology to also graph and visualize these things. Great job on this video. We'll see you next time. All right, hi everyone, and welcome. I'm going to show you how to graph lines using a website that I really like. It's called Desmos.com, Desmos.com. Take a second, pause the video, and head over to that site. Once you get there, let's click the button that says, let's start graphing. And you're going to get a very nice sort of screen on the left. This is where you're going to enter your equations, and the graph will appear on the right. There's a settings bar up here. If you want, you can play around with the different settings that are there, but the standard one is usually pretty fine. And just to graph a couple of equations that we've seen, you could just start typing on the left side something like y equals 2x. As you type, you don't even have to hit enter. The graph, the line starts to appear. Feel free to zoom out or zoom in as you need, and you can start to see this graph. What's really nice about these things as well is that you can graph more than one line. So for example, if you wanted to graph y equals negative 4x plus 3, why not? I'm just making up numbers, but it will also graph the second line. Things start to get interesting sometimes where they meet. You can see that Desmos is already kind of thinking ahead and saying, well, you might want to know where the graphs intersect. So all you have to do is click on the gray circle, and it's there. You might want to know some intercepts, and they're already sort of called out for you. If you want the actual coordinates, just click on them, and you can see those. This is a really nice tool to get numbers pretty quickly. And you can make some pretty professional graphs if you just screenshot and play around with them. So that's really nice. So let's clear those by clicking the X button, and let's start again. One of the really nice things, again, like your calculator can do this, but what is the really nice thing that I like about Desmos? I explained before that the slope of a line, which we usually denote as m, is the rise over the run. It is the way to measure how the line is changing. When you introduce a variable like mx, it'll ask you if you want to add a slider. Go ahead and hit yes to that. And what that does, it lets you interact by dragging the slider around, and you can see the line for different values of m. This is really nice. So as we saw before, when m is positive, the graph goes from low to high. When m is negative, drag it over your favorite negative number, it goes from high to low. When m is right in the middle at 0, we have a very flat horizontal line. And what's fun about this too, there's a little play button here. You can move this along and kind of watch this thing go and see the whole spectrum of numbers. Feel free to click on the 10 or so to change it. You can make it to be -3 to 3. You can pick whatever values you want. Desmos is very interactive this way, but you can kind of watch this happen. So you can see the point, and you can also type in and override a number if you want as well. So that's really nice. So we have a nice slider here for m. In addition, in point-intercept form, there's also a number called b. b is the value of the y-intercept. It's where the graph crosses the y-axis. Now you can have two sliders. Again, another beautiful thing about Desmos. You can see that as I increase b, the intercept is getting larger. The intercept, the y value of the intercept, is always larger. As I make it negative, it meets the y-axis down here in negative land. And again, I can press play and let it run, and you can watch this graph. Oh, there it goes, too far. You can watch it move up and down. It looks like it's sliding left to right, but really just chase the intercept. You can see that this thing is moving up and down on the graph accordingly. What's kind of fun, and get ready for this, once you have a good understanding of how the y-intercept works, feel free to press play on m, and in addition to moving the graph up and down, you can also spin it, and then sort of sit back and enjoy the ride. It's a little bit like watching fire. This graph is moving up and down, spinning around. It's a lot of fun. It's great for modeling. You can see really what the pieces do. So have a lot of fun with this as you go. One other thing I want to show you, just since we're in Desmos, let me just show you this. You can also add a couple things. Often you work with data, and you have a table of data. You can also copy a spreadsheet in here as well, but let's just pretend for a second we had some data points, 1, 2, 3, 6, and let's make up some numbers, 4, -2, let's say -5, I don't know, what's your favorite number? And let's say 0, why not? Okay, so you get some scatter plot. it could be as large or as small as it wants. So you can paste it into from Excel into here, or you can just type it out. The variables in this case, notice when you have a table, it's not quite x anymore, it's x sub 1 and y sub 1. One of the ways to get a line through data is to use the line of best fit. Many softwares will do this for you. Different technologies will have different ways, but Desmos does this as well, and I just want to show you how. Remember, the variable is y1, so just be careful. When you do y, do subscript 1. Hit the right arrow to get it back on the main line. And when you're approximating, when you're doing the line of best fit, be careful. It's not equals. It's the squiggle or the tilde. So you hit tilde. Then you can do whatever you want. For us, it's a line, so we'll do mx1, be careful, x1, plus b. So things to watch out for. Sometimes students put equal sign here. It doesn't work. But it's mx plus b, of course, is your line. But just be careful. It's y1 and x1 because you're using table variables. Desmos does split that out. So if you type this in carefully, you will get automatically some statistics on here. If you know what r and r squared is, there they are. If you don't worry about them. But the thing we're more interested in is what is m and what is b, and all of a sudden you have, in a very quick and easy way, the line of best fit. So you can write down your formula, y equals negative 0.0428571 x plus b, and b is 0.0535714. Anyway, so a really nice way if you have a table to get the equation of a line, and then from there you can go off and do all the great things that we do with lines, understanding and interpreting both the slope and the intercept. All right, I hope that was helpful. Look forward to seeing you in the next problem. Keep Desmos open, graph as we go along. Really great visualization tool. See you later. All right, hi everyone, and welcome to our lecture on linear inequalities in one variable. Let's just talk about the title for a second. Inequalities just means not equal. So when you work with inequalities, you're going to be working with equations of the form x is less than something, who knows what. You could, of course, have that x is greater than something, who knows what. Or you can always add the less than or equal or greater than or equal. So I think we've seen these symbols before, but let's just make it official. What does it mean? So let's define one of them, and the rest will follow immediately. So we're going to let a and b be real numbers. And we'll say that a is less than b, written as a is less than b, if b minus a, if I take the difference, then I get a positive number, so a positive real number. On the number line, of course, you could think of this as just meaning that a is to the left of b if I draw this. So when I subtract, there is some gap, there is some space. From this, you can immediately write the opposite and say that b is greater than or less than equal to. So you can mix these all up. So this is our basic definition, and it's interesting to think of this as positioning on the real line. And when you subtract, you can sort of capture that gap, capture that difference. So now that we have this notion of inequality, what can we actually do with it? Let's talk about some properties of inequality. This will be our rule book that we have to follow when working and solving inequality. We're going to list out 4 of them. Here we go. The first one says either a is less than b, b is less than a, or a is equal to b. One of these 3 things has to happen. This is called the law of trichotomy. Either you're less than a number, greater than a number, or equal to the number. Nothing else can happen. Think about that for a minute. Convince yourself why that is true. If I start with an inequality, if a is less than b and c is some real number, then if I add c to both sides, the inequality does not change. The sign stays the same. Number 3, if a is less than b and now c is a positive real number, then if I multiply both sides, AC will still be less than BC. If you multiply by a positive number, that'll be exactly the same. And last one, if A is less than B and C is negative, then AC is greater than BC. This last one is the one we got to watch out for. I'm going to put a little star next to it. The key here is notice the sign changed when you multiply by a negative. Remember, division is the same as multiplication by a reciprocal, so if we divide or multiply by a negative, we must switch the sign. This is the only algebraic thing you got to watch out for. However, it's extremely important. Just to show you a quick example of that, hopefully you agree that 3 is less than 4. But if I take c to be minus 1, a nice negative number, and multiply it by both sides, minus 3 and minus 4, stare at this for a second. Which way does the sign go? Which is bigger? And of course the sign switches. So if you multiply both sides or divide both sides by a negative, the sign must switch. Let's do some examples to see that in action. Let's solve for the inequality 2x minus 1 is less than 4x plus 3. We treat these almost the same as equalities. However, we've got to remember the one exception. Watch out when you multiply or divide by a negative. As usual, we have x on both sides. We want to isolate x. We want to put it on one side. So let's move it over to the left by subtracting 4 from both sides of the equation. When I do that, subtraction's fine. Proceed as usual. 2x minus 4x is good old negative 2x. Minus 1, keep the sign the same. And now we're left with a 3 on the right side. Let's add 1 to both sides. Again, addition of numbers does not make me nervous, doesn't change anything. I get negative 2x is less than 4. And finally, divide both sides by negative 2. Oh, I just said it, divide by a negative. I'm going to put this in red so we are super aware that we're doing this. So watch out when you do this. When you do this, you get x is, change the sign, greater than negative. So final answer here is all x that is greater than negative 2. If I were to try to graph this on the number line, remember I'm handing back infinitely many choices here, I plot negative 2 and I sort of look at it as an open circle and I go off to the right. So any number greater than negative 2 will satisfy the inequality. You can always test this, pick your favorite number greater than negative 2 and plug it into the original one, and I promise you it will work. As another example, let's look at a little more challenging problem called the compound inequalities. I'm going to write negative 1 is less than 2x plus 3, which is less than or equal to 5. When you see something like this, just realize it's a lazy person's way of writing two inequalities at once. You can split this off as saying minus 1 is less than 2x plus 3, and, you got to get both conditions to hold, 2x plus 3 is less than or equal to 5. So when you see this compound inequality, it probably makes sense to treat it into two separate equations. We're going to handle both of them the same way, adding, subtracting, isolating x as we need. Just remember that if you multiply or divide by a negative, we must switch the sign. Let's go through that now. So let's subtract 3 from both sides. So addition and subtraction is not a problem. So we have minus 4 is greater than 2x. And now I'm going to divide by 2. But I'm dividing, so I just think about it. 2 is positive. Okay, I don't have to worry about the sign. And I get negative 2 is greater than x. So the left side is now done. Moving over to the right side, let's subtract 3 from both sides. When I do that, I get 2x is less than or equal to 2. Divide both sides by 2. That's a positive number. That's perfectly fine. And I get x is less than or equal to 1. So I'm looking for, remember there's an and statement in here, I'm looking for all x's that is greater than negative 2 and less than or equal to 1. And if I were to draw this on the number line, I put negative 2 on the map, I put 1 on the map. I don't want negative 2, I got to be strictly greater, so I'll draw an open circle, and then I'll head over to 1, and since I'm allowed to have 1 in here, I'll close the circle up, and I'll write this way on the number line. This is the set of numbers that I'm looking for. While drawing the number line and these open and closed circles is nice, you get to see what numbers are included and not. I tend to write this using intervals. If I want the number, you use a bracket. This is a bracket, and this means include the number, include the endpoint. If you don't want to include the endpoint, if you have an open circle, we tend to use parentheses, and this means we do not include the endpoint. So for this particular example, since I don't want negative 2, I would write this as parentheses negative 2, and since I want 1, I would write a bracket around 1. You can use a bracket or parentheses on either the left side or the right side. So we've seen two answers here. Depending on what flavor you want to do it, you can do an interval notation, parentheses negative 2 comma 1 bracket, or you can do an inequality. This is saying negative 2 less than x and x is less than or equal to negative 1. Maybe I'll write that just even a little more fancy and put it back together in a compound inequality. So I'll write it in inequality notation versus interval notation. And of course, we even have a little picture on the number line to represent either of these situations. Intervals are going to be our preferred notation going further. The pictures are nice, but we tend not to draw pictures. Intervals are just more concise, and it's really important that you get these down. So in general, there's a few different combinations of ways to write this. If you think about all the ways you can include or not include endpoints using parentheses or not, you can have parentheses on the left, brackets on the right. You can have brackets on the right, parentheses on the left. Pick your favorite combination. In addition, sometimes we also want infinity as an interval. When we do that, you'll see in a second, we always, since we can't actually include infinity, we always use parentheses. Okay, so here's just a bunch of them. I'm sure I'm missing a couple. Maybe we could even have negative infinity to b and include it, or we can have include a to infinity. There's a couple, I think these are all of them now, but there's a couple things I want to point out. If you use infinity, if you have infinity or negative infinity anywhere, we always use parentheses. You can't get to infinity, I can't include infinity, so this is just notation. We're always going to include parentheses with that. And just a reminder, if you have brackets, that means include the endpoint. If you have parentheses, that means don't. Any interval can be written, of course, in inequality notation. So let's think about the other way you could see this. This says I want a less than x less than b. If I go the other way here, this says I want a less than or equal to x, include the endpoint, less than or equal to b. And of course you can start mixing and matching. I want a, x greater than a, and less than or equal to b. And on this side I want to include a, but I don't want x to equal b. Now over here, a to infinity, what does that mean? That just means that x is greater than a. Any number you want. There's no upper bound. And on the other side, if I have b as my upper bound here, this just says that x is less than. When I have parentheses, I use the less than sign. If I have the brackets, then I can be less than or equal to a, and on the same side, I can be less than or equal to b. This very last case, when you have all possible numbers, negative infinity to infinity, this might be worth writing out again. If you have this, just realize this is the same as the set of real numbers. This is saying all reals. So our goal is going to be able to become comfortable with intervals and inequalities. Either way you want to write it, they're fine. It's just a matter of preference. Sometimes the directions will be clear, but otherwise you write it the way that you know how. Let's do another example. Let's look at x minus 1 times x minus 3, and we'll set this greater than infinity. Now, we have a nice inequality here. We have a product. One of the things I want you to fight the urge to do is to FOIL this. When you have an inequality, we sort of approach these a little differently. For a quick minute, and this is perhaps a little counterintuitive, so maybe I'll say we come off on the side, secret, you pretend that it's actually equal to 0. I know this is an inequality, but we set it equal to 0 for just a minute, and then you solve. And this is why you don't FOIL it, because we like it in factored form. When you solve it, you get x equals 1 and x equals 3. That you go off on the side to get those numbers. See where it's equal to 0, even though you're working with an inequality. Then you come back to your equality. We're going to draw what's called a sign graph. We graph the numbers that we just found, 1 and 3, and we put them on the real number. So this is called a sign graph. These numbers will partition, they'll split the real number line into different segments. When you have your different segments, you then grab any number you want as your test points. Always pick kind of easy numbers. I mean, don't pick like square root of 2 or something like that. Pick nice, easy numbers. So what's a nice, easy number to pick? Left of 1, how about x is 0? What's a nice, easy number to pick in between 1 and 3? How about x is 2? What's a nice, easy number to pick greater than 3? How about x equals 4? There's no wrong choice here. I just tend to try to pick the easiest ones. So when you make a sign graph, the first thing you do is you find the places where it's actually equal to 0 and graph them. Then you pick your test points, which we've just done. And then, here's the nice thing about this, we're going to plug in. Plug in to test if they work. Plug in. So let's see, does the numbers actually work? The beautiful thing about this is that there's no algebra. There's no algebra. Very hard to make a minus sign mistake or some other mistake here. So let's just plug in. We're testing to see if it works. So let's do the first one. X equals 0. Remember, you plug in your test points. When I plug in my test points, I get 0 minus 1, and I get 0 minus 3. And I ask myself, I say self, is this thing greater than 0? Let's find out. So we get minus 1 times minus 3. Is that greater than 0? Hey, that's just 3. Is 3 greater than 0? Absolutely. And so I put a little check next to the spot that works. So that means I want this interval. I want the interval at x equals 0. Let's do the other test point. Remember, the other one we picked was x equals 2. Here we go. We have 2 minus 1 times 2 minus 3. So I'm plugging in to the original equation. I am not foiling. I'm not doing algebra. I'm just plugging in. I'm doing arithmetic. 2 minus 1 is 1. 2 minus 3 is minus 1. And I ask myself, I say self, is this greater than 0? Hey, is minus 1 greater than 0? No. So that means I don't want the interval containing the test point. I don't want that middle interval. And then last but not least, let's test x equals 4. When I do that, I get 4 minus 1, 4 minus 3. Is that greater than 0? That becomes 3 times 1, which of course is 3. Is that greater than 0? Yes, absolutely. So I want them back. So our final answer will then be the combination of the two intervals containing our test points where this inequality was satisfied. That means we want everything to the left of 1. Remember, we don't want 1. Why don't we want 1? If you plug in 1, Well, remember we said we get 0, and we want this to be strictly greater than 1. So I want all numbers to the left, that's like negative infinity up to 1, parentheses, or I want everything to the right of 3. I don't want 3. If I plug in 3, I'm going to get equals 0, and I have to be strictly greater than 0. So I want 3 to infinity. So I have these sort of two intervals that I want to hand back, and I could write that with either an or, just write out OR, that's fine. If you want to get fancy, you can certainly write the union of two sets, 3 to infinity. This is the union, and that's perfectly fine as well. So you could write the union of the two sets to say or this interval or this interval, and again, pick your favorite number. I promise it'll all work there. Let's do another example. Let's look at x minus 1, x minus 3, and 5 minus x is less than or equal to 0. So we're going to make it a little more difficult now. We're going to put less than or equal, and I have 3 pieces multiplied together. 3 pieces multiplied together. Okay, remember, do not put these together. Fight the urge. We like factored form. Why? We go off on the side and we set it equal to 0 for a second to try to find the roots or the zeros of this equality. So we set it equal to 0. Don't tell anyone. I know it's an inequality, but when we do that, we get x is 1, x is 3, and of course x is 5. Those numbers then go on our sine graph. We love these kind of questions. There's no algebra to do. We map these, put them in the right order. So we have 1, we have 3, and we have 5. Then once you have your sine graph, you pick some nice test points. Pick your favorite points, something nice and easy. 0 seems good, 2 seems good, 4 seems good, and oh heck, 6 seems good. With 3 intervals, with 3 solutions, we're going to have 4 test points to do. Once you have your test points, you test the test points. Pick your favorite value. So let's pick x equals 0, and we'll plug in, and you ask yourself, is it true? Does it satisfy the inequality? When I do this, I get 0 minus 1, 0 minus 3, 5 minus 0, and I ask myself, is this less than or equal to 0? This turns out to be negative 1, negative 3, and then 5. Two positives, two negatives make a positive, and I just get 15. And you can ask yourself, is 15 less than or equal to 0? No. So I do not want this section over here. If, we'll do one more and I'll leave the rest to you, but let's test, let's say x equals 2. What happens if I plug in x equals 2? Then you get 2 minus 1, 2 minus 3, 5 minus 2, and you ask yourself, is that less than or equal to 0? When you simplify, you get 1 minus 1, and then 3. Put that all together, that's negative 3, and is negative 3 less than or equal to 0? Yes, it is. So we're going to want that middle interval. For the same reasons, and I'll let you go do this, you can check, you don't want the interval containing 4, and you do want the interval containing 6. So we want 2 intervals. We want the interval from 1 to 3. Now be careful. You have to ask yourself, do I actually want the number 1? Do I want the number 3? I want to write this out as like 1, 3, but I want to know, do I want to use parentheses or brackets? We saw before that if you plug in x equals 1, you actually do get 0. And since I want 0, I'm allowed to be 0 because less than equals. Yes, I want 1. And for all the same reasons, I want 3. When I plug in 3, I'm going to get 0, and that is allowed. So we use brackets here from 1 to 3. I'm going to combine it with the other inequality. This is the one from 5 to infinity, so I want 5 to infinity. Whenever I have infinity, I always use parentheses. That's not what I'm worried about. 5 turns it to 0. We said before that 5 turns it to 0. I want 5. So let's put them together with the big fancy union sign, and this will be our final answer. I want the interval containing 1 and 3, union, bracket 5 to infinity, and of course parentheses on infinity, of course, of course, of course. Realize what you're doing. You're handing back infinitely many answers. Handing back infinitely many answers for x. This is no longer the days of x equals 2, x equals 7. I have to hand you back a whole interval saying any one of the values in this interval will work. Let's do one more example with an absolute value just to see how these work. So as an example, let's do 2x minus 1 in the absolute value is strictly less than 3. Solve for x. When you have an absolute value, remember what this is saying. The inside could be positive or it could be negative. It's probably worth breaking this off into the two statements that the absolute value is trying to capture. So for example, if 2x minus 1 were positive, the inside thing were positive, the absolute values do nothing. And it's saying, hey, solve for me where 2x minus 1 is less than 3. That's if the inside is positive. But you got to remember, and people forget this sometimes, the absolute value is really testing two things. It says, well, what if it's positive? Then I'll step back and do nothing. But if it's negative, I multiply it by a negative Two negatives then turn that value positive. So if the inside expression 2x minus 1 is negative, I'm going to negate it. 2x minus 1 is less than 3. So this absolute value expression is really two things written at once. So we have to solve two things. That's fine. Let's do the left one first. We'll move the 1 over. I'm adding numbers to both sides. That's perfectly legal. So we get 2x is less than 4. Divide both sides by 2. Just remember you're dividing, so pause for a second, but it's positive 2. No big deal. And I get x is less than 2. On the other side, I got to solve. When I divide by negative 1, I get 2x minus 1. The two negatives cancel, and I have to switch the sign, and I get negative 3. Be careful, be careful, be careful. Make sure you switch the sign when you divide or multiply by a negative. Once you're here, then it's business as usual, and I get 2x is greater than, minus 3 plus 1 is minus 2, and then I divide both sides by positive 2. It's okay to divide by positive, you don't have to switch the sign, and you get x is greater than negative 1. In terms of the number line, let's think about what we want here. I have a negative 2, and I have negative 1 and 2 on the map. I want to be greater than 2, strictly greater than 2, so I want everything to the right of 2, but not including 2. I want to be greater than negative 1. When we draw a number line, I want to be less than 2, so I want to be everything to the left of 2, but I also want to be greater than negative 1, and what ends up happening is you get the interval right in between them. So the final answer, of course, here is parentheses, negative 1 to 2. It's extremely important when you do your parentheses to realize this is an inequality. You would never write the 2 first as it comes to the right of the number line. So final answer here in interval notation, negative 1 to 2, parentheses on both numbers. All right, go through some of these practice problems. Keep in mind the golden rule when working with inequalities. If you multiply or divide by a negative, you must switch the sign. Be careful writing and get comfortable using either interval or inequality notation. Great job on this video. We'll see you next time. All right, hi everyone, and welcome to our lecture on linear inequalities in two variables. What does a linear inequality in two variables look like, you might ask? Well, that's a great question. So it's a linear inequality. So first of all, let's get used to these terms. What does linear mean? Well, linear means that I'm going to have only variables that have like a 1 as an exponent. That's what linear means. There's no squared, there's no 1/2, there's no cubed or anything like that. It just means 1 as an exponent, as a linear term. We don't write the 1, of course, so you never get to see it. So it really just looks like a to the x, where a is some number, plus some other term, because now we have two variables. So the a and the b here are the coefficients. My variables are x and y. I, of course, could use any variable I want, x, y, a, b, c, d, whatever. It doesn't matter. And since it's an inequality, I need some sort of less than or greater than sign. Of course, less than equal or greater than equal works just as well. So we'll say less than just to start, and we'll put some other constant over here. So here, a, b, and c. These are capital letters. They're real numbers. They're constants. They're fixed numbers. And in place of the less than, of course, I could have always used less than equal, greater than, or greater than equal. Pick your favorite one, and you've created a linear inequality in two variables. Just to put some examples behind this sort of abstract, like what this looks like, let's start off with y is greater than x minus 3. This is a great linear inequality in two variables. My coefficients on x is 1. Again, we don't write that. My coefficient on y is also 1. My constant here is minus 3. What's another one I could use? How about 2x minus y is greater than or equal to 1? How about x plus y is less than 0? So it doesn't matter what inequality sign you use. It doesn't matter which way it faces. These are all great linear inequalities. And technically, since a and b can be any real number, there's nothing stopping me from letting them be 0. And even though it's an inequality in two variables, I guess I could write y is less than or equal to 0. That's perfectly fine as well. Okay, where are we going with these? What's the point? Normally, if I have an equality, I want to solve for x. I may have one answer for x, or two answers, or a couple numbers, who knows, or no solutions at all. We've seen examples like that before. With inequalities in two variables, it is the same exact idea. Now I want to find a solution. Our goal is to find a solution to the inequality, but I am no longer looking for just x. I'm looking for a ordered pair, x comma y, that satisfies the inequality. To satisfy an inequality just means when I plug in the x and I plug in the y, it means that it makes the inequality true. So for example, what is the solution here to y less than or equal to 0? Well, that could be 1 comma negative 1. There are obviously lots of solutions here, so oftentimes with linear inequalities in two variables, we're going to have to return back many answers, and often we do it via a graph. Let's take the example y less than negative 1/2 x plus 2. I'd like to graph the solution set. Where does the solution set live? Well, I still have x's and y's, so we're still going to draw the xy plane. I draw x and y on the xy plane, and just like we did before, we're going to go off on the side, and we're going to consider what if they were equal to each other for 1 second. Now I know it's an inequality, but don't tell anyone. What if it's actually equal? This is an equation of a line. So we're going to graph this line on the xy plane. We got to find a couple of points that make that work. When x is 0, we get y is equal to 2. So let's put 0, 2 on the map. And what's another good point we could use? When x equals positive 2, then y is negative 1/2 times 2. That's of course just negative 1. So negative 1 plus 2 is 1. So y turns out to be 1. So let's put 1, 2, and then 1 on the map. When I graph that line, because it's less than, I want to use a dashed line. Just like we use open circles to say, hey, don't include, or parentheses to say, don't include those points, I really don't want to include the point 0, 2. Why? So here's my question to you. Is 0, 2 a solution of the inequality? This is all our side scrap work here. Well, how do you know? Check it. Is 2 less than negative 1/2 times 0 plus 2? This is asking, is 2 less than 2? And last time I checked, 2 is equal to 2. So no. So I don't want these points. I don't want any of the points on the line. They don't satisfy this strict inequality. So we do a dashed line. What values make this work? What values satisfy this equation? We're going to do something now called the test point method. So just like we did before in the number line, we pick a test point, and this line splits the plane into sort of an upper and lower part. So you get to pick a test point. The easiest point, you could pick lots of numbers, but the absolute easiest point to pick is x comma y equals 0, 0. So we're picking our point right at the origin. Why not? As long as it's not on the line, we're great. So we pick the origin. I could have picked 100, 100 or pi. Pick your favorite point and test it. And you're going to ask yourself, if I let y be 0 and I let x be 0, is the inequality satisfied? Is the inequality true? And when you plug this in, you're really asking yourself, hey, is 0 less than 2? Of course it is. So that says that I want the region, I want everything to the left or underneath this line. That entire half plane is the solution set. This is the graphical representation of the solution set. It also should make sense that I'm graphing below the line because the y value is going to be less than the line, so you can graph this and see the picture here. So any point below this line solves this inequality. Let's do one more. Same thing. I'd like to graph the solution set. Let's pick an inequality x less than or equal to 3. Our solution set are ordered pairs on the xy plane. Let's go off on the side for a minute. Don't tell anyone. When we work with inequalities, we use our skills of equalities. Set it equal to 3 for a second, and graph the line x equals 3. Now we've done this. 1, 2, 3. This is a nice vertical line. Now I'm going to draw a solid line in this case because of the less than or equal to part. I actually want x equals 3. I want the line x equals 3, and I want any point on it. So when you have a less than or equal or greater than equal, we draw a solid line. If you have strictly less than or strictly greater than, we draw a dashed line. Now the question is, I want x to be less than or equal to 3. You could pick a test point. Why not? You could certainly pick 0, 0 and ask yourself, does 0, 0 satisfy? Is it a point that I want to keep? So if I grab the x value, that was just saying, is 0 less than or equal to 3? Of course it is. Again, I want x less than or equal to 3. This should convince you right away. I want everything to the left, and now you get to have fun. You kind of go bananas and you shade, there it is. It's the most fun in math you'll ever have. And you shade everything to the left. There's no pretty way to do this, to describe this. The actual answer is just x less than or equal to 3, but you have to realize we're in the xy plane, and what part of the graph, what section are we caring about, are we carving out to talk about? Let's do one word problem, and then we'll wrap this video up. So here we go. The post office defines the girth of a box as the sum of the length, twice the width, and twice the height. So I have to add up these things. So let's draw a box. So draw your favorite box. Friendly reminder, if I have a box, I have my length times my width times my height. So we're going to define the girth to be the sum of the length plus twice the width plus twice the height. So I have to draw the picture. Notice these good practices here. Don't picture a box in your head. Write it down on paper. Label your diagram. If you want X, Y, and Z, or A, B, and C, or alpha, beta, gamma, I don't care, but you have to introduce your own variables. Then, as you work through the word problem and get it out of a word problem, write the equation down. The maximum girth that the post office will accept is 130 inches. How do we turn that into an expression? Well, I know my girth, G, can be no more, is less than or equal to 130. If the length of the box is 50 inches, then that inequality must be satisfied. Then what inequality must be satisfied by the width and the height? So if the length of the box is 50, so we know that the length is 50. So let's plug that into our equation here. I know that the girth, which is 50 plus 2w plus 2h, can be no more than 130. What is the inequality? That's basically saying simplify this a little bit. So we just work with our algebraic rules of inequalities. Friendly reminder, if you multiply or divide by a negative, switch the sign. Here I'm going to do neither. I'm going to subtract 50. So I get 2w plus 2h. Subtraction or addition preserves the sign. And I get 130 minus 50, which of course is 80. I can factor out a 2, I can divide everything by 2, and I get w plus h less than or equal to 40. That is its most simplified form. That is a linear inequality in two variables. I can certainly graph this if I want. Just keep in mind, if you graph this, just due to the constraints, so this is a little bit new, you can't have a box with negative width, negative length, or negative height, so everything has to be positive. So if I were to graph w plus h less than or equal to 40, I would certainly graph things only in the first quadrant. If I graph my w and h axis, when w is 0, my height has to be 40, and when h is 0, my width is 40. So you want this triangle that's trapped, instead of the entire half plane, you want this triangle that's trapped in the first quadrant. Keep units or physical restrictions in mind as you do word problems, especially with inequalities or heck, even equalities. It's good advice as you go through these. All right, remember your rules. Have fun with these. Great job in this video, and we'll see you next time. Hi everyone, and welcome to our lecture on systems of equations. We're going to be focusing on linear equations in two variables. So a friendly reminder, what is a linear equation? So a linear equation is one of the form ax plus by equals c. A, b, and c, of course, are just some real numbers. We want them not to be 0, so that I actually have an equation. But this is standard form of an equation. You can certainly solve for y and get different forms. You can get the slope-intercept form or point-slope form, however you want to manipulate the equation. But realize this is a linear equation, and so in particular, its graph is a line. We're often interested in solving for these equations. We're often interested in seeing what happens when they turn into inequalities. So in this section, we're going to talk about more than one of these equations. We're interested in solving a system. So we're going to define our term. So we say a collection of two or more equations is called a system. So system is just a fancy way to say I have more than one. So for example, as a system of linear equations, I can certainly have 2x plus 3y equals 4 and 3x plus 4y equals 5. Pick your favorite numbers. This is a system of two equations. There's nothing stopping me from listing 100 more. Then I would have a system of 102 equations. It doesn't matter. In this particular example, we're going to start off small. We're going to keep things linear. You can certainly start adding x squared plus y squared, whatever. That's a different talk for another day. But we're going to start with two equations in our system, and they're going to be linear. And what we're after, what our goal is, we want to find the solution set of the system, and this is the points or the ordered pairs x comma y that satisfy both equations or all equations in your system. We're not interested in just solving 1 or 2 or 3. We want points or xy coordinates that satisfy all the. Let's see a couple of examples and actually solve some of these. Sure, you should know your rules of algebra, but just remember, I'm working here with two lines in these systems of linear equations. In your mind, where do these lines live? On the xy plane. And what do these lines do? Well, oftentimes they'll intersect. So there's line 1 and there's line 2. Oftentimes they'll intersect, and when they do, you have a point that lives on both lines. Any point that lives on both lines will satisfy both equations. So what we're really after, our solution set, will be the point of intersection, but we will see that not every line has to intersect in just a point. Just as a little hint of what's to follow, can you think of two lines that don't intersect, perhaps, on the xy plane? We'll see examples of this in a second, but just keep in mind, we're usually after intersection point or points when they occur. So now let's solve by graphing. Graphing is such a great tool for these systems of linear equations. I want you to go grab a calculator or open up Desmos, and I want you to throw these equations into your calculator. I'll give you a system of two linear equations. Here we go. X plus 2y is 6. 2x minus y is equal to negative 8. These are both lines. Graph them any way you want. In this particular case, I don't want you to graph it by hand. You could, and I think the answer here is going to be easy enough, but I'd rather use a calculator and practice finding your intercept. If they intercept at kind of a weird, non-traditional point, it's going to be very difficult for you to get that exactly. So go grab Desmos, and when you do that, you get a graph that looks something like. So pause the video and make sure yours matches. You have to zoom into the right window, of course, to find the point of intersection, but Desmos is so wonderful that it knows whenever you graph more than one, it'll call out automatically the point of intersection. All you have to do is hover your mouse over the point of intersection and the label, the answer, will appear. So our solution set to this system is the point -2, 4. The single point of intersection corresponds to the point that satisfies both equations. You can test, plug in x equals -2 and y is 4 to both equations, and it will work out. Let's do another example of a nice system of linear equations. So let's start with 3x minus y is 2, and 2y minus 6x is -4. Notice that the x and y's are given in reverse order. That's okay. You can certainly rearrange it if you'd like. Again, let's do this by graphing. Head over to your calculator or to Desmos and graph these two lines and tell me what happened. Ready? When you graph these lines, you're going to have a hard time finding that second line, in particular in Desmos. You can turn off, if you click these colored icons on the left in Desmos, you can turn them off, and you'll see what you're looking at really is the same line. These equations, while they are different, they have the same solution set. Let's see why that's true. Let's start with the first one. 3x minus y is 2. And let's multiply both sides by -2. Let's send -2 on the left and we'll multiply -2 on the right. When I do that, remember you got to distribute and hit both pieces. You get -6x plus 2y equals -4. Of course, a little rearranging will give you the 2y minus 6x is -4. So they are exactly the same. They have different equations, but they have the same solution set. So the solution set in this particular case is infinitely many points. If I draw a line and draw the same line again, how many times did the two lines meet? All the time. Every single point on that line is a solution to these system of linear equations. So the way to hand that back is you can write set notation. You're really just handing back the line. 3x minus y is 2. You're handing back infinitely many solutions. So now we've seen that systems can have one solution. That's where the two lines are different and they meet at a single point. They can have infinitely many solutions, as this example shows, where they have the same exact line. Let's do one more. As another example of a system of linear equations, let's look at y is 1/2 x plus 2, and x minus 2y is equal to 4. Take a second, graph these two equations, whatever format you need for your particular technology. If you're on a calculator, they often want you to solve for y. Go ahead and do it. But if you graph these, what do you get? Let's see. When I graph these in Desmos, I get two parallel lines. Now, what do we know about parallel lines? Well, parallel lines have the same slope. Let's see that from the equation. The first equation is in slope-intercept form. So you can look at the coefficient on the x and tell me that the slope is 1/4. The second equation, however, I have to solve for y to see that. So let's go ahead and do that. If I add 4y to both sides, I get x equals 4y plus 4. Let's solve for y. Move the 4 to the other side. So we'll subtract 4. And let's switch to the equation. So we get 4y is x minus 4. Then divide everything by 4, and we get y is 1/4 x plus minus 1. The slope is also 1. They have different intercepts. That's why they're different lines. These are not the same lines, but they're parallel. You can see that by looking at their slope. Now my question to you is, Well, if I'm after points of intersection, then I have parallel lines, they're never going to touch. So they have no points of intersection. That tells me that my solution set is empty. That's the symbol for the empty set, like a 0 with a slash through it. There are no solutions. There are no solutions. This can happen. This is okay. So you have to be comfortable now when you work with more complex objects, like a system of equation, having no solutions, infinitely many solutions, or one solution. In fact, a system of equations that has at least one solution, we call it consistent. So a system of equations with at least one solution is consistent. We saw this when we had two lines that intersected. This would be consistent. Your point of there's one solution. And we also saw that if we had lines that were exactly the same, their equations gave the same line. So line 1 is equal to L2. This is consistent with infinitely many solutions. The opposite, the third case that we saw, was when we had parallel lines. We had two lines that never touched. In this case, when I have no solutions, we would say we are inconsistent. So these words are used to describe the system. I can have a consistent system, which means I have one or infinitely many, or I have no solutions, in which I'd say the system is inconsistent. A consistent system with exactly one solution, we'd clarify this and call this independent. And a consistent system with infinitely many solutions we would say is dependent. So you can have an independent, consistent linear system, a lot of vocabulary there for you, or a dependent, consistent linear system. Okay, graphing is great. However, sometimes the calculator will either not work for whatever reason. It gives us back a decimal. Maybe we want closed form. We'd like some algebraic way to solve for these linear systems. So graphing equations of systems, it does visualize the system, tells us how many solutions it has, but we often want a simpler way to do this. We want some algebraic way. So the way we're going to talk about now is the substitution method. And let's look at an example. So let's start off with the system 3x minus y is 6. And the second equation will be 6x plus 5y is negative 23. Substitution says the following. Pick any variable you want and isolate it. Solve for it. So in this particular case, let's solve for y. I can write y as 3x minus 6. Once I have y, I then substitute it into the second equation. Or if I had solved for y in the second equation, I would substitute it in the first equation. It doesn't matter what you do, but you pick one variable and you isolate it and then you plug it in to the second equation. In particular, so I get 6x plus 5, parentheses, 3x minus 6 is negative 23. Clean this up a little bit and I get 6x plus 15x minus 30 is negative 20. Now I have a very nice linear equation that I can simplify and solve for x. Keep going. 21x is negative 23 plus 30. That'd be positive 7. And solve for x, you get 7 divided by 21, better known as 1/3. Now remember, you got to fight your urge to stop here. The x-coordinate of the solution is 1/3. However, to find y, I go back to the equation where I isolated y and I plug in. And when you do that, you get y is 3 times 1/3 minus 6, or 1 minus 6, which is equal to minus 5. So our solution is the coordinate x comma y. It's the point of intersection 1/3 comma negative 5. You can go ahead and check that 1/3 comma negative 5 does in fact satisfy both of the original equations. Let's do another one. Let's take the equation y is 2x plus 1,000, and let's do 0.05x plus 0.06y is 400. Now, the first equation has done us a little bit of a favor. It has already isolated the first variable. So we might as well use that and just plug that into the equation for y. When you do that, you get 0.05x plus 0.06, and here we go, use parentheses, 2x plus 1,000 equals 400. Now, I'm going to leave this as an exercise, but you can absolutely solve this, distribute as needed. It's okay if you're working with decimals. So now we have another linear system with only x inside of it, so we can simplify this. It's okay to work with decimals, get comfortable working with decimals. Grab the calculator if you need. We're going to distribute that 0.6. When we do that, we get 0.12x plus 60 is still equal to 400. Clean up a little more, combine like terms, you get 0.17x is equal to 340, and solve for x, you get x equals 2,000. Remember, I'm not just interested in x, I also want y. How do I get y? Go back to the original equation, plug in x, and when you do that, you get y is 5,000. So our solution is x equals 2,000, y equals 5,000. Go ahead and check, plug them back into the original equations, and you'll see that it in fact works. What does the algebra look like when I have an inconsistent or a dependent system? Watch what happens. So let's start off. Let's look at the linear system. 3x minus y is 9, and 2y minus 6x equals 7. Let's go through and solve this using substitution. Doesn't matter which equation you pick. I usually pick the first one just because, but when you isolate y, you get y equals 3x minus 9. I'll then substitute that back into the second equation. I get 2 parentheses, don't forget the parentheses, minus 6x is 7. Let's solve for x, so we'll distribute the 2. You get 6x minus 18 minus 6x equals 7. My goal is to solve for all x's that make this true. The 6x's tend to cancel, and all of a sudden I get negative 18 equals 7. Oh boy. Now, students get to this point and they panic. They say, what happened? I must have done something wrong. And they'll go back and do it again, and they get the same answer. They get something like this. The way to read this, the way to interpret this, is to ask yourself, what values of x make negative 18 equal to 7? When is negative 18 equal to 7? Hopefully, you say, wait a minute, it's never equal to 7, and that's okay. Assuming all the other math is right and you get this, just realize that there are no solutions. There are no x values that will make negative 18 equal to 7. Don't panic, everything's okay. This is the algebra saying that there's no solutions, which graphically, what does that mean? Again, you can go graph these if you want. When there's no solutions, there's no points of intersection. When you get some really weird false statement like this, it means the lines are parallel. So you got to promise me when you get this, you're not going to panic. You just realize the algebra is saying no solution. Let's do one more. Let's look at 1/2 x. Let's look at one more. Let's look at 1/2 x minus 2/3 y equals minus 2. And 4y equals 3x plus 12. Okay, same thing. Let's try to solve for the variables. Let's follow the same method as before and isolate y. In this particular case, I think it's easier to work with the second equation. If we divide both sides by 4, we get y equals 3/4 x plus 3. I then substitute that value of y into the first equation. I get 1/2 x minus 2/3, big parentheses here, 3/4 x plus 3 equals minus 2. Distribute the negative 2/3 in. When you do that, you get negative 1/2 x minus 1/2 x minus 2 equals minus 2. The negative 1/2 x and the positive 1/2 x, they cancel. And the negative 2's, if I add 2 to both sides, all of a sudden I get 0 equals 0. This is another one of these equations. You could also have stopped and got negative 2 equals negative 2. That's fine too. But this is another one of the things that sort of freak students out and they start to panic. They think something is wrong. Everything is okay. No problem here. Ask yourself the same question you did before. What values of x make 0 equal to 0? This statement's an identity. It's always true. Every value of x makes 0 equal to 0. That's always true. So the solution set here is all reals. You're in the case when you have infinitely many answers. Your solution set is minus infinity to infinity, sometimes written as just r. And what this algebra is trying to tell you is that you have the same lines. If you graph this, you'll find that the lines turn out to be exactly the same. I want to show you one more method. There's more than one way to solve these, and sort of pick your poison what you like. Let's do one more system of linear equations. Let's do 3x minus y is 9, and 2x plus y is 1. The addition method is when you look at this and say, you know what I can do to these equations? Let me just add them. Usually this is a nice method to do when there are some obvious cancellation that's going to happen if you add or subtract. When I do this, when I do the addition method and add these, I get 5x, the y's cancel, is 10. You get a much simpler method. It's another easier way to eliminate a variable. And then of course right from here I have x is 2. I don't want just x, I also want y, so now you pick any equation, first one or the second one, it does not matter, and plug in. So if I plug into the first one, I get 3 times 2 minus y is 9, or 6 minus y is 9, subtract 6, and you get minus y is 6, so y is minus 6. So your x coordinate is 2, your y coordinate is minus 6. This is a nice way to do the addition method. It's a little bit of a shortcut. Once you have your value for x, go ahead and plug it into any equation you want. It does not matter. Remember, it's got to satisfy both, so pick the easiest one you want. If you plug it into the first one or you plug it in the second one, you can check, but you get y equals negative 3. Go ahead and check that these points do in fact satisfy the system. We have a nice consistent system. Again, in your head, you want to think about the xy plane with two lines looking like an X. They cross and they meet at a single point. Let's do one more. What if I had 2x minus 3y is negative 2 and 3x minus 2y is 12? Now you say, well, the addition method here may not apply. I don't have some immediately obvious thing that if I started adding or subtracting would cancel. And that's true. So maybe substitution would be better here, but I just want to show you can do something to make these things cancel if you want. I can certainly multiply the top equation by 3, and I can certainly multiply the bottom equation by 2. You are allowed to do any algebra you want as long as you don't break any rules. So whatever I do to the left side, I must do to the right side. So don't forget to multiply the right side by 3 and multiply the left side by minus 2. When you rewrite those systems, we then get a new system of equations. They're equivalent, but you get 6x minus 9y is negative 6. And the second equation becomes minus 6x plus 4y equals minus 24. Now it's more obvious that I should add these together and use the addition method. And when you do that, the 6 and the negative 6 cancel. You get minus 5y plus 4y, that's minus 5y, and then you get negative 6 minus 24, that's negative 30, and of course that means that y is 6. Once you have y is 6, pick any equation, first one, second one, the revised one, either one you want, plug in, and I'll leave it to you to check me, but you get x equals 8. Any equation you want, go ahead and pick another one. So your coordinate here is 8, 6. That is the solution to this system of linear equations. Let's do one word problem. Joseph made $25,000 profit on the sale of his condominium. He lent part of the profits to Nicholas at 10% interest and the remainder to Orlando at 8% interest. If he receives $2,200 in interest after 1 year, then how much was lent to each business? Take a second, pause the video, try to work this out. So we're all on the same page. We're going to need to introduce our own variables here. They're asking how much was lent to each business, so let's call x the dollar amount lent to Nicholas, and we'll let y be the dollar amount lent to Orlando. Now this question is saying solve for x, solve for y. Try to set up the equations that correspond to this word problem. Ready? What's the first equation? I know that I lent some money to Nicholas, and I know that I lent some money to Orlando. So x plus y is $25,000. And I also know that my interest received, $2,200, was at 10%. Careful, 10% is 0.10, or just 0.1, I guess is fine, of what I lent to Nicholas, and 8%, 0.08 times y. From here, I have a nice system of equations. To solve this system, it does not matter which method you pick. For no good reason, I'm going to pick the elimination method, so I'll multiply the top by negative 0.1. And when I do that, I get negative 0.1x minus 0.1y equals negative, now remember this is just 10%, 2500. And I'll keep that with the second equation, positive 0.1x plus 0.08y equals 2200. Now I'm going to add the equations, and the reason why I do that is to eliminate the x. You get 0 for x. I get 0.08 minus 0.1. That is negative 0.02y to negative 300. Divide by negative 0.02. Then you get y is 15,000. Remember what this means is word problems, so be mindful of the units. This is $15,000. If the total numbers have to add to 25, I can take y and plug it back in, and that gives me that x must be $10,000. So we can answer the question saying that Nicholas was lent $10,000 and Orlando was lent $15,000. Go back and check. Make sure these numbers solve the system of equations. Great job on this word problem. Great job on all the algebra graphing that went into solving these systems. We'll see more applications and look at inequalities in the next video. All right, hi everyone, and welcome to our lecture on systems of linear inequalities. So friendly reminder, what do all these words mean? Well, system just means we're going to have more than one. So I'm going to give you a list. That could be 2, 3, or 3,000, who knows? And of course, linear means that everything is going to be linear in nature. What does that mean? I'm going to have terms of the form ax plus by, and then inequalities, of course, means I'm going to have less than or equal or greater than or equal. So start putting it all together, and we get a nice example. Again, there are many of these I could start with, but let's just take x plus y is greater than 5, and x minus y is less than 9. Here's a system of linear inequalities, 2 linear inequalities, and we're interested to solve the inequality. We want all solutions, all points, order pairs x comma y, that satisfy both of these. Remember, this is not an or condition. I don't want one or the second one. I want all of them, the first one and the second one, and if I had more, third one, fourth one, you just name them all. So really, when you think of this, you really want to think of this as the first one and the second one. And for example, what would be a point that I could pick? Well, how about, let's pick the origin. Is the origin 0, 0 a solution to this system of linear inequalities? Well, how would you do that? You would check, does 0 satisfy both equations? So does 0 plus 0 greater than 5? Once you have one that fails, of course 0 is not greater than 5. Once you have one that fails, we do full stop, and we can say that the origin is in fact not a solution. Now, of course, just because the origin is not a solution doesn't mean that there are other points that are solutions. So let's do another one. How about 4, 2? Let's check 4, 2. Let's plug in, is 4 plus 2 greater than 5? Well, that's true. Let's try the second one. Is 4 minus 2 less than 9? So I have a yes to both. So the answer then, yes, 4, 2 is a solution. The solution set to a system is generally a region in the coordinate plane. It's usually a big area. It's not just one or two particular points. It's the intersection of all the solution sets to the individual inequalities. So we're going to treat this system one inequality at a time. And to find a solution set to a system, we're going to graph the corresponding equation to each inequality in the system, and then we're going to test a point in the region to see if it satisfies it or not. So it's very similar to a single inequality, but now we just have more to work with, and we just have to be a little more careful. Be very careful here. When we talk about systems of linear inequalities, you can also talk about non-linear inequalities. But what is it? What's the difference between the two? Linear inequalities means that every equation or inequality in the system is linear. When you see this word in front, every single thing is linear in whatever we're talking about. Here, since we have inequalities, we'll write inequalities. So I have x plus y greater than 5, 2x plus 3y less than 7, and maybe x is greater than 0. Each one of these is linear, so we have a very nice linear system of inequalities. However, be careful. You can certainly have non-linear inequalities. So what would an example of that be? Even if you have x plus y greater than 5 and 2x plus 3y less than 7 and x greater than 0, all I need is some non-linear piece. Let's say x is greater than y squared. All of a sudden I've left the world of just x's and y. I have something as simple as an x squared, and it only appears once. However, once it appears, you automatically move over to a system of non-linear inequalities. It's almost not fair to the linear pieces of this system. All it takes is one non-linear term, and we call the entire system a non-linear system of inequalities. So when we say linear system of inequalities, appreciate how strict that is. It says that every single inequality, or if we're working with equations equality, every single one of the system is in fact linear. You can't break this linearity requirement at any place along the way. Let's do an example. let's look at the linear system of inequalities x plus 2y less than or equal to 4 and y is greater than or equal to x minus 3. Appreciate these are both linear, and appreciate this is both inequalities. I have a nice linear system of inequalities. How do we handle these things? Well, both of them together are lines. So you treat each one individually, and we're going to graph on the xy plane what these things would look like. Now, the first one is not in the standard slope-intercept form. You can certainly go off on the side. Shh, don't tell anyone. Usually you set them equal to each other. You take x plus 2y and you set it equal to 4, just for a minute. Solve for y. 2y is equal to negative x plus 4, and so y is equal to negative x over 2 plus 2. This is a slope with negative 1/2 and intercept 2. The inequality, to go back to the inequality, is less than or equal to, so we're going to do a solid line, and give or take it'll look something like that with negative slope, and this is, we'll label it x plus 2y is less than or equal to 4. Notice I draw the solid line and not the dashed line, because of course the inequality is less than or equal to. We can do any test point we want. The origin is perfectly fine here as a test point. If you pick the origin, 0 plus 0 will in fact be less than or equal to 4, so I'm interested in all the entire region sort of under this line. But that's not the only line I have to worry about now, not the only inequality I have to worry about. I also have y is greater than or equal to x minus 3. So if I go off on the side and set it equal to it for a second, I have the line y equals x minus 3. Now this is a nice line. It's got positive slope of 1, has intercept negative 3, and it looks something like this. They don't quite meet at the x-axis there, but we're doing a sketch here. So we have y equals x minus 3, and I want everything that is greater than this line. You can test the origin. Is it true that 0 is greater than or equal to 0 minus 3? Yes, it is. So on everything above the line, so we'll start drawing our region here this way. And the solution to this system is the points that intersect, where the two regions overlap. This corresponds to everything that's above my blue line, and including my blue line, as well as below my green line. So it's this region sort of down here. If you're looking at it as an X, it's like the left side. Any point, there are infinitely many points, this entire region is the solution set. I cannot list this out for you. I can't hand these back one by one like I was able to do with other systems when I only had one or possibly two solutions. Here, I have an entire region. So often, we solve this just by graphing, and we look at the region, and it's easy to tell, draw a nice diagram, label points correctly, where the region is. That was a solution by hand. If you were to do this a little more fancy using Desmos or some other similar software, you get a picture that looks like this. Remember, it will draw the lines, it will shade, and in Desmos is great, it darkens the overlap, and you can also see from a clearer picture that the region that we're interested in is this area to the left of the line. Often the graph is enough for these sort of things because I can't list out every single point. Let's do another example. Let's look at y is less than x, and y is greater than 3 minus x. Appreciate for a second, this is a nice linear system of inequalities. Both equations, both have just x's and y's. You're okay to have constants. That 3 is perfectly fine. But there's no x squareds or other functions like that, other expressions. So this is a great linear system of inequalities. I want you to pause the video for a second and graph this. Do a sketch by hand. See if you can shade the regions correctly. See if you can find the points where they overlap. Test your points. Ready? It's very similar to the last problem. So I did it in Desmos for you. You can see that the red area is the line y equals x. This is the line y equals x. Goes right through the origin. It's a dashed line because of that strict inequality. The other line, the line with negative slope, is the line y equals 3 minus x. That's a dashed line. They meet at point 1.5, 1.5. If you want to find the overlap of these two regions, we're going to be taking now the part to the right of this x that these two lines form, this shaded region in the Desmos diagram, and everything on this right side, sort of below the line y equals x and above the line y equals 3 minus x, is going to be our region that we care about. We don't want the borders because of the strict inequality, so we use dashed lines to express that. Oftentimes, these regions, to graph them by hand or just a sketch or use technology, that's fine. However, what are some other questions that you might get asked? You might just get asked, does a point satisfy the system? Those are easy questions to answer. You just check, and just remember that any point has to satisfy both. So you plug in negative 2 for x, you plug in 1 for y, and you just check. Does negative 2 minus 2 times y, which is 1, is that less than 3? And what about y, and, of course, 1 minus 3 times minus 2, is that greater than 5? If the first one is not satisfied, then you do a full stop. But let's clean this up and work it out. Try not to do too much in your head, especially with all these negatives. Is negative 2 minus 2 less than 3? Is minus 4 less than 3? Yes, of course it is. So that one's checked. And on the other side, the second inequality is 1 plus 6 greater than 5. Well, of course it is as well. 7 is greater than 5. So we have yes to both of these. Because it satisfies both inequalities, we can say that the point negative 2 comma 1 does satisfy the system of inequalities. Now I know that we're supposed to be talking about systems of linear inequalities, but I just want to give you one example since I did mention the nonlinear case. If you have some fancier system, let's say y is greater than x squared, y is less than x plus 6, and y is less than minus x plus 6. Here's 3 inequalities. It's okay. We can handle it, right? We can plug them into Desmos if we need. Notice because of the very first one, this is a nonlinear system. And that is, of course, because of that x squared that is appearing in the first inequality. So we have a nonlinear equation, nonlinear inequality, which is giving us a nonlinear system. However, we can still talk about the solution set, all the points that lie in the region. You know how to graph these, so we're going to graph them very similar. Draw the xy plane. Let's draw the parabola y equals x squared. We can do a sketch by hand here. Goes right through the origin, goes up. And I want the y values to be greater than x squared. So of course this corresponds to everything above or inside the parabola. There's the nonlinear part, this nice bent curve. We also have the line y equals x plus 6. That's a line with positive slope. That goes right through 6. So that's going to be somewhere up here. So there's our line y equals x plus 6. The inequality that I want is y less than. So I want everything sort of below the graph, so I want to shade in the region to below the graph, and I need one more here. I want to run out of colors. I also have the line y equals negative x plus 6. This is another line that has intercept 6 but negative slope, so when I plug in 0 and have negative slope, it's going to go the other way. And once again, since y is less than this, I want everything below the red line. It's getting a little messy with all these colors and overlap, but I hope you can see where they actually do this. This is why it's really good to do this in pencil. You can erase the part that doesn't have overlap. There's a nice region, and these should all be dashed lines because I don't want the boundaries. There's a nice region that's happening inside of this parabola. There's still infinitely many points. Let's see if I can erase the parts I don't want. I want to keep everything that's inside the parabola and below the green line and the red line. This is a little bit of a hand sketch. If you want to do it officially in Desmos, of course, it does a nicer, cleaner, prettier picture. The region I was trying to draw is the dashed line that occurs above the parabola and below the two lines. You can see the points of intersection. Again, you can solve for those by setting the equations equal to each other, using substitution to find all that. But it's okay if you get nonlinear things. Treat them exactly the same. Don't get scared. In terms of types of systems, you've seen this before. You can have either consistent systems or inconsistent. We saw this with equations. You can certainly have it for inequalities. Just a friendly reminder what this vocabulary means. Consistent means it has solutions. So everything that we've seen before, all prior examples have been consistent. Inconsistent means no solution. It is possible to have a linear system of inequalities that is inconsistent. You have no solutions. As an example here, let's just take x to be greater than 0 and x to be less than 0. What is this region? So if I draw the xy plane, I want everything to the right, and of course I want everything to the left, and the solution set would be where they overlap. Well, guess what? They don't overlap, so there's no solutions. This is an inconsistent system. This could happen, is possible. They tend not to occur too often, or they're not really that interesting for our purposes, but it is an inconsistent system. So anything that has solutions, pick your favorite example that we've done prior. This is the one that these consistent systems are the ones that we're going to study the most. I just want you to be aware that inconsistent systems do exist, just like they did for equality. All right, let's do an application. So Sydney builds portable storage buildings. She uses 10 sheets of plywood and 50 studs in small buildings and 15 sheets of plywood and 45 studs in large buildings. All right, so before we keep going, let's try to keep track of what this word problem is telling us. It looks like we're building small and large buildings. So let's call x the number of small buildings, and we'll let y be the variable for the number of large buildings. Now we have to somehow keep track of how much plywood and studs that she's using. So let's give these sort of a name so we can do this. So we have to keep track of plywoods and studs. So if I use 10 sheets of plywood in each small building, okay, so that's 10 for each small building, 10x, and 15 studs in each small building, so that's 15x. So I got these two numbers. She also uses 15 sheets of plywood for the large building, so that's 15y, and 45 studs in the large building, so that's 45y there. Sydney has available only 60 sheets of plywood, so I can only use 60 sheets. That's less than or equal to 60. I don't have to use all of them, but I certainly can use up to 60, and I have 135 studs. So right away, I'm creating a system of linear inequalities. If Sydney makes a profit of $400 on small buildings and $500 on large buildings, find the combination of large and small storage buildings that she should build if she's to maximize profit. So we have these are called constraints, these are limitations, and what we're after here is our objective, our profit function, which of course depends on how many small and large buildings that we build. For each small building, I make $400, so 400x, and for the larger buildings, I'm at 500y. So notice that the profit is an equation, but the constraint on plywood and studs is an inequality. Let's play around with the system of inequalities first. You can use Desmos, or you can use a calculator to graph these things. One of the other constraints that are here but are not really here is keep in mind I can't make a negative number of storage buildings, so x is certainly greater than or equal to 0, and y is greater than or equal to 0. These two constraints put us in quadrant 1, so if I were to graph this, I'm only going to draw quadrant 1 on the xy plane. When you graph these two lines, you can certainly reduce the numbers to make things a little smaller. 10, 15, and 60 are all divisible by 5, so you can certainly turn this into 2x plus 3y less than or equal to 12. As a sketch, we'll do our best to draw that line. That's a line with negative slope. And if I were to reduce the other numbers, 15, 45, and 135, everything's divisible by 15. That turns into x plus 3y is less than or equal to 9. Let me use another color for that line. And if you sketch it by hand, you get a line that just hits the y-axis at a little lower point, at 3. So x plus 3y equal to 9 would be my blue line here in the picture. And the region that I get, you can test your test points here, is going to look like this polygon with borders the x and y axis, and then its first border is the line x plus 3y is 9, and then this other border, the line 2x plus 3y is less than or equal to 12. Okay, so this is my feasible region. I'm drawing this by hand a little quickly, but pause the video and check. The point that they intersect, if you were to set the two lines equal to each other, is 3, 2. You can solve for that. Now, how do I know where, out of all these points, what to pick as to be the answer where the profit must be the maximum, where I can get the maximal profit? Or what if I said to you, you can make $1 million? What if I said to you, you can make $1,000? If you start graphing, just say, I want to make $1,000. What if I said, for example, I want to make $2,500 in total? If you were to graph that line, 400x plus 500y, you would start to get a line. I'm not going to do this on my picture, but you would start to get a line that is out here. And if you realize, I want you to do this, graph this line, just say $2,500. Just imagine you can make that money. You would get a line that doesn't go through the parallel, doesn't go through the feasible region. If you were to make $3,000, you get something else. What you're doing, though, is you're not changing the slope. In fact, what you're doing is you're moving that profit line closer and closer and closer to your feasible region. And the first time that that line is going to hit a point that is allowable, that's inside of the region that I want, is right here at the corner of 3, 2. And this is true in general when you have these problems that you try to min-or-maximize. They usually happen right at a boundary point because the boundary points sort of stick out. And if you're thinking about moving this line closer and closer and closer, moving this is like a slider. So imagine this to be a slider. The point that will hit the slider first will be at 3, 2. So look for this boundary point, look for this point of intersection. So x equals 3, and y is going to equal 2 will be the point where you can maximize this profit. And when you plug in at 3 comma 2, you get 3 times 400 plus 2 times 500. That's 1200 plus 1000, which is 2200. So our maximal profit is going to be $2,200. These kind of problems are called linear programming problems, and we'll see more of these in later applications. All right, good job on this tough example. Make sure you can go through it and understand where the numbers come from. Make sure you're also able to graph these regions that we care about, the solution sets to these systems of linear inequalities, either by hand or, if you need to get fancy, using some sort of technology. Great job on this example. We'll see you next time. Hi everyone, welcome to our lecture on functions. So first of all, let's define what these things actually are. So we will say that a function is a rule that assigns each element in a set to a unique element in another set. So these are just rules. Our sets that we're going to work with are usually sets or subsets of the real numbers, so we can think about it as a rule or a machine sometimes where you give me a number and I will manipulate it, I will change it, I will do something to it. A very simple example of a function, we've seen the formula for the area of a circle, a equals pi r squared. You give me a radius, 1, I'll give you back the area. So if the radius is 1, I square it, multiply it by pi. 1 squared, of course, is 1, times pi is pi, so the area is, you can give me 2, and I'll square it to get 4, times it by pi, and I'll get 4 pi. So you can compute this function, you can evaluate this function by plugging in different numbers of r. Oftentimes there's a picture, you could think of numbers going in to the machine, so here's your function calculator, and then it spits out the answer. So as I plug in a number for r, let's say r is 2, the function, this machine, takes 2 and it does the arithmetic, it does all the manipulations that you want. Of course here the area is pi r squared, so I'll square, get 4, times it by pi, and I output, the machine outputs the number 4 pi. So this rule, this machine, is what we're after when we talk about functions. Now, if we start with 2 related variables, we can identify one as the first variable and the other as the second variable. And then we can consider these pairs containing their corresponding value. And if the set of ordered pairs satisfies the function definition, then we can say that the second variable is a function of the first. So in this example, we can say that r is a function of a. I don't have to use r, I don't have to use a. Oftentimes you'll see f, x, y, or even Greek letters. So just be comfortable with any variables that you see. So the variable that's used in the formula is called your independent variable. So in this case here, r is the independent variable. And the variable corresponding to the name of the function is our dependent variable. So a would be our dependent variable. As another example of a function, let's keep using geometric examples. If I have a square with side s, then the area of that square, so the area of a square, of course, is side squared. So in this example, the formula for area depends on the side. So our dependent variable becomes the a, and our independent variable, the one that's used in the formula, is our s for side. Now we can write formulas down all day, but often we want to visualize these formulas via their graphs, and we want to know what the graphs look like. What are the geometric shapes that we're playing with, that we are manipulating when we work with these functions? So when we're given a graph, we can check to see if that graph satisfies the definition of a function. We have to make sure that the uniqueness part of the definition is satisfied, which means that if I give you an x value, there's only one y value that corresponds to it. This criteria is known as the vertical line test, often abbreviated as VLT. It says the following: a graph is the graph of a function if and only if there is no vertical line, no up-down line, that crosses the graph more than once. A couple things about this notation. If you haven't seen this before, this IFF is if and only if. This is an abbreviation. Please don't tell me I spelled if wrong. If and only if means that if one part of the sentence is true, the other side is true as well. So if and only if, IFF for abbreviation. To use the vertical line test, you'll often be given a graph. So for example, if I give you a circle, or I give you the parabola, or I give you something a little more fancy, maybe this one, what you do is you look at the graph and you ask yourself, can I draw a vertical line in such a way that I cross more than once? Twice is fine, or just more, but vertical. It has to be straight up and down. As you notice, if I draw the vertical line all the way to the left, then sure, I don't actually cross the graph. So of course you want to draw it on the graph, and when you do this, you cross the graph more than once. So this is not the graph of a function by the VLT. If I have the parabola and you start drawing vertical lines, you'll quickly realize that you only cross the graph once, no matter what vertical line you draw. So this is, yes, this is the graph of a function. Pause the video for a second and try the third one. Is this graph that's given, again, I don't have a formula for it, just look at the graph. Is this graph given the graph of a function? Use the vertical line test. When you do this, if you start drawing vertical lines, you'll see that the graph only crosses the axis once. So once again, yes, this passes our test, this passes the vertical line test. This is, in fact, the graph of a function. When we have our function, again, think of it as a machine. I input some variable in, I do some manipulation to that variable, and the machine outputs a new number, or a new expression. Number in, number out, expression in, expression out, whatever it's doing. With any machine, you have to be careful what you feed the machine. So now, with this function, with this idea of a function as a machine, we're going to define the domain. The domain will be the set of numbers, often a subset of the reals, that are allowed to be used in the function. So the set of numbers that are allowed. And you say, well, wait a minute, what do you mean allowed? Like I can't use the number 7? Maybe. It depends. So for example, if I talk about a radius of a circle, so if I say a equals pi r squared, it doesn't make sense to talk about a circle of negative radius. Right? That just doesn't make sense when we think about a circle and what radius represents. It's a distance from the center. You might even want to say having a circle of radius 0 is kind of silly, just be a single point, but maybe you want to argue that or not. So our domain in this example, let's just make it positive. We'd say the domain is all real numbers that are positive. I don't want 0, it's kind of the world's worst circle, and I don't want negative, that doesn't even make sense for a radius. So my domain would be r greater than 0. This is the subset of the real numbers that are allowed in my function. Let's do another example. What if I said y is 1 over x? So take the reciprocal of a number. So if you give me 7, I return 1/7. If you give me 9, I return 1/9. What's my domain? What numbers am I allowed to take the reciprocal? Well, 1 over a number is like division. So now I'm allowed to take the reciprocal of every number, or divide by every number, except x equals 0. So my domain, I got to throw that one away. I'm going to say x is not equal to 0. Let's do one more. What if I said y equals x squared? Am I allowed to square any numbers? Are there any numbers that you're not allowed to square? Think about this for a minute. I could take a negative number and square it. That's fine. 0 squared is just 0. A positive number squared is positive. So in this case, the domain here would be all real numbers. When we can write that using our set notation, this is the capital R. This means all real numbers from minus infinity to infinity. But some functions you're allowed to throw everything in, and some functions you got to be careful about what you throw in to the domain. The domain captures what is allowed. The range of numbers is then your set of outputs of the function. If I give you a graph and you're looking at a graph, this would be the set of y values. Just as a quick example, let's look at our last example here, y equals x squared. This is the graph of the parabola. I'm allowed to square anything I want, so of course the domain here is all reals. But if you take a negative number and square it, you get back a positive number. If you take 0 and square it, you get back 0. If you take a positive number and square it, you get back a positive number. The y values that you get here, the range, is all y greater than or equal to 0. You will never get a negative number if you square a real number. So now we're going to start talking about function notation. If we call the function, usually we use f for function. F is our machine, so we have a bunch of numbers in our domain. We feed those numbers into my machine, and the machine outputs values in the range. We usually write this using parentheses. Now this gets a little confusing sometimes. So for example, let's just say 2's going in and 5's going out. This function, whatever it does, turns a 2 into a 5. Maybe it adds 3 to every number, who knows. When I write that, the function itself, we use f and then parentheses, and we'll use x here. We would read this as saying f of 2 would be 5 when I evaluate or plug in for x and say this function takes in 2 and outputs 5. Let's make it official and say that this function takes a number and adds 3. Another example, if I take in, what happens if I feed 3 to this function? If 3's going to the machine and the machine adds 3, then all of a sudden f of 3 becomes 6. So we would read this as saying f of 3 is 6. The confusion that a lot of students have is they see parentheses and they think I'm multiplying or something here. But this is important. You're not multiplying. Think of the parentheses as sort of the mouth of the machine. You're feeding the function in. This is not multiplication. What's interesting as well, and where we're going, is eventually we're not going to throw in numbers all the time. I can certainly throw in anything I want. These functions are kind of dumb. They just do whatever you tell it. It says I'll add 3. So if I throw in smiley face into my function, this will say, okay, this is smiley face plus 3. it doesn't really think too hard about what it's allowed to do, and eventually where we're going, of course, is not throwing in smiley faces, but we're going to throw in expressions, like what happens if I take a minus 1 and throw that into the function? Well, this will say, okay, no problem, I'll take a minus 1 and I'll just add 3, which we can simplify to get, of course, a plus 2. So what's going to happen is we're going to start to throw in not just numbers, but expressions into these functions. So look for this letters of the functions and parentheses and just realize it is not multiplication. So our goal in this video is really to study linear functions, and so linear functions are defined to be very special kind of functions. They're of the form f of x equals ax plus b, where a and b are some real numbers, there's some constants, and this is called a linear function. The reason why it's called a linear function is because if I write the equation y equals ax plus b, then of course I get a line. So the graphs of these things are lines. The slope of the line is given by the first variable, often called m, but we use a here, and the intercept of the line is given by b. So linear functions have graphs that are straight line, and any non-vertical straight line is the graph of a linear function. So we've seen these before, so our practice now is just to get used to this using function notation. So let's do an example. Find the slope of the line 2x minus 3y is 3. So remember, the slope is the coefficient against the x when I write this function in its standard form, in the form ax plus b. The problem is, as I write 2x minus 3y is 3, I am not in that form. I have to solve for y. So let's do that now. So let's move the 2x to the other side. I get negative 3y is minus 2x plus 3. Let's divide everything by negative 3. I get y is positive 2/3 x, and then minus 1. The slope, in this particular example, the coefficient on the x would be positive 2/3. Often the most important property, even more so than the y-intercept, is the slope of the line. If I wanted the x-intercept, if I want to know where this graph crosses the x-axis, you set the y value equal to 0. When I set the y value equal to 0, I get 0 equals 2/3 x minus 1, and then of course I solve for x. Let's add 1 to both sides. You get 2/3 x equals 1, and so of course x is 3/2. So the point, the intercept, is 3/2, 0. If you get asked for the y-intercept, well then of course we're going to set x equal to 0. Appreciate that for a minute. When x equals 0 is the point where the graph crosses the y-axis. When I set x equal to 0, I get y equals 2/3 times 0 minus 1. The point that is the y-intercept is then 0, minus 1. Oftentimes you'll be given a graph of a line, and you know that there are 2 points that go through it. So you have x1 and y1, some specific point with the numbers given. You have another point, x2, y2. And they ask you to find the equation of the line that passes through these two given points. Often that means you're going to want to calculate slope so you can find slope and put it into your equation. So the slope is defined, this is usually denoted as m. Our slope is defined as the change of y over the change of x. Sometimes people call this rise over run. The formula for this is the difference between the y values, y2 minus y1, and the difference between the corresponding x value. It's important that whatever point you use first, you line them up accordingly. As a quick example, let's find the slope of the line that passes through 2, 3 and negative 4, 0. So what's the slope? Remember, the slope is the change of y over the change of x. So I take my y values, 3 minus 0 over 2 minus 4. Watch that double negative. You get 3 over 2 plus 4, which is 3/6, better known as 1/2. Now sometimes students get confused. They say, well, wait a minute, what if I pick a different point? What if I start with the other point or write this backwards? Does it matter which number I call x1 or x2? Let's do it again, but switch the values. So in this example over here, I called the first point y1, but now let's switch it. What if I started and called the 0 y1? So I would do 0 minus 3, but now I have to do the corresponding x value. So I have minus 4 minus 2. What if I had chosen this one? Do I get a different answer? Let's see. So 0 minus 3 is negative 3, minus 4 minus 2 is negative 6. And it turns out, after you simplify and cancel the negatives, you get 1/2 again. So of course, it doesn't matter which order as long as you are consistent. The equation of a line through the points is the same whether you start with the first point or the second point. Just to bring this all the way through to completion, if I wanted the equation of a line, I already have m. I already have m here. So why don't we write it as y equals mx plus b. I'm going to replace my m with my 1/2 that I just found. And so now the question is, well, how do I get b? So let's pick any point we want. How about we pick 2 and 3, and I'll plug those in for x and y. So when y is 3, I get 1/2 x, which is going to be 2, so times 2, plus b. And I get 3 is 1 plus b, so of course b has to equal 2. So you can use any point you want to plug in for x and y, and you get an equation of only b. So my final equation for this line is y equals 1/2 x plus 2. The final check, you can certainly plug in the other point that you didn't use and say, well, what happens if I plug in x as -4? You're going to get -4 divided by 2, which is -2, and then add 2, you get 0. So this other point does satisfy the equation of this line, this nice linear function. So we have different ways to present the equation of a line. A line with slope m, and through a given point, x1, y1, has the point slope equation, y minus y1 is m, x minus x1. So it's named after the things that you have. If I have a point and I have a slope, I'm going to use the point slope equation, and this will give me the equation of a line. You can always rearrange this equation and put it into different forms. You can put it into the form y equals mx plus b, but it's usually common to get a point and a slope and write it in this form. Just a couple things that we should keep in mind. If I have parallel lines, then I have the same slope. Whatever the two lines are, they'll have the same slope. In your head, imagine two parallel lines. Their rate of change is exactly the same. They have two slopes. If you have perpendicular lines, these are lines that meet at a right angle. So let's draw two different perpendicular lines here. Then the slope of one turns out to be the negative reciprocal of the slope of the other. Just some things to keep in mind. If your graph goes up, if your line has a nice increasing quality to it, your slope's going to be positive. If your line is coming down, you're going down the hill, your slope's going to be negative. And if your line is nice and flat and boring, then we say that m is 0. We'll have 0 slope, so a vertical line has no slope. This point slope equation, compared to the last one, is different than the y equals mx plus b that we saw, but you can certainly change formulas and rearrange and put it into that form. That formula that we saw, the y equals mx plus b, its official name is the slope-intercept equation of a line. So this is the formula that you know and love, y equals mx plus b. And again, why? Because I'm given the slope, I can see it, I can use it, and now instead of another point, I'm actually given the specific point that is the intercept. So again, these names of these formulas, they come from the fact that you can see, you have all the pieces that build it. In this point slope equation of a line, I have the slope m, I have the intercept of the line b, and so the linear function that's described by this equation would just be, if I write it in function notation, f of x equals mx plus b. Just as a specific case, if the slope m is 0, then my function simplifies a little bit, and I get f of x equals b, just b the constant. This is a horizontal line with slope equals 0 going right through point 0, b. This constant linear function is a very special case that I don't want to throw out, but I don't want to forget about it either. It's a very simple form. So f of x equals 7 or pi or whatever constant you want. These are nice horizontal lines, very special kind of linear function. Let's do one example and then let you go off and try some on your own. So let's find a line that passes through the point 3, 1 and we'll say is perpendicular to the line y equals 2x minus 1. All right, here we go. So I want the equation of a line that passes through 3, 1 and is perpendicular to the line y equals 2x minus 1. So first, what can I grab from this? If I'm perpendicular to a certain line, then I know the slope of this line is going to be 2. But the slope that I want, then, is the negative reciprocal. So I negate and flip, two-step process. The slope that I want is negative 1/2. And I also know that I go through the point 3, 1. So I have a point and I have a slope. Well, now it makes sense to use the point slope formula. This is y minus y1 is m x minus x1. Let's plug in all the things I have. So I have y minus 1 is equal to the slope x minus, let's clean this up a little bit and put it in a different form. So we have y minus 1 is negative 1/2 x plus 3 over 2. Distribute the 1/2 to both pieces. Then let's add the 1 to both sides. I get negative 1/2 x plus 5 over 2. So this is our good old slope-intercept form. Y equals negative 1/2 x plus 5. If they had asked me for parallel, I would have used just good old 2 because parallel lines have the same slope. And I can put this, of course, in any form that they ask. So be ready to work with these variables, x or y, f of x, or different letters, Greek letters, why not? Pick your favorite scary variables and be ready to work with any sort of equations of lines. And of course, always graph these things. Just realize when you're pushing these symbols around a page and really manipulating lines in the xy plane. All right, great job on this video. In the next video, we'll study quadratic functions. We'll start to add more pieces and more complexity to these linear functions. I'll see you there. All right, hi everyone, welcome to our lesson on quadratic functions. So we're going to define a function, we'll call it f, of x to be a quadratic function if it is of the form ax squared plus bx plus c, where a, b, and c are just real constants. So notice I'm taking our prior linear function and adding on an extra term. So this extra term, ax squared, is the difference between a quadratic function and a linear function. The graph of a quadratic function will be known as the parabola. As a very simple example, the one I think we're all familiar with, if I take f of x and I set a to be 1 and let b and c be 0, I get good old f of x equals x squared. And its graph, this U-shaped graph, its official name is the parabola, looks something like this. It goes right through the origin and sort of opens upward. And this graph is known as the parabola. And notice in this example, we had a is 1, b equals c equals 0. Just to keep talking more about the parabola, the graph of the function f of x equals x squared, as x increases, the graph is moving down. We would say that the function f of x decreases in that case. Then we hit 0. This vertex, the spot here is called the vertex, the lowest point of the graph. And then as x keeps going up, when x is positive, the parabola makes a turn and starts to go up. I draw this as I move from left to right, and we would say here that f of x increases. So the parabola is known by having a decreasing or increasing portion. Of course, you can flip the parabola upside down and all of this reverses as well. This parabola never ends. It goes on forever and ever. So there's really arrows that are going on here. So we would say that the end behavior of the function, where the function wants to go, so as x gets, let's say, really large, off to positive infinity, the largest numbers, then the function f of x equals x squared goes to infinity as well. That's saying that the graph will go up and up forever and ever and ever. And on the other end, if I start plugging in negative numbers, as x goes to negative infinity, so think about plugging in negative a million, negative a billion, negative a trillion, where does the function want to go? Well, this function, because I'm squaring a negative, I still get back a positive number, wants to go to infinity as well. So to describe the behavior, the end behavior of these graphs, we'll use these arrow notations. Now, oftentimes we want a little more complicated function than just good old f of x equals x squared. So we're going to shift the graph. If you haven't seen these before, the shifts we're going to do horizontally, these are left-right shifts. So you always start with a real number c, take a positive number, and if I take the graph y equals f of x minus c, so take x and subtract off some number, x minus 1, x minus 2, then this will be the graph. This is shifted right c units. And this is a little counterintuitive because you're subtracting off, so you might think you're going to the left, but it's actually opposite of what you expect. You're shifting right. In a similar fashion, if I take the function f of x plus c, then I'm going to shift the graph that I started with. I shift it left c units. As an example, let's take the function f of x to be parentheses x minus 2 squared. So notice this is x minus 2. So I'm taking the original parabola that I had, good old f of x equals x squared, and now I'm shifting it, but let's see if we can figure out which way we're shifting. We're subtracting 2. It's a little counterintuitive. We're moving it to the right. So 1, 2. You can also see this if you plug in 2, then you get a 0. You get the 0, the intercept at 2. So if you plug in 2, you get the vertex moves over to 2. and you had the parabola sort of shifted to the right 2 units. Nothing else about the parabola changes, it just shifts to the right. You could do the same thing with x plus 2, and of course it'll shift to the left. We're going to use these shifts to help graph or draw sketches of graphs of more complicated quadratic functions. Now often when we start with quadratic functions, we're looking at functions of the form f of x equals ax squared plus bx plus c. Now we're going to do a little bit of an algebraic trick to rewrite this, and this is a trick called completing the square. If you haven't seen this before, it gets a little messy at first, but then it kind of cleans up. So the first thing we do is we factor out the a, and we get x squared plus b over ax plus c over a. Convince yourself that that's okay, just distribute the a back in, and then what we're going to do is we're going to work inside this parentheses. We're going to write the x squared, we're going to write ba over x, and now we're going to do something that's perhaps surprising, and this is the move that is not obvious. We're going to add b over 2a quantity squared, that's some number, but I'm also going to subtract it. So in effect I'm adding 0, and hopefully you agree that if I add 0, I don't actually change the number. You'll see why I do this in a second. This is not an obvious move. This move is called completing the square. When you do that, when you add this extra term, and of course subtract it, just remember that you're writing 0 in a fancy form, you look at the first 3 terms. You look at your first 3 terms, including this new term. And that lets you write this as a x squared plus b over ax plus b over 2a squared. And then I'm going to distribute the a to the second portion. So I'm going to bring that a in, minus a, parentheses, b over 2a quantity squared, and then of course plus c over a. That's just good old plus c, and then plus c. The term inside those first set of parentheses, this is a perfect square. What does that mean? It means that I can write this as a, and then x plus b over 2a quantity squared. Now that's not obvious enough, so if you want to see that, FOIL this out. Just convince yourself that if you FOIL this out, you do get back x squared plus b over ax plus b over 2a squared. I'm going to switch the order on the other side to get c minus b squared over 4a. And last but not least, I'm going to write x plus b over 2a quantity squared. I'm going to write this as a single fraction. I'm going to combine, find it using a common denominator. So we get 4ac minus b squared over 4a. Now this is a lot of work to get this in this form, but this form actually tells us a little more information. So the squared term, the x plus ba squared term, is exactly 0 when x equals negative b over 2a. So the vertex of the parabola in this standard form, ax squared plus bx plus c, occurs at this point. This is the absolute minimal of the point. This tells us when the vertex occurs. Now, I wouldn't recommend going through these steps every single time. I would almost sort of commit this to memory, but if you have some parabola off in space, its x-coordinate is negative b over 2a. You can look at the equations. Remember, a, b, and c are all given in the equation. You can find the vertex for it. And in particular, when you have the vertex, the y value would then be the 4ac minus b squared all over 4a. So this is your vertex. Often we're just interested in the x value, so negative b over 2a, and then if we ever want the y value, you can just go ahead and plug it back into the original equation. So this vertex, of course, gives a minimal. We have a nice min here, the minimal value, when the parabola opens upward. The parabola opens upward when the leading coefficient, the a, is positive. If the parabola opens downward, you would get a max. So if in the other case you get a max at your vertex, and this thing spills water, we say, or it opens downward when the leading coefficient is in fact negative. So completing the square on these quadratic functions, it permits the graph to be determined by simply shifting the graph of a basic quadratic function of the form ax squared. So let's do one of these examples and you'll see what I mean. So let's look at the graph f of x equals x squared minus 2x plus 3. Let's complete the square. Let's complete the square by looking at b over 2a quantity squared. This is the term that we added and subtracted last time. In this example here, a is 1, b is negative 2, and c is 3. So when I look at b over 2a, I get minus 2 over 2a quantity squared. 2a is just 1, and this just becomes negative 1 squared, which of course is 1. So we're going to complete the square. We're going to write f of x equals x squared minus 2x. Now I have this 1. I'm going to add 1 and subtract 1. So I'm going to put these two together to get 0, and then I'm going to not forget about the 3 at the end. When you do this, you regroup and you look at the first three terms. Convince yourself that this is a perfect square. This is x minus 1 squared, and then I have minus 1 plus 3, which of course is positive 2. So now you can sketch the graph. We can draw this using this form. So how do we do this? I always start with the graph, good old f of x equals x squared, nice parabola. And then from here, we're going to look at the graph f of x equals x minus 1 squared. This is the graph shifted to the right 1 unit. So the parabola takes a little bit of a walk to the right. And then last but not least, let's shift this up to get f of x equals x minus 1 quantity squared plus 2. So now I'm going to take the point, remember I'm at 1, so I keep my vertex at 1, but I walk it up 2, and I get the vertex shifted right at 2. So the vertex in this particular example is at the point 1, 2. And you can look at that just by changing form by completing the square. Let's do another example. Let's study the quadratic function f of x equals 2x squared plus 12x plus 17. Now this one's a little different from the last one because there's a leading 2 here. So the first thing we have to do is factor this 2 out. And we get x squared plus 6x, and we can leave the 17 as is. We don't have to worry about that. Now we're going to complete the square. Now remember the square is b over 2a quantity squared. In our example here, b is 12. 2 times a is over 4. And I square that whole thing, so we get 12 over 4 squared, which is 3 squared, which of course is 9. So I want to come in here, and I want to work inside the parentheses. And I take 6x and I add 9, and of course I subtract 9 as well, plus the 17. I regroup and I look at the first three terms, and I realize that is just x plus 3, whole thing quantity squared. And I brought the 2 into this term, so I don't want to forget about this other part over here. I really want to write this as negative 18, and then I have the plus 17 floating around. So don't forget about all these other pieces. So you get 2 x plus 3 quantity squared, and then minus 18 plus 17, of course, is minus 1. From this, we have everything we need to sketch the graph of this function. Let's always start with our sort of parent parabola here, good old f of x equals x squared. And now let's start to manipulate this thing. If I want to, let's put the 2 out front. Let's look at f of x equals 2x squared. What does a 2 do to my graph? This makes it a little skinnier. This makes it actually a little skinnier. You can plot a couple points to see that, but it just makes it just a little skinnier. So the sketch is kind of the same. Instead of a fat graph, I have a skinny graph. Now let's do f of x equals 2 parentheses x plus 3 squared. This shifts it to the, now it's plus 3, so it's a little counterintuitive. We had to go left 3. So my skinnier graph gets shifted to the left 3. And then last but not least, we have the parabola, and I could do f of x equals 2 parentheses x plus 3 minus 1. This pulls my graph at minus 3 down 1. Down 1. So I have a nice graph over here. And again, this is something we can do. We don't need to rush to a calculator. This is becoming fluent in the language of quadratic functions. You can think of this as not having to look up every single word in the dictionary when you have a conversation in a certain language. But this is the idea. You can always sketch these things and understand how they are behaving based on completing the square in their standard form. Let's do a different flavor of an example. So I'd like to find the graph. So find the parabola, vertex at 2 minus 1, and contains the point 4, 2. Now, since we know the vertex, I can write this in its vertex form. Remember, it's a, it's going to be x minus the vertex, the x value of the vertex. So x minus 2. Whole thing squared, and then plus the y value, so minus 1. Just a couple things about this, by the way. Notice that I did shift the sign on the 2, that you have to subtract off the 2 value here. So it's like the opposite sign inside the parentheses, but then the y value does not change. So just be mindful of that. So what's missing here? Really, all I need is just a. All I need is a. So this is where the other point's going to come in. So I know that if I plug in 4 into this function, which gives me a 4 minus 2 quantity squared minus 1, I know that has to output 2. I get a, 4 minus 2 squared is 2 squared, which is 4, minus 1 is 2, or 4a equals 3, and well, all of a sudden, I can get a as 3/4. So final equation for this would be f of x equals 3/4 parentheses x minus 2 squared minus 1. Any discussion on quadratic functions, of course, would not be complete without the quadratic formula. So this technique of completing the square is used to derive a formula for finding solutions when I have ax squared plus bx plus c is equal to 0. So what you're doing here is you're finding the x-intercepts. And remember, we do that by setting y equal to 0. If I have some parabola, I'm after the points where the parabola crosses the x-axis. Now, I'm going to leave this as an exercise. We can go through it, and if you want to look it up, I encourage you to do it. Look up the proof of the quadratic formula by completing the square. It's very similar to the last one, but you get x equals negative b plus or minus square root b squared minus 4ac all over 2a. At some point in your math career, you might want to memorize this. There's YouTube videos out there where they sing songs to Pop Goes the Weasel, so you can sing a song to do it. But the idea of this is that you have a formula to give you the x-intercepts, which can even give you more information about your parabola, and you can get very accurate. Often there's a square root involved, so if you need decimals, you're going to need a calculator. This term under the square root, and it has a name. This term, this b squared minus 4ac, is called the discriminant. And it tells you the number of solutions you may have. So for example, if it's positive, so if b squared minus 4ac is positive, then you're going to get two x values in the picture that you have here. So you have two distinct real solutions, two x-intercepts. And the picture is the one that I drew, something like this. If the b squared minus 4ac, if the discriminant is equal to 0, then under the square root of 0 is just 0. And then you have the numerator, you're plus or minus 0. So you only get a single value of x. You get x equals negative b over 2a, and in particular, this is just one x-intercept. You say, wait a minute, how do you have one x-intercept if you have parabola? That just means the parabola touches right at the vertex touches the x-axis at a single point. This is like y equals x squared. And if, the final last case, if b squared minus 4ac is in fact negative, then you have a non-real solution for x. You have no x-intercepts. Parabola that would never touch the x-axis would be something either above or below it out in space. So all three of these are very possible. Let's just do an example with a more complicated quadratic function. How about x squared plus 2x minus 1? Let's study this parabola. Tell me everything we can. So as always, our first step is going to be to complete the square. Go off on the side and look at b over 2a squared. When you do that, then you get 2 over 2 times 1 quantity squared. That's just 1. So I'm going to rewrite this as x squared plus 2x plus 1 minus 1 minus 1. I'm going to look at the first three terms together. I'm going to complete the square to get x plus 1 quantity squared. Combine the two negative ones to get minus 2. When you do that, I immediately can tell you the vertex. Now I know that the vertex occurs at minus 1 comma minus 2. Notice I'm changing the sign on the number that's inside the parentheses. Now, to find, let's say we want to find the y-intercept, remember you just set x equal to 0. This is the easier piece to do. And when you set x equal to 0, you get y equals 0 plus 1 squared minus 2, which is 1 minus 2, which is minus 1. So my y-intercept occurs at 0 comma minus 1. If I want to find the x-intercept, all right, now this is the harder one to do here, we're going to use the quadratic formula. So let's write it out. So x equals negative b plus or minus square root b squared minus 4ac all over 2a. Let's plug in our numbers. We get minus 2 plus or minus the square root b squared, 2 squared is 4, minus 4 times a times c, so 4 times 1 times minus 1, all over 2a. This is minus 2 plus or minus 4. Now two negatives make a positive here, so it's like 4 plus 4. So it's root 8. Not a super pretty square root, but we'll still work with it, all over 2. Now you can write root 8, I don't know if you've seen this before, but you can write root 8 as square root of 2 times square root of 4, and the square root breaks up over multiplication. Square root of 2 is some number, not super pretty, but square root of 4 is just 2. So this becomes 2 root 2. So I'm going to write this as negative 2 plus or minus 2 square root of 2 over 2. You can factor out a 2. You get minus 1 plus or minus root 2, and the 2's will cancel. So your x-intercepts occur at negative 1 plus or minus root 2. Notice since my discriminant was 8, I knew I was going to get two distinct values. Now if you want to grab the calculator and approximate these, you can plug this and you get 0.4 and negative 2.4 if you want just some decimal approximation. That's enough. I think we've said everything we can about this parabola. This allows us to graph this thing pretty accurately. So remember, its vertex is at -1, -2. So I'll put the vertex down here. The A value, the A is 1, is positive, so this thing's opening upward. So I know that it's going to open upward, so I can draw something like this. Well, not the world's most prettiest parabola, but it's going to open upward. And I know the exact values of where the x-intercepts occur. I know the y-intercept occurs right at 0, -1, and the x-intercepts occur at positive 0.4, 0, and back here at negative 2.4, 0. So even though my parabola is not the world's most prettiest parabola, I can certainly tell you with great accuracy the important points of this parabola on the graph. All right, so great job with this example. Go over these again, try some of the practice problems, memorize your quadratic formula, and really great job working with these more difficult functions. I'll see you next time. Hi everyone, and welcome to our lecture on common functions. So we're just going to list in this lecture some basic functions that you've probably seen before, but we're going to describe them in full detail. We're going to give their graphs. I'm just going to sketch their graphs on the lecture, but I encourage you to go over to one of the websites that we talked about and see the graphs in perhaps a better detail, more drawn to scale. The first kind of functions that we talk about are linear functions. These are the pretty common ones that I think most of us have seen. These are the form f of x equals mx plus b. We're going to have a lot more to say about this later. You might have known that m is the slope and b is the intercept, but this is the general form of a linear function. They're called linear function because their graphs are, perhaps not surprisingly, lines. The two that I want you to know for this one here is the very basic one when m is 1 and b is 0. So this is f of x equals x. This is a graph. This is a function whose graph you should know when you see the function. If you think about what this is the identity function. So you plug in 0, you get 0. You plug in 1, you get 1. -1, you get -1. It's a nice diagonal line that goes right through the origin. So this is great. Let's say, though, a little more than just the graph itself in terms of what we can describe. What are some attributes of this graph? The domain of the graph. So the domain, remember, is a set of all inputs. What numbers am I allowed to input into this function? What this function says, give me a number, I'll return it back. There's no problem with that at all. So its domain is all reals, and its range, which we'll denote with a D and an R, its range is, you give me a number, I give it back. It's exactly the same as the domain. I'm writing reals with this double bar R. That's a common way to write all real numbers. Some folks like to write it using interval notation. That's perfectly fine as well. You can write -infinity to +infinity, and then this is important, make sure you put the parentheses on the infinity signs. Either way you like to write it, with the R, with the double bar, or the -infinity to infinity is perfectly fine. So this function, f of x equals x, has a graph of a line. Its domain is all reals. Its range is all reals as well. Other things you might want to know if you have a graph that you can talk about, like what are its x-intercepts, what are its y-intercepts. So I'll abbreviate that with x-int and then y-int as well. Friendly reminder, the x-intercept is where the graph crosses the x-axis. For this particular graph, it goes right through the origin. So we'll list the origin down here in 0, 0. The y-intercept is where it crosses the y-axis. It's this easy function here. It turns out to be exactly the same. Other things you might want to ask yourself are sort of what are the end behavior? What does this function want to do as x gets large? That's going to be a nice defining property of functions here. So as x gets large, again, the function is just returning what the value input is. So we say as x goes to infinity, as x gets large, the function gets large as well. So as x goes to infinity, the function goes to infinity, and same thing, as x gets very small, the function gets very small as well. So we can write it out as a separate sentence if I can fit it here on the slide. So as x goes to -infinity, f of x goes to -infinity. So this is a nice little summary of the property of this function. It is related to one other function, so let's do f of x equals -x. These are the only two linear functions that I want you to know everything about. F of x equals -x. So what did I do? I changed the coefficient on the x. I changed the value of m. This is now a negatively sloped line. Slope has -1. So for example, if I give you x is 1, you return -1. If I give you x is -1, you negate that and you return +1. So same thing goes right through the origin, nice diagonal line, only this one is going from high to low as you move from negative to positive. It has very similar features. Its domain, again, all reals, and its range, since you're just negating every single number, is all reals as well. Its x-intercept and its y-intercept, once again, are both the origin. Where does this graph cross the x-axis? Where does this graph cross the y-axis? And now, so far everything looks the same, right? But what's different about this one? The end behavior. So as x gets large, then the function, where's the function want to go? Down into the abyss. The function goes to -infinity. And as x gets small, so what's the end behavior now? As I get negative, the function actually gets quite large. It blows up and goes to +infinity. Okay, so infinity, +infinity, they're the same thing. I just want to stress that as x gets small, this gets large. So there are many, many, many linear functions, but these are two that I want you to know everything about. The next kind of common function you'll see are what's called quadratics. The general quadratic is a polynomial of the form ax squared plus bx plus c. You may know this from having to memorize at some point the quadratic formula, which solves for roots of this type of equation. Again, there are lots of variables, lots of numbers here you can pick for a, b, and c. So there are infinitely many kinds of these, but I just want you to know the basic one for the most part. This is f of x equals x squared. This is the parabola. This comes up often enough that we should just kind of know everything about it. So let's collect all the facts right here, right now. And you can keep these handy and use it as a reference sheet. So we've drawn this before. Y equals x squared is the parabola. It goes right through the origin, has a nice sort of U shape to it. So let's list some things about it. What is its domain? What numbers am I allowed to square? Can I square positives? Sure. 2 squared is 4, 3 squared is 9, etc. Can I square 0? Sure. 0 squared is 0. Can I square negative numbers? Sure. -3 times -3 is +9. So you can square anything you want. Its domain is all reals. Its range. Now this is interesting. What is going on with the range here? The range is a set of outputs. It's a set of y values. If you think about on the y-axis, what are the numbers you get? The range here, can I ever get a negative number if I square something? Think about this for a minute. Can you ever get a negative number? The answer is no. If you restrict to the real numbers, which is what we're going to do for our domain, I can certainly get 0, right? I cross the origin there, so 0 squared is 0. So 0 is an output of mine, and I get any large number I want. I can definitely get positive as I square things. So this is important now. I can get 0. When I can get the number, when the number is included in my set, I put a bracket. I don't use open parentheses. When I can't get the number, like infinity is not really a number, it's a concept, like you never quite get there, use open parentheses. So be very careful here with your brackets and your parentheses. Bracket means include. Parentheses means like don't include the number or you can't get to the number. Infinity always gets a parentheses because you can never quite get there. All right, so what else do we want to know? Let's talk about intercepts. What is the x-intercept and what is the y-intercept? Once again, this graph, nice little parabola, goes right through the origin. So it has one point where it crosses the x-axis, which is exactly the same point where it crosses the y-axis. Not every graph will have this. Not every quadratic will have this. But this parabola does. What's the end behavior? As x goes to infinity, as x gets large, where's the function want to go? So the function f of x goes to infinity. And as x gets small, as x gets really small, where's the function want to go? So if you're a little bug and you're walking left on this thing, on the parabola, where do you go? Off to infinity as well. So different range, same intercept, same domain, and different end behavior to help sort of distinguish what it means to be the quadratic. Again, lots and lots of quadratics out there, but this is the one I kind of want you to know. This will be the foundation for most of the other ones that follow. Okay, next up is a cubic. So a cubic. So f of x is ax cubed plus bx squared plus cx plus d. A cubic is a way to say a degree 3 polynomial. A degree 3 polynomial. Friendly reminder, the degree of a polynomial is the highest exponent that appears. So when the highest exponent was a 1, we had a linear polynomial. When the highest exponent was 2, we had a quadratic polynomial. And now the highest exponent is 3, we have a cubic polynomial. Once again, I just want you to know the simplest kind of quadratic, cubic that there is, and this is x cubed. So when the coefficient's 1 and the rest are to 0, just good old x cubed. This function, I like to call it the disco function. Why? Move your hand in this motion as I draw it. Stand up, put on your 70s outfit, you'll see why. Okay, goes sort of low to high, and like the other graphs that we've seen so far, crosses the origin right at 0. So think about this. So this is like you give me a number and I will cube it. So 0 cubed, 0 times 0 times 0, that's 0. 1 cubed, 1 times 1 times 1, that's 1. 2, 2 times 2 times 2 is 8, etc. You can throw in positives, you can throw in zeros, you can throw in negative. So your domain on this guy is all reals. Your range, now this is interesting. If I take a positive number and cube it, I get back a positive number. If I take 0 and cube it, I get back 0. And if I take a negative number, 3 negatives make a negative, so you actually get all real numbers back for your range. That's kind of nice. So my set of inputs is all reals, and my set of outputs is all reals as well. What is the x and y intercept? A little theme going on here for these sort of introductory functions. It's the origin once again, so it goes right through 0, 0. And what's the end behavior? So as x gets large, the function, so if you're a little bug, you're walking on the graph, where are you heading up? You heading up? You heading down? Going somewhere else? We're going to infinity. And as x goes to negative infinity, as x gets really small, 3 negatives make a negative, I also head to negative infinity. So this is another graph that I want you to know. I want you to have sort of a picture when someone's talking about a cubic behavior. This is the graphs that should come in your mind. And again, these properties and facts about it as well. Let's look at another common function. This is a little unlike some of the other ones, a new one, square root here. So let's just write this guy out. This is f of x equals the square root of x. And in this class, it's going to make more sense for us to do a little algebraic switch. Friendly reminder, the square root of x is the same as x to the 1/2. So you'll see it either way. And if I draw the graph, the sketch of this graph, taking a square root of a number gives you back a positive number. The square root of 0 is 0. Some people get confused with that, like, am I allowed to do that? Yes, you're allowed to do that. Can't really see that color, so let's mix that up a little bit. So if I take 0, I get back 0. And then like square root of 1 is 1. The square root of 4 is 2. And this graph just kind of goes and rolls and off it goes. It grows slowly up like a slow steeping mountain. Okay, so this is the graph y equals the square root of x. Okay, let's give this thing some basic properties. It's a little more rounded than I drew it, but this is the idea. What is its domain? What are you allowed to plug into the square root function so that we get an answer back? We can only plug in this class 0 or positive. Plug in 0 is fine. Plug in positive is fine. You can't plug in negative numbers. Our universe that this class studies is real numbers. If you know a little bit about complex numbers or imaginary numbers, yes, they're a thing. Yes, they happen when you throw negatives under a square root. But we're not going to talk about them in this class, at least for a little while. When we talk about functions, the underlying assumption is that everything is a real number, so our domain is only going to be 0 to infinity. So this is our first graph where we have a restricted domain. This is not the entire real number. Can't throw a negative under a square root. Its range is also, remember I get back a positive number if I take a square root, and I also do get back 0 if I plug in 0, the same 0 to positive infinity. Brackets on the 0, parentheses on positive infinity. X-intercept and y-intercept, I promise this won't always be the case. We go right through the origin again. For end behavior, as x goes to infinity, if you're a little bug and you're walking on the graph, you're getting there slowly. It's not as fast as the other ones, but you certainly do climb and climb and climb and climb forever and ever and ever. And that means that the function, the square root function, wants to go to infinity. We don't really talk about end behavior as x gets small because it's not in the domain. So I won't even put what happens. The question doesn't make sense if I said to you what happens as x goes to negative infinity of this graph because there is no graph back there. It's not included in the domain. So square root function, a little similar, a little different than the other ones. Know this one as well. Here's another one, 1 over x. This is what's called a rational function. It's like a ratio of terms. So they call these rational functions. This is the parent category that 1 over x falls under. Its graph is kind of neat. It's a reciprocal, or give me a number, I give you back the reciprocal. So if you give me 1, I give you 1 over 1, that's 1. If you give me 2, I give you a half. So as I work my way, as x gets larger and larger and larger, I give you a half, a third, a fourth, and this function gets small. It still says positive, right? Positive 1/2, positive 1/3. Start taking reciprocals of numbers. If you get to 100, like 1 over 100 gets really small. If you start working your way closer to 0, like let's say 1/2, and take its reciprocal, like flip it, you get 2. If you take 1/3 and flip it, you get 3. So as you get closer to the y-axis, the graph actually shoots up. And you have an asymptote over here. And the same thing on the other side. You get this very similar behavior, just everything's negative. If you take the reciprocal of a negative, you also get back a negative. This is a nice, interesting function, and it's the first one we've seen with a little bit of an asymptotic behavior. So the y-axis is certainly an asymptote, as is the x-axis. You can think of the lines like that the function gets close to, but never quite gets there. So this is a new little function. This is a good one to know. It's got some symmetry to it. It's kind of cool. So let's think about what its domain is. So what numbers am I allowed to take a reciprocal of? Can I take positive like 3, 4, 5? Sure. 1/3, 1/4, 1/5. Can I take negatives? Sure. I just can't take 0. So you can't take 0. There's a couple ways to write this depending on how fancy you want to be. The kind of simple way to do it is to say x not equal 0. Like, okay. It's kind of like saying like the negative though. It's like what I can't do versus what I can do. If you want to get a little fancy, there's a couple different ways to do this. If you know your interval notation, you can do like negative infinity to 0, but don't include 0. And then I want 0 to infinity again. And I want like this first interval, negative infinity to 0 or 0 to infinity. And you can union, look at that, now we're getting fancy. You can union the two. This in the union of two intervals is exactly the same as x not equal to 0. Exactly the same. Another way, if you're really, so this is called like interval notation. Another way to do it if you want set notation, now we're getting like super fancy here. You could write all real numbers except, and you could throw 0. It's a set though, so you have to use those curly brackets. This says the same thing. It says basically anything you want except 0. Any one of these three is fine, quite fancy. Pick your poison. So that's the domain. The range, this is also anything, I'll say y not equal to 0. All your outputs are fine, you'll just never get 0. To start with 0, you'd have to have 0 in the denominator and flip it, and you can't divide by 0. So for all the reasons why x is not 0 in the domain is all the reasons why y is not 0 in the range. X-intercepts and y-intercepts. Aha, finally, not the origin. This graph you can see from my sketch does not go through the origin. So what are my x-intercepts and what are my y-intercepts? So to find this, ask yourself, where does the graph go through the x-axis? And you look for a second and say, wait a minute, x-axis is a horizontal asymptote. It never goes through. That's cool. So there's no x-intercepts. Y-intercepts, where does the graph cross the y-axis? It doesn't. So you don't have any, none. So that's new. Finally, not the origin. So we have domain, we have range, we have intercepts. What's our end behavior? So this one, as x goes to infinity, now this is interesting. If you're a little bug, and you're walking, where are you headed towards? The function goes to 0. The function wants to go to 0. Never quite gets there, a little asymptote, but it's going closer and closer and closer. And as x goes to negative infinity, the function also wants to go to 0. This time though from below. So if you're a little bug and you're walking left, you're approaching the 0. You're pushing y equals 0, the x-axis. So here's one also. A lot of things, a lot of new things finally happening here as our functions get a little more complicated. We have no intercepts, and our functions don't want to go to infinity. Finally, as x gets large. Okay. So here's absolute value. So we've seen this before, I think, but let's just write it down. This is where you put bars around the number, and this means give me back the positive version of the number. So for example, if I hand you the absolute value of 5, well, that's just 5. It's already positive. If I hand you 0, well, that's also just 0. The thing is, if it's negative, well, then you just give me back positive 2. Okay, so you just you don't return any negatives. If you start graphing this thing, you'll pick some points and start graphing. So 1 gives you 1, 2 gives you 2. You start getting the line y equals x. At least if you're positive, it's exactly what this means. It says really do nothing, the bars don't contribute anything, and you get y equals x. You go right through the origin. But if you're negative, then I start getting positive values. So negative 1 returns positive 1. Negative 2 returns positive 2. And you get a line, basically negate yourself. To negate a negative gives a positive. And you get the line y equals negative x. So you get this V shape. It's two lines, slope negative 1 and slope 1. And it goes right through the origin. So we're back to that case. It's a nice little function. Has a letter V to it. So the domain, all reals. Range, 0 to infinity. Can certainly get back any of those things. And then x and y intercept. Back to our common case here. Where's the graph cross the x-axis? Where's it cross the y-axis? Right at the origin. As x gets really big, then the function wants to go to infinity. And as x gets really small, then the function also, plug in a large negative number, get back a large positive number, wants to go to infinity. Okay, so these are the big ones that we want you to know. You've probably seen these before, and these are like all the ones that we're going to assume that you have some working knowledge of. These will come up in conversation and use this as a reference. One thing I want to mention, and this is just a super brief intro, we will spend a lot of time in this course on exponential and logarithms, but you hear it all the time. People talk about like models or growth, like this grows exponentially. The exponential function, the most common one, I just want you to know the graphs here. We don't need to go into all the details here, but just the shape of the graph, because it's going to come up, of course. E to the x, now e, of course, is a number. It looks like a letter, but it's like 2.718 and change, so a little less than 3. Exponential growth, when you see something like this, an exponential growth, it starts off low and goes high. Think about like compound interest or something else. But exponential growth, populations tend to exhibit, spread of diseases tend to exhibit exponential growth. So you start off low and you go high. And all these numbers are kind of nasty numbers if you plug them in on the calculator. There's only one nice little point, and that's the y-intercept. And that's if you plug in at 0, so like a number raised to the 0, you're going to get 1. You can go through, we'll talk about the domain and the intercepts and everything else and why it has an asymptote back here later, but I just want you to know the general shape of this graph. Again, go have fun with this thing, go graph it, play around with it, add some sliders if you want, e to the x, and then just as a general shape, I want you to know what the logarithm looks like. So someone's talking about it at this point, you have an idea. The most common logarithm, again, we'll see the other ones, is the natural log of x. And that graph is sort of the exponential graph, but flipped, like turn your head a little bit and flip it over the line y equals x. This is also lots of nasty decimals that you get by plugging into your calculator. However, what you can do is, there's only one really nice point, and it's the x-intercept this time, and that's at 1. So if you plug in 1, so the natural log of 1 will give you 0. This is your x-intercept. Okay, and on the exponential graph, if you plug in e to the 0, you get 1, and that's your y-intercept. Okay, it's just general shape of the graph. I just wanted to do some lots more to say about exponents and logs, but we'll get there eventually. But this is just a good general place to start and introduce these two functions. All right, great job on this one. See you next time. In this lecture, we're going to talk about some less common functions, but I don't want the name to sort of mislead you. These are a very close second, often talked about a bunch. The first one that we're going to see is a little different than anything we've seen so far, and it's called the greatest integer function. And it's written a couple different ways, and in all honesty, it varies depending on sort of book that you pick up. So the greatest integer function, when you write it, some books use a straight up bracket around the x. Other books I've seen use the sort of floor of the bracket, because this function sometimes is called the floor function. It's an interesting little function. It's a different way to think about rounding. Most of us, when we were taught how to round, we were taught like 5 or more, we round up, and if it's less than 5, we round down. The cute little expression, of course, is like 5 or more, let it soar, 5 or less, let it rest. This function is called the floor function because you always round down. You always round down. So what does that mean? So if I hand you something, for example, I'll use the floor notation just to stress this, but if I hand you like 3.4, all right, we're going to round down to the nearest integer, so this is 3. Fine. Okay, so now here's where it gets weird. If I hand you like 3.5, normally this would be 4. We round up, but of course here it's 3 as well. We round down. And this round down is very strict. It's like if you're not 4, you're rounding down. So even if you're like 3.9, I don't know, 99 or something like that, that's not 4. So that would still have to be like rounded up. But we don't round up anymore. We round down. This is in fact 3. If I hand you just an integer itself, so the round to 3 to integer, you just get back yourself, that's fine. But the weird stuff is like if you're super close to 3, you round down. And that's true for any number. So for example, you could throw in like the floor of pi. For the reminder, pi is like 3.14. So it's like 3 and change, you round to 3 as well. And this is true for any number you want. So 2.999 rounds down to 2. 10.001 rounds down to 10. So you just keep rounding down. This is the rule. There are applications where you would use this and you would round like this. So what does this graph look like? What does this graph look like? So if I'm 0, I round to 0, and I go all the way up to 1. But at 1, I jump up. So the round to 1, I'm 1. And then if I'm 1.1, 1.2, 1.3, I'm still 1. Even 1.8, 1.9. When I get to 2, I jump up again. And you get this sort of staircase, and the pattern continues even in the negatives. You can certainly do the same rounding down for negatives. And you get this staircase where there's always this closed circle on the left of the stair and this open circle on the right of the stair. So that should be open and close, etc., etc., etc. So this is called, this graph is called a step function. This is called a step function. It's a little weird. It's kind of neat, but it's a little staircase here, and each interval is 1 and each height is 1. But it passes the vertical line test. If you want to start drawing vertical lines, you will only pass this graph once. It's a nice little graph, and it's a perfectly good function. Right? You play the game all day. You give me a number, and I will just round it down. So it's a great little function. So let's talk about its properties. A little weird. Domain, what am I allowed to round down? Any number I want, so its domain is all reals. Its range is weird. The only numbers you get back are integers. So the fancy way to write this, if you want, you can write as like the set -3, -2, -1, 0, 1, 2, 3. That gets at the idea. This is a little sort of more advanced than what we want to get at, but you have to realize I don't get back every single real number. I'm always going to give you an integer back. The fancy way to say this, I guess if you want to get a little fancy in math speak, this set of integers is denoted with a z. Why is it z? Z for Zahlen, a little German coming in there. This is a fancy way to say integers. The G, though, it picks it up from the German way to say it. So Z with a double bar. That's a little probably more tough than you'd ever see in this course, but it's good to sort of know it and see it. So domain is all reals, range is all integers. Okay, so do we want to get into the other stuff with this one? We could talk about it a little bit. What's the x-intercept? Where does this graph cross the x-axis? Ooh, tough. If you want, pause the video and try this. Look at the graph too to help you out here. It has infinitely many x-intercepts. X-intercept is from 0 to 1, bracket on 0 because it's a closed circle, and then open circle, which means an into parentheses on 1 there as well. The y-intercept, a little more standard. Where does this graph cross the y-axis? That is only at the origin. That's kind of nice. And then end behavior does go off to infinity and negative infinity as we talk about it, but in a stepwise fashion. So a little weird function, kind of neat, kind of different, and we like it, but it doesn't come up as much, but still good one to know about just because it's going to be an example of a non-traditional function that we're going to use a lot in this course. So this is the greatest integer function, the floor function, the round down function, all these things. Another way to write a function that's not as obvious is something called a piece piecewise function. I call these like schizophrenic functions. They have multiple personalities. They are built or cut and pasted from other functions. So let me give you an example. I'll write it first and then we'll talk about it. And these you read a little bit right to left. So they have a whole bunch of sort of different flavor going to them as we go through it. Okay, so how would I read this function if I presented this to you? This is f of x equals brackets 1 minus x for x less than or equal to 1, and then x squared for x greater than 1. What I'm handing you is like a copy and paste, or like two functions that are cut together. This is a line and this is a quadratic. These are things that we know. But this is saying, you read this right to left, like if x is less than or equal to negative 1, then I do 1 minus x. Then I'm this particular graph, this function. If x is greater than 1, then I'm the quadratic x squared. So you just have to be careful and think about like what you're drawing and just follow the rules. And again, read this right to left. So if x is less than negative 1, less than or equal, then I am 1 minus x. So in particular, like let's just start plugging in points. If x is negative 1, then this is 1 minus negative 1. So that's like 2 in particular. So let's put 2 on the map, and there it is. And now what is this? This is a line with slope negative 1, so it's coming down. And we graph this thing, sketch it more or less, but it's a line. And at negative 1, I truly am 1 minus minus 1 is 2, so I'm going to have a nice closed circle at 2. It's just a line, and it goes on and on forever and ever and ever. When x is greater than, let's make this negative 1 as well. When I'm greater than negative 1, I want to be x squared. I want to be x squared. So this function, as soon as you move past to the right of negative 1, it becomes the parabola, but not the entire parabola, just the part of it that is greater than negative 1. Again, negative 1 here on this number. So what does that mean for my function? So I am the parabola. So I plug in negative 1 squared, I get back 1, but this is strictly greater than. So it's an open circle. The closed circle corresponds to the equals part of the inequality, open circle to the not to the just a strictly greater than. And then on the parabola, which normal U-shaped curve goes to the origin, often doing his thing. So you can kind of see when I say like this feels like it's cut and paste a little bit. This is what they look like. They don't have to be connected. They certainly can be connected if the pieces are lined up just right. But you get these sort of like copy and pasted, cut and pasted graph that are there together. And you can evaluate these things. So if I ask you for like f of 2, you say, okay, 2, which branch, which piece do I use? You just see which condition is satisfied. Is 2 less than or equal to negative 1? No. Is 2 greater than negative 1? Yes. Okay, so I'll be the parabola. And 2 is 2 squared, which is, of course, 4. And I can ask you, like, what's f of 0? You say, okay, same thing. 0 is greater than negative 1, so this is the parabola, so 0 squared. But, like, what is f of negative 2? Aha, well, negative 2 is less than negative 1, so I'll use the top branch, and you get 1 minus minus 2, better known as 3. So that's perfectly fine. It's domain. You can play around with this thing. What are the values you're allowed to plug in? I'm allowed to plug in any x less than or equal to negative 1. The line has no problems with that. And I'm greater than 1, negative 1 as well, and square. This domain is all reals. Its range is a little funny. You say, well, what y values does this thing take on? You might be tempted at first to sort of exclude this little gap between the two pieces from 1 and 2, but the parabola hits those on the right side anyway. So its range is actually all reals. And you can ask all the same questions. What is its x-intercept? What's its y-intercept? You can see it from the graph that it goes to the origin. And end behavior, as x gets large, the function wants to go to infinity. That's the parabola dictating that. And as x gets small, then the function can get to positive infinity as well. And that's the line that is dictating that. So you can have a piecewise function with many pieces, 1 piece, 2 piece, 3 piece, 10 pieces, who cares? You follow the rules, you look at it right to left when you evaluate, and you graph this thing in pieces, paying careful attention to open circles versus closed circles. You've actually seen a piecewise function before, although you never actually called it that, and this is the absolute value graph. So when we describe the absolute value graph, most people say, oh, it returns the positive, right? They give it to you in words. But I want you to think of it now as a piecewise function. So think about it treats different pieces separately. If I'm a positive number, again, you write this right to left. So if I'm positive or 0, so if x is 5, if x is 10, if x is 0, the absolute value graph does nothing. It just returns the number. Like, what's the absolute value of 5? 5, right? Like, you don't need the bars. They don't really do anything. The only time it does any work is if what if x is negative? Now, you really got to think, like, how do you turn a negative number positive? Well, you multiply it by a negative. Two negatives make a positive. So if I hand you negative 5, then the absolute value function will return negative 5. Two negatives gives you positive 5. So the bars on this graph, really it's a piecewise function, and that also hopefully lends some intuition as to why the graph looks like two pieces. When I am greater than or equal to 0, I am the line y equals x. When I am negative, when I'm less than 0, I am the line y equals negative x. Put them together, glue them together, and you get one function called the absolute value function, and you get this V shape to it. The little vertex at the V, this is called a cusp in fancy math language. That's called a cusp, the vertex of this piece. So you've seen a piecewise function before. You've gone through all the things with domain, range, all the properties of it, and behavior, but you just normally don't see it presented this way. But just understand, every time you work with an absolute value graph, you are working with a piecewise function. Other functions that I just want to introduce, I'm not going to ask you a ton about it now, but I want you to understand the general properties or what it looks like. You should sort of know the general thing of this. So sine and cosine, these are functions that oscillate. They're waves. We'll just do from 0 to 2 pi. We're going to think about it in terms of radians. So 0, pi, and 2 pi. Again, just the behavior graph. We don't need to go through too much here. We'll spend lots and lots of time on trig functions. But this is a wave function. It will continue to wave both in the negative direction and positive direction. Some key features of this graph, just what makes it sine. This is, I should probably label this if I'm talking about it. Y equals sine of x. Goes right through the origin. Goes through pi. Goes through 2 pi. It maxes out at 1 and it has a min, like it oscillates. It does a wave between 1 and negative 1. The fancy way to say that it goes up and down is to say that it oscillates. Cosine is very similar. It is also a wave function in itself, but instead of starting at the origin, I want you to think about it as starting at 1. So it goes down, and then it goes up. That's one period of this wave. And it also will go from 0 to 2 pi. It crosses the x-axis, though, at pi over 2. Its minimum occurs at pi, and then it has another x-intercept at 3 pi over 2, or like pi and a half. And like sine, it has the same max and min from negative 1 to 1. So this is y equals cosine of x. I don't want to get too into what they are. We'll spend lots of time on it now, but just the domain of these things, this wave goes on forever, so its domain is all reals. The domain is all reals for cosine as well. And the range, so what are the set of y values? From -1 to 1. And that's both true for sine and cosine. You can get -1 and 1, so we'll use brackets for all those. We'll leave all the other discussion of what sine and cosine are until later. But again, these are some basic graphs that come up. They come up often enough that you should kind of have the general shape of these graphs in your mind as we go through, at least until we get to the chapters where we study these in more detail. And last but not least, now this is under the section called least common functions, but let's draw this for a second. So the unit circle is one very special circle out of many of these things. So the unit circle, a couple things about it, it has radius r equals 1. So friendly reminder, the radius is the distance from the center of the circle to the end. So this is at 1. So this is a unit circle. Again, there are lots of circles, but if I say the unit circle, I mean this one in particular. The unit circle, the radius is 1. That's true. Radius, you can start at center and go in any direction. So you have 1 on the top, you have -1 over here on the left, and -1 on the bottom as well. And it is centered, so lots of circles with radius 1. Think of it like a magnet, you can move around. But its center, if I say the unit circle, it's centered at the origin. So this particular circle, the one with the center at the origin and radius 1, this is what's called the unit circle. We're going to study this thing a lot, especially when we get to the trigonometry chapter. All I want you to know right now is the unit circle, radius 1, center at 0. Let's draw a prettier circle than perhaps what I drew here. And the equation for that, like if you want to go graph this in Desmos or some other website, the equation for this is x squared plus y squared is 1. That's an equation. Again, the unit circle, you can imagine such a fundamental object to math. You should know the equation when you see it. X squared plus y squared to 1. This is the equation of the unit circle. And that gives you the circle radius 1, center at 0. If you want to go graph this and go play around with it, have some fun with it as well. In particular, though, one thing you just got to call out, it is not a function. Not a function, sadly. It fails the vertical line test. So this will be an object that's not a function, one of the few objects that are not a function in this class that we talk about, but it's so important you should know when you see it, and just know that it has an equation that describes it. X squared plus y squared is 1. All right, add these to your list. Great job. We'll see you next time. Hi everyone, and welcome to our lecture on composition of functions. So here's what we're going to be given. We're usually going to be given two functions. So a function f and a function g. Of course, they could be called anything they want. And we're going to define what's known as the composition of the two function, or the composite function. And the composite function will be denoted as f composed with g. So this little circle, when you write it, is a little circle in the middle, but you don't read it as f circle g, you read it as f composed with g. And this function is going to be defined as f composed of g. This new function is f of g of x. So we take x and we shove it into f. And this is a property, this is an operation of functions that is unique to functions. If you think about this, this is not multiplication, it's not addition, it's not subtraction, not division. It is a composition. And this is something you cannot do with numbers. You can't take 3 and shove it into 2, or vice versa, but you can apply a function to another function. So let's do an example of this just to see what I mean. So if I give you a function f of x equals x squared, and let's say another function g of x equals x plus 1, so we have a nice quadratic function, the parabola, a nice line, x plus 1, and I say take these two functions and let's make a new function, I can certainly find the composite of the two functions f composed with g. And this is a new function in terms of x, and remember it's defined as taking g and plugging it into the function f. So when we write this out, let's write out all the steps. So this is f of g. Now g is x plus 1, so we'll substitute the equation for g. And then the function f says, give me something and I will square it. And again, it doesn't care if it's a number, an expression, or an equation. So you give it x plus 1, and the function says, fine, I will square x plus 1. And you can FOIL this out and you can get x squared plus 2x plus 1. Great. What's nice about this operation is that it doesn't matter which function goes where. You can certainly take f and also apply it to g. So this is now the composition of g composed with f. And so you read that, g composed with f. And this becomes g of f of x. In particular, that's g of x squared, since f was defined to be x squared. And g says, you give me something and I'll just add 1. You give me anything, I'll add 1. So sure, we'll give it x squared. And g says, I'll take it and add 1 to get back the new function, x squared plus 1. And again, look at this and realize this is not a product or sum or anything like that. It is truly a new operation that is nice and unique to functions. In particular, this example highlights an important property, and this is that if you compose two functions, order matters. Order matters. So we say that the f composed with g is in general not equal to g composed with f. This is important. The fancy way to say this, of course, is saying that the operation is not commutative. Good reminder for you. Not commutative. And you've seen things that are commutative and you've seen things that are not. So this says order matters. So be careful the order that you put it in. If you mix up the order, you might get the wrong answer. So for example, like addition, 2 plus 3 is 3 plus 2. Order doesn't matter which one you do first. Multiplication, 2 times 3 is 3 times 2. And again, order doesn't matter, so you don't really have to be careful which one comes first. However, if you have division, let's say, division is like composition. It's not commutative. So for example, 2 divided by 3 is not 3 divided by 2. Subtraction, also not commutative. 2 minus 3 is not the same as 3 minus 2. So you just have to be careful of the order. Composition falls under one of these operations where order matters. And Students in class like to say, fog is not equal to goff. Ha ha ha, yes, I get it. But of course, we wouldn't say it like that. We say f composed with g is in general not equal to g composed with f. And a fancier way that the operation is not commutative. All right, so let's do a couple more examples to get familiar with this idea. And let's look at the function f of x equals the square root of x plus 4, all under the square root. Now here's something I want to do that's kind of neat. You can do this. You can take a function and you can compose it with itself. Again, like imagine taking 2 and then like throwing 2 in itself. You just can't do it. But functions you certainly can. And so I can give you the same function and kind of treat it as itself. So what is the function composed with itself? Well, this says take f and plug in the equation for f. And this says, so what does f do? It says, give me something, I'll add 4 and throw it under the square root. So we'll do that. It says, give me something, so I'm handing you root x plus 4. The function will add 4, and I'll throw the whole thing under the square root. So you have like a square root inside a square root. It's kind of scary. This is one of the reasons why you usually see square roots written with 1/2 to avoid this sort of notation. So what you know how you might see this is maybe x plus 4 to the 1/2, and then plus 4, and then maybe the whole thing with parentheses or brackets raised to the 1/2. So taking compositions of functions with itself is certainly something that you can do. Another thing you can do, just like you can multiply 3 numbers together, is you can certainly take the composition of more than 2 functions. So now let me give you 3 functions. F of x equals 3x minus 2. G of x is x squared. And then h of x is x to the 1/3. And I'd like to find f composed with g composed with h. And there's nothing really stopping you from doing 3, although it gets a little tedious after 3, but let's put these 3 together. And the idea is the same. I take f of g of h of x. And you work your way right to left when you solve these things, so stare at the middle and work your way out. So this says I'm going to take f of g, and I'm going to plug in h, which is x to the 1/3. And this says feed h into g. Take square something that's x to the 1/3. So g just says give me whatever you want, I'll square it, no problem. So g says I will square x to the 1/3, and you get x to the 1/3 squared. Now it's probably in our interest to clean this up a little bit. Maybe I'll go over here. So you get equals, remember exponents multiply, so you get x to the 2/3. So simplify when you can. And last but not least, we have f, and f says give me something. I'll multiply it by 3 and subtract 2. So that's what f will do. It'll take x to the 2/3, it'll multiply it by 3 and subtract 2. And so you can take compositions of more than one functions, and again I can mix and match the order. I can call the variables theta, t, or whatever Greek letter I want. I can call the functions f, g, h, I, j, k, who cares? So just be ready for any sort of these in any order. So the big idea of composition is that if I give you 2 functions, it's really you're creating another function from them. And so when you do this, you can ask all the same questions that you did with any other function. What's the domain? What's the range? What's the graph? What's the end behavior? What are the intercepts? Any asymptotes? This sort of thing. So let's go through one of these more detailed studies of a function given f of x is 1 over x and g of x is x squared plus 2x. Let's find the composition f composed with g. And this says we take f and we plug in g of x. So it says we take f and we're going to use the equation for g, x squared plus 2x. And f is the reciprocal function 1 over. And this becomes 1 over x squared plus 2x. These are our new functions, our composition. So let's ask some questions that we ask with any function. In particular, what's the domain? What's the domain? So what's the domain of this new function? So 1 over x squared, I have a fraction. Like any fraction, I can't have the denominator be 0. So I want to study the points where x squared plus 2x is 0. I'll throw these away. You can factor. There's an x in both terms. And you get x plus 2 to be 0. And so x equals 0. And x equals minus 2, these are going to be the places where the denominator is 0. So for my answer, I throw these away. My domain would be, the answer would be x not equal to 0. and x not equal to -2. This is my domain. There's a few ways to write that using interval notation or set notation, but we'll go with this. A couple other things you can talk about, like what are some horizontal asymptotes maybe. You can also do some intercepts, but horizontal asymptote, we want to know what's the end behavior. So as x gets really, really large, where's the function going to go? Stare at this for a minute. This function, everything's happening in the denominator. If I take a large number and square it and then add 2 times that large number, I'm going to get back an even larger number. So this denominator is getting huge as x gets really, really big. What that happens is, think of it like 1 over 100, 1 over a million, 1 over a billion, 1 over a trillion. Then the entire function wants to go to 0. So you're going to have a nice function that approaches 0 from above. You can have a nice horizontal asymptote on the x-axis. Other things we ask for functions, maybe what's the x-intercept? So where does this graph cross the x-axis? Remember, you set y equal to 0. You set the function equal to 0. So you get 0 equals 1 over x squared plus 2x. In that case, you say, well, what values? Remember, fraction 0, when the top is 0, you can cross multiply to see this, however you want to do this. But you're going to get, if you cross multiply, you get 0 equals 1. Now, people look at this and say, oh, no, I made a mistake. You didn't make a mistake. Remember, you're trying to say, what values of x make this true? So when you get 0 equals 1, you say, what values of x make 0 equal to 1? And I hope you agree that there are none. So the way to interpret this is that there are no x-intercepts. This graph will never cross the x-axis. Another thing we can ask about where the y-intercepts. We've seen this before. This is when you set x equal to 0, but we already said that x can't be 0 from the domain, so we have no y-intercepts. So we're getting all the pieces that we want here. And again, if you want to go graph this and see what the algebra is telling you, that's not a bad thing to do. But you don't need the graph to start answering some of these questions. And again, the function created by function composition is just another example of a new kind of function. And we ask all the same questions given any function. Let's do one more skill related to composition. And I'm going to give you h of x is 3x squared plus 7x all raised to the 9th. And here's what I want you to do. It's like reverse now. I want you to pull this apart. So I want you to write this function as the composition of two functions. So write this as f composed with g. What is f and what is g of x? What are the two functions that make this function as a composition? If you stare at this hard enough, you can see that the h is taking something and raising it to the 9th. So that leads to our understanding of what the outside function is going to do. It's going to say, give me something and I'll raise it to the 9th. And the inside function, you can say, well, this is 3x squared plus 7x. So there isn't a lot of math to do here, for lack of a better word. It's more of looking at the function and kind of breaking it down, seeing it as a recipe. It says, give me an x and I'll square it times 3 plus 7x. So I'll do that part first. And then when that's done, I raise it to the 9th. And when you go through that process and can see a function as it steps, or at least in larger pieces, then you're getting closer to seeing this as a composition. All right, so have fun with this idea. Grab any two functions, grab your favorite two functions, start putting them together, take a function, compose it with itself, and just start getting used to asking all these questions about what functions do I create? Do I get anything new and exciting? What properties stay the same? And what properties are different? All right, good job on this one. I'll see you next time. All right, hi everyone, and welcome to our lecture on exponential functions. So just to remind you what we've seen so far, we've seen functions of the form f of x equals x squared. These are called polynomials. These are quadratic functions. Their graphs are parabolas. Notice the variable is in the base, and then the constant, the number, is upstairs. What we'd like to do now is switch it and talk about exponential functions, and we're going to write things now the form 2 to the x, or perhaps 3 to the x, 4 to the x. You can pick any number you want as the base, but the key is the base is now a constant, and the variable now becomes the exponent. When the variable is in the exponent, these are called exponential functions. The base can be any number you want. It doesn't have to be a pretty number like 2 or 3. It could be pi or square root of 2 or something like that. So this leads to our general definition of an exponential function. So we say an exponential function with base a, we're going to let a be some constant here, is of the form f of x equals a to the x. Again, notice that even though there's letters everywhere, a is a constant and the variable is in the exponent. So x can be any real number. There's no restriction on x, but we have some restrictions on the base. We need the base to be positive, and a is not equal to 1. We'll talk more about these restrictions in a second. So let's look at some examples here. Again, you can graph these on a calculator, or you can plug them into Desmos if you'd like as well. So let's take the function f of x equals 2x. So start plugging in some values here. Notice our base here is a. So if you plug in x equals 0, you get 2 to the 0, which of course is 1. And if you get 2 to the 1, that's 2, and then 2 squared is 4. So it starts to grow very quickly, and this sort of behavior, this sort of graph looks like exponential growth. And this is the general shape for any value of a that is greater than 1. We're going to look at exponential growth. In the case that a is 1, let's think about this for a second. Why would I not want 1? There's nothing stopping me from doing 1 to the x. But what's the problem? What's 1 squared? What's 1 cubed? What's 1 to the 4th? Instead of an exponential function with this nice exponential shape of a graph, I just get a constant function. I just get 1 for everything. So this is not really an exponential function. This is actually the function f of x equals 1. So because it's not really an exponential function, and I don't want to sort of include it, we throw it out. We say, look, if you want to talk about constant functions, go do that somewhere else, but I don't want to do it here when I'm trying to study exponential functions. The other case that you can have is if a is a nice little fraction between 0 and 1. So let's say 1/2 to a power, something like this. That's perfectly allowed. Again, I'm positive, and I'm just less than 1. In that case, think of the numbers you're going to get. Graph this if you want to think about it. If you plug in 0, you still get 1. That's all fine. But then all of a sudden, if you take 1, you get a half. And if you plug in 2, you get a fourth. And your numbers get smaller. And that is going to be the general shape. We're going to say this is exponential decay when you plug in as a base a number that's less than 1. Because in that case, when you start taking powers, the numbers get smaller. Now you could see this as 1 to the x, but by properties of algebra, remember the exponent hits both the numerator and the denominator. So honestly, it's more common to see this as 1 over 2x. Again, if you see it in this form, just remember the base itself is 1/2 and not just 2. They brought the x into both the numerator and the denominator. Whenever we have a new function, we want to start asking general questions that we would ask for any function, including what's the domain? What are the numbers that I'm allowed to plug in to a function of the form f of x equals a to the x? And just remember that a is positive and a is not equal to 1. So what am I allowed to plug in here? And it turns out that the domain of this function, whether you have growth or decay, so let's remind yourself what the graphs look like in general. So this is the graph where a is greater than 1. And if you have decay, we go from high to low. This is the case where I'm between a equals 0 and 1. So I have growth or decay. In any case, in either of these two cases, the domain turns out to be all real numbers. There's not a problem plugging in any power you want. This is any real number you want. So let's say I just take the easy case 2 to the x, something simple. Well, what does it mean to plug in different numbers? So if I take f of 4, this becomes 2 to the 4th. That's fine. That's 16. There's nothing wrong with doing that. What if I take something that's not so pretty? What if I take pi? Well, you have 2 to the pi. Now, we don't know that number, but your calculator does, right? This is just some number. When we write it, we usually leave it as 2 to the pi. If the question ever wants you to write it 3 decimals, 4 decimals, or whatever, then sure, go grab a calculator and plug it in. But pick your favorite ugly numbers and plug in, and it will all work. If you need decimals, again, grab a technology, grab a calculator, grab the internet, but you can always write these things. So the domain is all reals. So the next question, of course, is what is the range? If you look at the graph of either case, either growth or decay, the outputs of all these functions are positive. And you have a nice horizontal asymptote in either case. So the range in this case we're going to say is all y values that are positive. So I write y is greater than 0. Notice I do not include 0. This function never gets to 0. We have a nice asymptote at the x-axis, so y is greater than 0. There's a few ways to write this range. You could write it using inequalities. Of course, you could also write this as 0 to infinity. Notice I'm using parentheses on both 0 and infinity to show that I don't want 0. And of course, you always use parentheses with infinity because you can never get to infinity. So there's lots of ways to write this. If you want to get super fancy, of course, you could also write this as real numbers, but just the positive ones. So sometimes once in a while you see this as r plus. So for any exponential function in its base form, y f of x equals a to the x, you're going to have domain all reals and range all positive numbers. This, of course, will change if you start translating or rotating or shifting the graph, but in its sort of base form, basic form, this is your domain, this is your range. No matter what kind of exponential function you start with, whether it is growth or decay, so friendly reminder, if you have growth, we say it goes from low to high. This is when your base is greater than 1. If you have decay, exponential decay, think like zombie apocalypse, then you say that a is less than 1. but by restriction it has to be greater than 0, so you're in this very specific case. Now notice there's still infinitely many numbers between 0 and 1, so there's lots of numbers you can choose from. So we have growth or decay. There's some common themes to both of these, and these are called properties of the exponential function. So the first one that says, if a is greater than 1, then the function is always increasing. This is a very nice property. It goes up forever. It never has a hump. It never goes down. It never starts to decrease. It's always increasing. And if a is in the other case, where I'm between 0 and 1, then f of x is always decreasing. So this is interesting. It's a function, I don't know if we've seen these before, but it always goes up or it always goes down. There's no chain. In particular, they all have very nice intercepts. The y-intercept, remember how to find the y-intercept? You set x equal to 0. No matter what your base is, if I have a to the 0, friendly reminder, any number raised to the 0 is going to be 1. So the y-intercept of the graph is always at 0, 1. Oftentimes, if you start picking random points on the curve, they're pretty ugly numbers. They're usually decimals or gross, but every single graph in this form, a to the x, is going to have a very, very nice intercept. So when you have nice numbers that appear in the graph, you should know what they are. So the y-intercept is a nice one. Again, that's because if I plug in 0, sometimes people confuse this, like what's 2 to the 0? Everyone should say 1. What's 3 to the 0? 1. Those sort of things. Next, number 3 is that the graph has a horizontal asymptote. I'm going to abbreviate that with HA. Horizontal asymptote at the x-axis, which is given by the equation y equals 0. So either growth or decay, there's a nice asymptote here. Remember what our asymptote is. It means that the graph's going to get infinitely close but never touch. So we have a nice horizontal asymptote in either case. 4, no matter if we're growth or decay, the domain is going to be all reals and the range is going to be positive y values. And last but not least, the function f of x is 1 to 1. Now let's talk about 1 to 1 for a second. So 1 to 1 means we pass the horizontal line test. Horizontal line test says if you start drawing horizontal lines, then you're only going to cross the graph once. That means that for every input, there's only one output. The algebraic way to say that is if f of x1 equals f of x2, then that implies that x1 equals x2. This says if the y values are equal, if you have two different points and the y values are equal, the x value is the same. Again, compare this to the parabola where that's not true. If I take the y value at positive 1, I could have plugged in either positive 1 for x squared, right? 1 squared is 1, or I could have plugged in negative 1 because negative 1 squared is also 1. So there's two x values that go to the same y value. This is just another property that separates this exponential graph and kind of gives it its own characteristics, its own unique flavor. In particular, we will see that when we have a one-to-one function, we're going to have an inverse function. We're going to be able to define an inverse function. And maybe you know this, maybe you don't, but the inverse of the exponential, of course, is the logarithm. So step 5 here, property 5, is allowing us to sort of pave the way so we can talk about logarithms, whether you want to or not. Solving exponential equations sometimes can be tricky, but we're going to use this one-to-one property of it. And here's the property that I want to use. So if a to the x1 is equal to a to the x2, then x1 equals x2. Let's think about that for a second. So remember here, the key here is the base is the same. So if I have 2 to the 3 equals 2 to the something, if I know the bases are the same, from that I can write the equation 3 must equal my exponent, right? So if the bases are the same, the exponents are the same. This kind of feels like what we've been doing in algebra all along. Whatever we do to the left side, we must do to the right side. So it's the same idea. So for numbers, they're not too exciting. Like obviously 2 to the 2 cubed is 2 to the something, but it's often going to come into play when we talk about exponents. So for example, if I have 2 to the 3x minus 1 is equal to 1, well, what do I do in this case? How do I solve for x? This is where we're going. How do we solve for x? Well, the key to this one is to realize 1, well, wait a minute, that's my y-intercept. So I can write this as 2, 3x minus 1 is going to equal 2 to the 0. Do we all agree that 2 to the 0 is 1? I hope so. So now we're going to use the properties of exponential equations. I have the same base, and since they're equal, I must have the same exponent. And this is a beautiful little skill here because you take a very difficult exponential equation and you completely remove it. And from this you get, well, if the bases are the same, guess what? The exponents have to be the same and you have a nice linear equation. So you've taken all the difficulty out of this equation. From here, it's an easy solve for x. You get 1/3 and you're done. And you can go back and check that it works, of course, in the original equation. This property of exponential equations is going to allow us to solve for x in a whole new family of functions. Let's do a couple of examples. Let's look at the example f of x equals 3 raised to the 4 minus x. I'd like to find the value of x such that f of x is equal to 1/9. Let's say it one more time. So when f of x is 3 to the 4 minus x, find x such that f of x is equal to 1/9. This is in fact saying let's set 1/9 equal to 3 raised to the 4 minus x. Now in its current form this looks a little scary, but I want to use the property of exponential equations. In particular, I really need things to be the same base. So I see 1/9. Now 9 is the nice power of 3, so why don't I write 1/9 as 1 over 3 squared? We're getting there, okay. But it's still not a form of the power of 3, at least not yet. So do you see how I can turn this into a power of 3? Rule are we going to use to get this to be a power of 3? Well, 1 over 3 squared is the same as 3 to the minus 2, and all of a sudden I have two equations with the same base. So this takes a little bit of rearranging. Don't be afraid to get in there and get your hands dirty as you do this. But 3 to the negative 2 is 3 to the 4 minus x. That's amazing because now I took this exponential equation and I'm just going to look at the exponents. Because the bases are the same, I can leave the world of exponential equations and look only at the exponents, make them equal to each other, and of course solve for x. Let's solve for x here. So let's add x to both sides. So we get x minus 2 is 4. Add 2 to both sides and I get x is 6. So even when they don't look like they have the same base to start with, look for powers. Oftentimes when these questions are set up correctly, when you have 3, you'll have 9 or 27 or just some other powers that you'll find, and you can write this. We'll get into more complicated exponential equations later, but for now be able to solve these, and I think you're off to a good start. All right, great job on this video, and we'll see you next time. All right, hi everyone, and welcome to our lecture on solving exponential equations. I thought just in this video we would just do a bunch of examples and work through the thought process on how to do them. So let's just start off with something basic. 5 to the 3x equals 5 to the 7x minus 2. The goal here is to solve for x. When you see these problems, sure, they might be just presented as equations, but you have to remember as you go through and see more complicated examples, they're going to be presented in word problems, perhaps in different units, perhaps with scientific notation. That's all fine, but the basic skills of understanding how to solve for x is the same. The key thing to realize is because they have the same base, they must have the same exponent. So you look at an exponential equation and it's almost, I don't know, it feels like cheating a little bit. You get to remove the exponent, you get to remove the base, and therefore, 3 little dots in a triangle means therefore, you get to write the two exponents as being equal. So 3x equals 7x minus 2. This is a beautiful step. It's extremely important to realize that you're only allowed to do this because the bases are the same. If the bases are not the same, you are not allowed to equate the exponents. Once you have it from here, I have a nice linear equation. We know how to solve these. I'll subtract 3x from both sides. I get 0 equals 4x minus 2. Slide the 2 over, and you get 4x equals 2. And of course, x equals 2 over 4, or 1/2. I recommend as we go through these to pause the video as I put the equation on the board, and then see if you can solve it first, and then go through my answer. Let's do another example. What if I had 4t squared is equal to 6 minus t? Same thing, solve for t here. Now t is a variable. These are dummy variables. I could have x, I could have a, I could have b, I could have Greek letters, alpha, beta, gamma, who cares? But we're always solving for the variable. In this particular example, same basis means I can set the equations equal to each other. And now I have a nice quadratic equation. T squared equals 6 minus t. Now be careful, what do you do with this? You set all the variables to the same side. So I'll move the t over to get positive t, I'll move the 6 over to get negative t, and I have a nice quadratic. There's two ways to solve a quadratic. I could always factor if I could, so let's try to factor this. Can I write it as something times something is 0? In this case, I think we can. You have x plus 3, t plus 3, and then t minus 2. You can FOIL that out and check. Again, you should always check these things to make sure that that actually works. We would FOIL this out to check. When we do that, we have t plus 3 is 0, or t minus 2 is 0. Two things multiplied together give you 0, means one of them has to be 0. And we get t is minus 3, or t is equal to 2. So we have two answers here, and that makes sense. Get into the habit, once you have your answers, go back and check, plug in your answer. Is it true? Let's say plug in for minus t, that minus t cubed, minus 3 cubed, is that equal to 4 to the 6 minus minus 3. Watch out for that minus, the double negative there. Minus 3 times minus 3, of course, that's 4 to the 9. And is that equal to 6 minus minus 3? That's the same as 6 plus 3, 6 to the 9. Absolutely, it works. Let's also check the other one, it equals 2. Is it true that 4 to the 2 squared, is that actually equal to 4 to the 6 minus 2? Again, we want to make sure our answers work here. And of course, you get 4 to the 4th is in fact equal to 6 minus 2. That's also 4. So everything works out to be okay. Get used to checking your answers. You never know if you're going to get an extraneous solution. Let's do another one. What if we had 3 to the x equals to 9 x plus 5. Now you may say, oh man, I don't have the same base. I don't know what to do. It is wrong here to set x equal to x plus 5. They are not the same base. We cannot set x equal to x plus 5. Let me say that one more time. You cannot set x equal to x plus 5 because your bases are different. However, being clever, you can certainly write that 9 as 3 squared. So we can write 3 squared raised to the x plus 5. And now we use our properties of exponents. Exponent to an exponent means we multiply. So I get 3 to the x is equal to 3 to the 2x plus 10. Now and only now are we able to equate the exponents and get x equals 2x plus 10. Subtract x from both sides. We get 0 is x plus 10, or x equals minus 10. Oh heck, don't take my word for it. Let's check 3 to the minus 10, is that equal to 9 to the minus 10 plus 5? This is our question. So 3 to the negative 10, some number, could use a calculator, is that equal, so to 9 to the minus 10 plus 5, that's minus 5. Now you can check this with a calculator, or you can start moving things around and writing this as minus 2 times 5 if you don't want to grab a calculator. And you can write minus 2 times 5 as 3 squared to the minus 5, and all of a sudden, it might have been easier just to grab a calculator, but absolutely they are the same. So it all works out as it should. Always check your work. Let's do another one. How about 4 to the 5 minus 9x equals 1 over 8 x minus 2. Solve for x. Now, once again, this is not set up in the most perfect format. We're going to have to do some rearranging and try to think what, if any, common base can I write 4 and 8 as. So you look at 4, you look at 8, and of course you think, well, wait a minute, 4 is 2 squared, and 8 is 2 cubed. So can I somehow, some way write these things like that? Let's see. So 2 squared, let's write 4 as 2 squared, and we have 5 minus 9x, and that's going to be equal to 1 over, now 8 is 2 cubed. Again, know your small powers, 8 is 2 cubed. And you get x minus 2. Now I play around with these things. Remember, exponent to an exponent means I multiply them together. So 2 times 5 is 10 minus 18x. And I keep going on this side. I get 1 over 2 to the 3x minus 6. I still cannot equate the exponents. This is an important step to realize because I have a 2 as my base here. And remember, this is 1/2 as my base. If you think about just with the exponent downstairs, this is really 3 to the x minus 6. And 1/2 is your base. So 2 and 1/2 are not the same. The trick, of course, from algebra is to remember that when an exponent is downstairs, I can bring it upstairs at the cost of a minus sign. I'm certainly allowed to bring it upstairs if I introduce a minus sign, and that's going to allow me to write this expression with a common base. Now I have 2 to the 10 minus 18x equals 2 to the negative 3x plus 6. Using all my algebra here. Finally, I can remove the base and equate the exponents and get 3x plus 6. Let's simplify. Let's add 3x to both sides, and let's subtract 10. And when I do that, I'll do it over here. We have 10 minus 10 is 0, minus 18 plus 3 is minus 15x. So these guys cancel, the 3x's cancel, and I have 6 minus 10 is minus 4. So divide both sides by negative 15, and I have 4 over 15. 4 over 15 is as perfectly good a number as any other, so we'll leave it as that. Again, if you want to go back and use a calculator to check your work, it's really nice to see that you actually have the right answer after you do all this work. I want to stress that all this work that we've done only applies when we have the same base, or we can manipulate the equation like we did in this example to have the same base. That is not always the case. So for example, if I gave you a tougher problem, say 7x equals 9, you want to think about this for a minute, 7 to the what is equal to 9, no matter what you do, you're not going to be able to write 7 and 9 as the same base. They are just not powers of each other, and I can't solve this yet. I don't want to leave you sort of hanging with these, but just realize there are more examples out there that we cannot solve, and these sort of examples are going to use what's called logarithms, and that's usually done in a pre-calc class. So when you are on your way and ready for the next class, you will start to solve more complicated expressions using exponents like this, where you can't algebraically solve this. And of course, once you have this heavy machinery like logarithms, you can always go back and use logs to solve these kind of equations as well. But right now, I want you to get used to the understanding and the manipulation of using the one-to-one property of the exponential. So you'll solve more complicated problems in future classes. I do hope you go on to take precalculus, but in that case, you'll see logarithms. And again, if you want to go explore on your own just to see how to solve all these kinds, again, go research and find some problems using logarithms. For now, understand how to solve exponential equations with the same base, and we'll save the harder stuff for another day. All right, great job on these examples. See you next time. All right, so hi everyone. Let's start talking about polynomials, and let's start with a basic definition. We've seen these before, but so hopefully this is a little bit of review. But we talk about n being a non-negative integer, so we want it to be non-negative. That means it can be 0, and it can be positive. It just can't be negative. So we want this to be an integer. These are our numbers like 1, 2, 3, 4, 5. And we also want to pick a bunch of numbers, a1, a2, ... an. Pick any of your n favorite real numbers. And then we're going to put these all together to create what's called a polynomial. And in its most general form, we have a to the n, x to the n, plus a to the n minus 1, x to the n minus 1, plus ... a1x plus a0. This is a big, fancy, complicated way to say a polynomial, but of course you know it when you see it. The ones that you normally see are the constant polynomials. So for example, just when I have the a0 term, this is like, I don't know, how about y equals 7? So all the original coefficients in front are 0, and the last number is constant. We can call it y equals 7. You can also write, of course, as f of x equals 7. You've also seen linear equations. This is just when I have the first and second terms here from the right. So how about 3x plus 4? These are your lines. We have seen when I go one more out, you can have a quadratic. So how about 4x squared plus 7x plus 2? This is a quadratic polynomials. So polynomial just generalizes these terms, these linear terms, these quadratic expressions that we've seen before to allow for anything. And now we're just going to allow for like y equals x to the 10 plus 7x to the 9 plus, well, you get the idea. How about 3x plus 2? We'll simplify it up. But you're allowed to have as high a degree. We call the degree the exponent of the leading term here. So remember, when you have only one term, you're called a constant. This is the constant term. When you have one expression, one variable exponent, the degree is 1, you're linear. If your highest degree, when your highest exponent is 2, this is a quadratic. And polynomials with 1, 2, or 3 terms, they're called monomials, binomials, or trinomials, respectively. So this one has 3, so it's a trinomial. We usually write the terms of a polynomial in a single variable, so that the exponents are in descending order. Notice I've written each one of these in descending order from left to right. You can certainly move them around, but this is the traditional way to write it. And when a polynomial is written in this manner, the coefficient of the first term is called the leading coefficient. So in this example here, leading coefficient is 3, leading coefficient is 4, and the leading coefficient here is 1. The degree of the polynomial, this is the highest exponent that appears. So degree 10, degree 2, degree 1. Degree 1 are called linear, degree 2 are called quadratic. Some of them have names, some of them don't. If you're degree 3, so if I wrote something like with a 3, that would be called a cubic. And perhaps equally as important to know what is a polynomial, it's equivalent to know what is not a polynomial. So how do I break a polynomial? Well, how about y equals 1 over x? This is x to the minus 1, and remember we said the integer has to be non-negative, so that's not allowed. Other things that are not allowed, how about the square root of x, which is like x to the 1/2. Again, that's not an integer, although it is non-negative. And of course, all your other functions like sine, cosine, log, exponentials, those are all not as well. So polynomials are a very specific type of function. You can think of polynomials as sort of generalizing a number, and so of course you can add and subtract them. We're just going to do a couple of these by examples, but the general idea is to find and combine like terms. So if I had the quadratic polynomial negative x squared plus 3x, I'll put that in parentheses, and I subtracted from it x squared minus 5x plus 1, so I have two quadratics that subtract. Let's clean this up a little bit. So as usual, we'll bring the minus sign into all the pieces. We distribute. That's called distribution. expression. So we have minus x squared plus 3x. Here we go, ready? Minus x squared plus 5x minus 1. And now we combine like terms. So I have a degree 2 term here and a degree 2 term there. So I get minus 2x squared. I have a linear term, degree 1, 3x and 5x. Put them together, of course, you get plus 8x. And then the only constant I see is a minus 1. So my final answer is negative 2x squared plus 8x minus 1. Challenge with polynomials, of course, is that you can have many terms. So you just have to be careful. Let's do a higher degree term. Let's do 3x cubed minus x plus 5. And let's add that to negative 8x cubed plus 3x minus 9. Again, the key here is to combine and find like terms. You sort of look for all the similar terms. I see a 3x cubed and a minus 8x cubed. So it's like I combine the coefficients. 3 minus 8, that's negative 5x cubed. Negative x plus 3, so that's plus 2x. And then 5 minus 9, my constants, well, that's just good old minus 4. Let's do another example. What if I had minus 3x squared minus x plus 1 minus parentheses x squared minus 9. These aren't incredibly difficult. You just have to be careful with these minus signs. Always use parentheses just to be safe. So if we bring in the minus sign, this becomes minus 3x squared minus x plus 1 minus x squared plus 9. Oftentimes I see people do these in their head and they just make silly mistakes. I make silly mistakes sometimes, so check my work. Always look for combining the like terms. I see a degree 2, so minus 3 minus 1 is minus 4x squared. And then I see only x here. There's nothing to combine it with. That's okay. You're not always going to have things that have pairs or other parts, so we just bring it along for the ride. And then 1 and 9, of course, that's 10, and you get back another polynomial. So there's two skills here going on. One is to combine using arithmetic. You can add, subtract. We'll do multiplication in a second. But the other bigger thing to kind of keep in mind is that whenever you add or subtract two polynomials, you get back another polynomial. This is true for addition, it's true for subtraction. Let's see multiplication. It's going to turn out to be true as well. So let's look at minus 3x times 2x minus 3. So as always, we distribute, bring it in, just watch your minus signs. Minus 3 times 2, deal with the constants first, this minus 6, and then x times x is good old x squared. Add the exponents as you go, and then bring the minus 3 in again. Two negatives make a positive, and we get 9x, positive 9x. We're going to do one more. What if I had x squared minus 2, x squared minus 3? Now I'm going to do this a long way, and then I'll show you a shorter way to do it in a second. Technically, what I'm going to do is I'm going to bring both these in and distribute. So that said, I have x squared minus 2 times x squared, right? I multiply the whole first expression by the first term. And then I have minus 3, maybe I'll bring that up front, times x squared minus 2. Like, this is okay. If you know the shortcut, just hold on a second, we'll do that next. So let's bring the x squared in. When I have x squared times x squared, I have good old x to the 4th, then minus 2x squared. And then if I bring the negative 3 in, again, you can bring it in left or right, doesn't matter. Multiplication is commutative. Minus 3x squared and then plus 6. Watch that, plus 2 negatives make a positive. And there's a little bit to combine here in the middle. So this is x to the 4th minus 5x squared plus 6. This is our most simplified form after combining all like terms. But I want to show you that the idea of distribution holds even if you have more complicated polynomials. When you have the product of two binomials, that's just a polynomial with two expressions, so these are binomials, you might know this, perhaps you've heard this expression before, but you can also do this as FOIL. And we're going to look at that in the next slide. So let's do this one again, but we'll do FOIL and we can compare our answers. So FOIL stands for first, outside, inside, last. So let's look at this example one more time. It only works if you have binomials. So it's a little bit of a shortcut in a very special case. However, it comes up so much that it's worth knowing. So FOIL says take the first ones, there's your f, and start putting things together. X squared times x squared is x to the 4th. Outside says, let's go outside. There's your O. So it's x squared times negative 3. Watch the negative. You get negative 3x squared. So first, outside, here comes your inside. I'm going to run out of room here, but inside, minus 2x squared. And then, of course, last, minus 2 times minus 3 is positive 6. It's just a shortcut so you don't have to distribute. And again, it only works when you have two things times two things. So it stands for first, outside, inside, last. It just tells you the order in which you can multiply. After you do your first outside, inside, last, of course you still need to simplify, and you have to combine like terms. That gives us minus 5x squared plus 6, and you can compare. This is a little shorter, right? It's 2 lines compared to the other one where it was a little longer, but you get the same answer. So the FOIL method is quick, it's good, it's a good memory aid, it helps you things out. But you can certainly FOIL. Let's just do one more. How about we do a plus b quantity squared. Okay, so now remember here, when you have something like this, we do not bring the 2 in. It is a common rookie mistake to try to bring the 2 in over addition. So I'm just going to put this in red here. This is not a squared plus b squared. No, don't do that. I call it the high school dream theorem. Like, you wish that were true, but that is absolutely not true. But I see a lot of people make that mistake. Just remember, this is a plus b times a plus b. You are allowed to bring exponents in over multiplication. That's okay. You can certainly do that. Multiplication or division, but you cannot bring it in over addition or subtraction. So do not bring in the exponent and say, isn't it just a squared? No, you have to FOIL. You have to FOIL this out. So be careful here. When you do this, first is a squared. Outside is ab. Inside is ba, but I'll just write it as ab so it looks similar. And then last is b squared. So first, outside, inside, last. Combine the 2 terms in the middle, and you get a squared plus 2ab plus b squared. This is our final answer. Notice if you had just mistakenly brought in the square, you would have lost that middle term, and of course been just wrong. So just watch out for that. So this a squared, a plus b quantity squared, is a squared plus 2ab minus b squared. Be careful, be careful, be careful. Oftentimes you might need to rationalize a denominator. This means is a fancy way to say get rid of square roots inside the denominator. It's a little bit of an algebraic trick, and there are times when you want to do this and there are times when you don't. But sometimes you get a fraction like this where there's a square root downstairs. Now remember, this is an irrational number. And there might be a time later on in your math career when you don't want numbers downstairs. As a number itself, this is perfectly fine. You can certainly plug this into any calculator or not. But if you know a little bit about computers, rational numbers are a little messy. They get into floating point arithmetic. It's, they're not the nicest things to work with all the time. So often we're going to rationalize the denominator. That's a fancy way to say multiply by 1. But not just any 1. We're going to do 2 plus root 2 over 2 plus root 2. Now appreciate this for a minute. I am multiplying by a fraction with the same numerator and the same denominator. This fraction is a big fancy way to write the number 1. So really I have not changed my number. All right, if I take this expression with or without a new fancy 1, I'm going to get the same decimal representation back. But why would I do this? This again, you don't see the benefits of this until a little bit later, but this is a skill you want to sort of take away here. I'm multiplying fraction by a fraction. Friendly reminder, how do you multiply fractions? You go across the top and you go across the bottom. So this top fraction becomes 2 times 2 plus root 2 over 2 minus root 2 times 2 plus root 2. Notice, by the way, that I changed the sign. When you rationalize a denominator, you do want to change the sign. So because I started with a negative, I'm going to put a positive on my product, on the thing I multiply by. If they had given me a positive, I would have switched it and made it a minus. The reason for that is because you want the difference on the denominator when you work this out. Keep cleaning this up. So let's bring in the 2 to both pieces. And you get 2 times 2, which of course is 4, plus 2 root 2. So that's my numerator. And now downstairs, here it comes. I have 2 binomials multiplied together. So of course, what am I going to do? I'm going to FOIL. Here we go. So let's do it carefully. First, 2 times 2. Got that. That's 4. Outside becomes 2 times root 2. Not much I can do with that. I just put them together, 2 root 2. And then inside becomes negative 2 times root 2. That's nice. That's why we switch signs, because what's going to happen is these 2 terms cancel. And then last but not least is the outside. Negative times a positive is negative, and then root 2 times root 2 is 2. Actually, I'm going to bring that 2 back out for a second. You'll see why in 1 second. So I'm going to leave it as 2 times 2 plus root 2. Use parentheses. And my denominator is just 4 minus 2. That's 2. So now you can see why I brought the 2 back out, because it will cancel. So my final cleaned up fraction at the end of the day is a much simpler expression, 2 plus root 2. And if you want, you can check, go throw both these numbers in the calculator, use parentheses if you plug in the first expression, and you'll get the same exact decimal expression. They're exactly the same, but one's just a little more cleaned up. And this is the idea of rationalizing the denominator. Sometimes it just gives you nicer numbers to work with. Polynomials Like numbers, which you can divide, I could certainly take 2 divided by 3, you start to get into remainders and it gets a little messy. Division of polynomials in general is a little messy, and we're going to save the sort of messy expressions for another day. But just so you have the vocabulary that's associated with division of polynomials, we say that if the dividend, px, and the divisor, dx, are polynomials, so any polynomials you want, such that dx is non-zero, as usually you can't divide by 0, then there exist unique polynomials, q of x, called the quotient, and the remainder, r of x, such that p of x equals q of x times d of x plus r of x, where r of x is 0, or the degree of r of x is less than the degree of d of x. This is a fancy way to say you can divide polynomials. It gets a little messy. If you want to look up expressions, if you want to go on your own and look up more polynomial, look up synthetic division or look up polynomial division. The cases that I want you to know for sort of our purposes are the relatively simple ones, where if I did something like 8x to the 5th divided by 2x squared. I want you to be comfortable with this. I want you to realize this is 8x to the 5th divided by 2x squared. This is a monomial divided by a monomial, and then your algebra rules come into play. Divide the numbers first, the constants, the coefficients. 8 divided by 2 is of course 4. And then friendly reminder, when you have x in the base and you're dividing, you subtract exponents. So this is x to the 5 minus 2, which is x to the 3rd. So final answer is 4x cubed. We can do another one. What if I had x cubed minus 8, it's a little more complicated here, divided by x minus 2. What I'm looking for here is I don't want to go through the whole division algorithm. I want to look to factor this expression. I want to split this up somehow, some way. Realize that 2, I can write x cubed minus 8 as a factor of x minus 2. X squared plus 2x plus 4. Now that's not obvious, but this is called the difference of cubes, 8 of course being 2 cubed, but you can check that that's true. And so when you can factor, when you can break off a piece that's kind of nice, things cancel and you're left with x squared plus 2x plus 4. So some of these are going to be a little easier than others, and always look for something to factor and something to cancel as you go through and practice your examples. Just to give you one more, how about x squared minus 3x plus 2 divided by x minus 1. So I'm looking at this and saying, this is not monomials. I have some expression here. Can I factor, can I reverse FOIL my polynomial? How do I write this? So we have x minus 1. How about x plus 3? Check that, FOIL that back. You do get back the original expression. And now things cancel. And of course, this is just good old x plus 3. Let's do an example now where we solve a polynomial equation. Let's try to find 6x to the 5th plus 24x cubed equals 0. Use our algebraic skills for polynomials to see how to solve this. The first thing we look at and say, do these expressions have anything in common? Do they have any common terms? This is a degree 5 equation, also known as a quintic. And you can look at this and say, wait a minute, well 6 and 24, I could factor out a 6 from both of the coefficients. And there's 5 x's here that are multiplied together and 3 x's here, so I can certainly factor out 6x cubed. When you factor that out, you're left with x squared plus 4 is 0. When you have two terms together that multiply to give you 0, one of them has to be 0. So that's going to tell you that 6x to the cubed equals 0, or x squared plus 4 is 0. Now 6x cubed is 0, you can divide both sides by 6. You get x cubed is 0. What's the only number cubed that gives you 0? Well, that of course gives you x equals 0. On the other side over here, we sort of have a choice to make here. We can say that there's no real solutions. If you want to get fancy, you can certainly introduce complex numbers, because you're going to get x squared is negative 4. There's no real number squared that gives you negative 4. If you know a little bit about complex numbers, again, you don't have to be too fancy for us in this case, you're going to get, take a square root of both sides, you get plus or minuse 2i. I'll leave that as sort of good to know, but you don't absolutely have to know it for the purposes of this course. But complex numbers are out there, and well, I guess you shouldn't be scared when they do pop up. Now let's look at the function x cubed minus x squared minus 9x plus 9. And let's set it equal to 0 and see if we can solve for x to solve this polynomial equation. One thing you might look at is in all four terms, they don't really have anything in common. There's only x's in the first three, there's 9 in the second two. But that leads us to another sort of approach to solving these things. Instead of treating all four pieces as one, let's look at just the first two together and perhaps the second two together. And say, well, they have things in common, so let's try to play around and factor out things of just the first two. When you look at this is called factor by grouping. You're almost like drawing like parentheses around each of the pieces. Here I got to be careful with that negative sign. But in the first two I can certainly factor out an x squared because both terms have an x squared. I'm left with x minus 1. In the second part I can factor out a minus 9. I can factor out a minus 9. And when I do that I get x minus 1. Stare at that for a second. Just convince yourself with that minus sign that if I bring the minus 9 back in, I do in fact get negative 9x plus 9. And now all of a sudden you say, well, wait a minute. Now they do actually have something in common. There's an x minus 1 that's common to both terms. So I can factor out the x minus 1, and I'm left with x squared minus 9. So this factor by grouping technique is really nice, especially if you have a polynomial with many terms. X minus 1 is already simplified, and x squared minus 9, well, that's x minus 3. X plus 3, and that's going to give me all of it equal to 0. So you set each piece equal to 0, you get x minus 1 is 0, x minus 3 is 0, x plus 3 is 0, right? If it's going to be 0, one of these things has to be 0. So the roots of this equation become, the solutions to this equation are 1, 3, and then minus 3. So we have 3 solutions to this equation. And that's okay. You can certainly have more than one solution. All right, so practice solving your polynomial equations. Look for these factoring techniques. Look for ways to rewrite or change the expression to a more simpler form to work with. Rationalize your denominators as needed. Have some fun doing these. Again, these are really good to really solidify your algebraic skills working with higher degree polynomials. Great job on this video, and we'll see you next time. Hi everyone, welcome to our lecture on graphing polynomials. So friendly reminder, we've seen constant linear quadratic functions. These are polynomials of 0 degree, degree 1, and degree 2 respectively. And these are all functions that arise in applications in science, economics, and other courses in math. And then what's nice about these polynomials is that they're often used to approximate other more complicated functions. This is due in part to the fact that the values of polynomial functions can be computed using only the operations of addition, subtraction, and multiplication. So their evaluation can be done very quickly by a computer. So what we want to do now is look to systematically sketch graphs of polynomial functions. And I know what you're thinking. You're thinking, well, why can't I just graph these functions on a calculator? And you can, but they don't give you the actual values that you might need for, say, the intercepts or the zeros of the graph or where the maximum or the minimum values may lie. So we want a systematic approach to graphing these things. I also compare it to when you're fluent in a language, you don't go look up every single word that you need. You can understand the context and meaning, and that's what we're after, a little bit of fluency with these polynomials, where if I present a polynomial to you, you can have a basic shape, a general idea of where the intercepts lie, and what the graph looks like without having to run to a calculator to go graph this thing every time. So let's start off with an example. Let's start off with the function f of x equals minus 3, x minus 2 cubed plus 1. All right, so what is happening with this function? So this is a manipulation of the parent graph, which is f of x equals, at its heart, like what kind of polynomial is this? Something cubed, x cubed. Now this graph we should know and love. This is the disco function. This goes from low to high, right through the origin, nice symmetry around the origin. And so the question is, what's happening to this graph? So let's build this up step by step using all the pieces that we see. The first thing that we can do to this graph is shift it. Let's do x minus 2 quantity cubed. Okay, so now what happens to this graph? How does it work? Well, let's see. So minus 2 is a shift to the right 2. Everything else stays the same. So the actual look and feel of this graph stays the same. We're just looking for rough sketches at this point. If I wanted actual values, I'll solve it algebraically. So think of this here as like, what would this be? Could you picture this graph in your head? Could you look at this and sort of build from all these ingredients the actual final product? So we've just shifted the graph to the right by 2. Now what's happening here? I have a negative 3 in front. So let's look at f of x equals minus 3, x minus 2 cubed. What does a minus do, and then what does a 3 do? So I want to take these almost separately. A minus will flip the graph. So everything positive turns negative, and everything that's negative turns positive. We still don't change the fact that this graph goes right through the point at 2. There's no change there. So some way, somehow, you want this thing to flip where the negative part flips up above the x-axis to become positive, and then positive part flips down below to become negative. The -3 is going to make this thing a little skinnier. I didn't do a great job drawing the graph a little skinnier in my sketch, but you can imagine it's going to have a tighter, quicker slope that goes up and down. The last part is the +1. Do you remember what a +1 does to any graph? It's also a shift. So I take -3, parentheses x minus 2 quantity cubed plus 1. This is a shift, however it is vertically, so we're going to push the whole graph up by 1. So I take my anchor point right here at 2, 0, and I move it up 1, so now I'm at the point 2, 1, and I still have the same exact graph, and it still has this very nice, I don't know, I call it the disco graph, because if you move your hand in this shape, you're going to start dancing like you're dancing to disco. But at this general shape. Now, if I wanted to fine-tune the graph and find the actual intercepts, I could start doing things algebraic, but for our general sketch of the graph, this is good enough. If you look at this graph, you should be able to sort of build these pieces, almost like a puzzle, start putting the pieces together, and land at your final product to have a general shape of this graph. If I wanted the actual intercepts or wanted some other values, I'd have to solve it algebraically, but for this example, this sketch is good enough. Let's do another sketch. Let's look and try to sketch the graph of the function -2, parentheses x minus 1, raised to the 4th. Before I had a degree 3, or cubic function. Now I have a degree 4, or quadratic function. So the first step is to look at the parent graph. What is the base thing that's happening? Let's look at f of x equals x to the 4th. What does this graph look like? This graph is sort of a fat parabola. It behaves like x squared a little bit. Everything's positive, but you have some sort of parabola being shaped. Now we can build this up. There's no wrong way to build it up. Let's do this as 2x to the 4th. So remember, when I have a 2 up here, I'm making all the numbers go to infinity faster, so you're making it just even a little skinnier. So you have a little bit of a skinnier parabola than what you had before. Put the negative in front. Negative flips everything about to the x-axis. Everything that was positive turns negative. Everything that was negative turns positive. The origin doesn't change. If you negate 0, you still get 0. So we now have a parabola that opens downward. Finally, last but not least, let's shift the graph. So let's build -2, parentheses x minus 1 to the 4th. This is the last graph, but shifted. Now there's a minus sign, so be careful. It's counterintuitive. You shift it to the right by 1 unit. So instead of having my vertex at the origin, I'll move it over by 1, and I'll draw my parabola facing downward. Again, if I wanted the exact values of the y-intercept, I'd have to do a little bit of algebra to figure that out, but as a general sketch, this is good enough. So one of the most important features of the graph of polynomial is the behavior of the y values as x gets really large, heads off to infinity, or x gets really small. We denote these in our pictures by these arrows, but we're going to start calling these things end behavior. So the question is, what is the function doing as x gets really large? As I move my pen along the x-axis in the positive direction, what does the function doing? Does it want to go to negative infinity like this example does here? Maybe it wants to go to positive infinity like other functions, or maybe it wants to have a horizontal asymptote or do something completely different. Who knows? So we're going to look at the end behavior as x goes to infinity, and of course on the other side of the world, as x gets really small, what does the function want to do? What is the end behavior of the function as x goes to negative infinity? And it turns out, whenever you have a polynomial, the leading term, when you write this thing out in expanded form, for us if we wrote this out, we'd have -2x to the 4th plus a bunch of other terms. The leading term is always going to determine the behavior of the function at infinity and negative infinity for a polynomial. There's two things we have to look at. We look at the leading coefficient. Is it positive or negative? We're going to look at the highest exponent, or the degree, and we're going to ask, is it even or odd? Now there are 4 possible combinations, positive, negative, even, or odd, but each one of those will completely determine how the function behaves. This will help with our sketching or understanding of the graph, especially when we start modeling things and look into the future. In this particular example, when I'm even, any number is going to be positive. No matter what I plug into the 4th, I'm going to get some positive number, and then the negative number in front will always negate it. So we're going to have a negative times a positive, which is why my function in this example had to end up with both arrows pointing down, the function approaching negative infinity in the y direction. Let's use end behavior to sketch a graph of the function f of x equals x cubed minus 3x squared plus 2x. This is a nice cubic polynomial. In particular, the leading coefficient is 1, which of course is positive, and the degree is 3, which is odd. So let's think what's going to happen to this function at the end behavior, if I plug in like a large number, think of a million or a billion or whatever. If I plug in a large number and cube it, large positive number cubed, so take your million, gajillion, billion, and cube it, it's like the number times itself, positive 3 times. That's going to stay positive. And the leading coefficient in front, which is also positive, keeps the number positive. So whatever this function is doing, it has to be increasing. It has to be getting larger and larger and larger. So I know that this function is going to approach positive infinity. So the arrow is going to point up as I draw it on the right side of the graph. Now, what if x is very negative? Negative 100, negative 1,000, negative a million. Take a negative number and cube it. 3 numbers make a negative. And then the leading coefficient in front, which is a 1, keeps it negative. So positive times negative will be negative. So because I start with a negative number, multiply it by itself 3 times, I stay negative, and I always have to consider the leading coefficient, which also stays negative. So this function is going to approach negative infinity. So I'm starting to get the end behavior of the graph, and the question is what happens in the middle? Now I have to start looking at the function and start, thinking of some other things. For this particular function, if we want to know the intercepts, maybe it's easy to factor. Let's start doing some algebra and actually work through it. If you notice, there's an x in each term, so there's nothing stopping me from writing this as x parentheses, x squared minus 3x plus 2. And of course, this quadratic factors nicely as x, x minus 1, x minus 2. So I know I'm going to have to go through the intercepts at 0, at positive 1, and at positive 2. Okay, so how is this function, how is it going to have to behave in this particular case? Let me redraw these parts of the function a little better to sort of make sure I hit my marks here. So I have to go through 0, and I know I have to approach negative. So that's going to force me to sort of draw the curve down. But then I also have to go through 1, and I also have to go through 2. So I'm going to have this curving feature of the function with a sort of max and a min, a hill and a valley, as I approach 1. But right away, because I know the intercepts just by factoring, and I know the leading terms in the degree, I know the end behavior, how this function wants to behave, I can completely draw the graph. One of the key features that I use in this graph were where the graph crosses the x-axis. These are the x-intercepts. Sometimes, though, they're also called the zeros of the function, and these are the values c such that p of c is equal to 0. So there are some functions that have more than 1. This example here has 3. There's some functions that have none. Think of the function f of x equals 7. There's no value that outputs 0. So the zeros, also known as the x-intercept, just depends on what context you're talking about them, but these are the intercepts of the graph where the graph crosses the x-axis. If you know these points, then it helps to sketch the graph of the curve. Another name that you might have heard of these in addition to x-axis, sometimes these are called the roots of the function. 3 words that sort of mean the same thing. Let's do another example. How about f of x equals x to the 4th minus 6x cubed plus 8x squared. Let's graph this degree 4 polynomial, this quartic polynomial. I'm going to look at this, and again, it has some nice things that are common to all of them. There's x squared in all of them, so right away I'm going to factor this and write it as x squared minus 6x plus 8. Then I look at this x squared minus 6x and realize, well, that can be factored as well. So let's factor that as x minus 2, parentheses, x minus 4. So right away, if I set this to 0, I already know the roots or the zeros. So the zeros of this function are at x equals 0, corresponding to the x squared. I have x equals positive 2 and x equals positive 4. So whatever this graph is doing, I know I have to go right through the origin, right through the point at 2, and right through the point at 4. Try to draw this graph a little bigger. I have a degree 4, so as I plug in larger and larger numbers, what's going to happen? As x goes to infinity, the function is wanting to go to positive infinity as well. So plug in a large number and then raise it to the 4th power. 4 positives is positive. Notice, by the way, I'm also looking at the leading coefficient. So the leading coefficient is 1. I don't care about the number 1. I care more that it's positive, so that it's not going to change the sign of my degree 4 equation, of my degree 4 polynomial. So as x gets large, the function is going to get large as well, which means that this graph has to be coming from the top down as I look from right to left. And as x goes to negative infinity, what's going on the left side of the world? We'll take a negative number and raise it to the 4th power. 4 negatives also make a positive. So this function has to be coming also from the top down as I move from left to right. Now I'm going to show you another trick that you can use, another property of polynomials that you can use when graphing. In particular, the multiplicity of a 0 is the number of times that the root appears. So let's write this down as a definition. The multiplicity of a 0 or root is the number of times the root appears. Now, I have to be careful here because really, and I was a little lazy when I wrote my zeros, this is of course x times x. So really I should have 2 zeros in my list. I didn't write it because it's redundant, but I know that it appears. You can also think of it as the exponent when the function is factored completely. So there's 2 zeros here. So for this particular case, we'd say this is a 0 of multiplicity 2. All the other roots, they only appear once, and again that's coming from the fact that their exponents are 1 on their terms when factored. So we'd say here that their multiplicity is both 1. And it turns out that if the multiplicity is even, then the function is going to bounce off the x-axis. What do I mean by bounce off the x-axis? So if I go back to my graph, I know from the end behavior I'm coming down from high to low, and I'm headed towards this target at the origin. But because the multiplicity at 0 is 2, which is an even number, I don't go through the origin. I'm not going to start heading down. I'm going to bounce off the axis. This is true if your multiplicity is even. And of course, if the multiplicity is odd, then the function passes through the root. So this is interesting because now I can completely determine. I know that I have to go to 2, but I'm also going to go through it. And now I also have to go to 4, but I'm going to go through it. And then I head off to positive infinity. And you can tell that this graph is going to have this sort of lopsided W effect. But I have a nice sort of bouncing graph at 0, like sort of hit the origin and bounce right back up. And then I'm going to go through 2 and 4, but I have to pass through them. You can almost think of it like a pass, like you have to go through these because they have multiplicity 1. So factoring a polynomial is extremely important and tells you how these polynomials behave at their origin. Usually if you put the polynomial zeros and their multiplicity and the end behavior looking at coefficients and degree together, you can graph anything you want. You can do sketches of it. Let's do another example. What if I took f of x equals x cubed minus x squared minus 9x plus 9. Okay, so I have, let's go to get all our information together. I have degree 3. I have a leading coefficient of 1, which is positive. So as I already start to think about the graph, as x gets positive, right, what does this tell me? As x gets really large, well, if I plug in a large number 3 times, 1,000,000 cubed is going to be some positive number. So the function, of course, is going to want to go to positive infinity, and it's going to stay positive because that leading coefficient is 1. As x goes to negative infinity, so take a negative number and cube it, where's the function want to go? The function is going to want to get negative. And the leading coefficient is going to keep it negative. 1 times a negative number is going to stay negative. So right away, I know this function is heading down and heading up. Now let's see if we can find the zeros and play around with this graph a little bit. There's no particular term that all of them have in common, but we've seen this before. If you factor out x squared from the first 2 terms, you get x minus 1. And if you factor out a minus 9 from the last 2 terms, you also get x minus 1. So friendly reminder, this is called factor by grouping. And once you have this, you can write this as x minus 1, parentheses x squared minus 9. And then that x squared minus 9 factors again as x minus 3, x plus 3. So right away I have my zeros at x equals 1, x equals 3, and x equals minus 3. And they all have multiplicity 1. I don't care the fact that it's 1, more importantly is that it's odd, so I know that the function has to pass through all these points. So if I put minus 3, and I put 1, and I put positive 3 on the map, I know I'm going right through the origin. Now what I don't know is if I'm coming down on the diagonal from left to right, or going up right to left, but this is where I use the end behavior of the function. If I know the function's starting low and headed towards minus 3, and I'm going to go through it, I have to be coming from sort of low to high. Then I have to sort of curve to hit 1, and I'm going right through. I have to go right through 1, and then last but not least, I got to curve again to sort of start heading up to positive infinity in the y direction, and I have this nice cubic polynomial. Again, look at this graph that I've done without doing any work, without grabbing a calculator, and then go graph this function. Look at Desmos, look at a calculator, and tell me how close we actually are. What's really neat about polynomials is that with minimal information, you can get a lot of information about the shape of their graph. If I tell you the end behavior, which is equivalent to saying what's the degree and the leading coefficient, if I can factor the polynomial and look at its roots and tell you their multiplicities, I can tell you how this function is going to behave. And I'm also interested in these max and min values, these hills and these valleys that appear. And those are going to become important pieces of this function. So right now we're interested in general shape and intercepts, but just for you know, the next thing you're after is, I wonder how high this mountain gets, and I wonder how low this valley gets. For those, we're going to need tools of precalculus or calculus to get. For simple functions like a quadratic, we can find the vertices, we have special formulas, but as the polynomials get more difficult, that gets harder to do, and that's a big part of what calculus does. Just so you know that we need more tools to analyze these functions further. Again, this is just the first step. I really do hope you keep going to study functions. It's really amazing how much information you can get and how applicable these things are. All right, work through the sample problems, practice with your quiz. Great job in this video, and we'll see you next time. Hi everyone, and welcome to our lecture on square roots. So we've seen square roots before, I think the first time when we were studying area, back in the day when we were studying geometry. So for example, to find the area of a square, I think we all know that the formula for the area of a square is area equals side squared. So we'll let S denote the length of our side. Here's my beautiful square with all sides equal and of course right angles everywhere. So A will be the total area and S is the length of a side of the square. So now imagine if the side of the square is say 3 centimeters long. Then the area of a square is 9 centimeters. So the calculation is not hard. We take 3 squared and we get 9. Of course we use our units and we get 9 square centimeters or 9 centimeters squared. So conversely, you can use the formula to find the length S of a side of a square if we're given its area. So if the area of a square is 25 centimeters squared, then the side squared is 25. And of course, if we solve for S, you could argue, well, S is either 5 or -5. Now, each of these solutions technically is a square root of 25. However, but because lengths are always non-negative and we're measuring a distance, 5 is the only possible solution that we're going to care about. It'd be a little weird to come back and say the length is -5 centimeters. And this is going to introduce our first definition. We're going to call the positive solution of the square root our principal square root. So if A is any non-negative number, so it's allowed to be greater than or equal to 0, the principal square root of A, denoted by the square root sign of A, is the non-negative number B such that B squared equals A. When we talk about square roots, when we use this symbol, this square root symbol here, we always want something that's non-negative. So for example, why do I keep saying non-negative? Why can't I just say positive? Well, as some examples that we saw, principal square root, or just the square root of 25, this is going to be +5. It's important to realize that if I use this symbol, I really do want the positive number. Think of it from a geometric standpoint. I only want the positive value. If I said, what is the square root of 16? We do not say positive or negative, we just say +4. Now here's one more for you. What do you think the square root of 0 is? Can you think of a non-negative number B such that B squared is 0? What number squared is equal to 0? Well, of course, that's equal to 0. So I'm restricting the numbers that I put under the square root to be non-negative. You can have positive, you can have 0. You just can't have negative numbers underneath. That leads you into the world of imaginary or complex numbers. We'll deal with that another time. Not every square root that you put under this symbol has to be a nice square root that we know. There's nothing wrong with talking about the square root of 2. This is the principal square root of 2. Now, this is not a nice number that we probably have memorized, but it is a number if you throw it in the calculator, you can certainly get that this is approximately 1.41421, and it goes on forever and ever and ever. So some of these are a little nicer than others, but they're all just perfectly fine real numbers, and these square roots are the subject of this lecture and this section in the course. Let's just do a couple of examples. What is the square root of 144? You can pause the video, see if you know this. All right, you all know this. Hopefully this is just 12. We've had this drilled into us since when we were a child. Let's do a second version of this. If S squared is equal to 144, then solve for S. Ready? In this case, since I'm going to take the square root of both sides, I want all solutions to this. I'm going to write that S is plus or minus 12. Now notice it wasn't asked of me with the square root symbol, so I'm allowed to get back both the positive and negative answer. To see this a different way, if I start with S squared equals 144, I can algebraically subtract 144 from both sides. Hopefully you agree, if I subtract 144 from both sides, I have S squared minus 144 is 0. Then I can factor this quadratic. I have S minus 12, parentheses, S plus 12. Stare at that for a second, foil this back together, convince yourself that this is true. Now I have two things multiplied that give me 0. So of course I have S minus 12 is 0, and S plus 12 is 0. I write both of them equal to 0, which gives, of course, the solutions S is positive 12 or S equals negative 12. A more concise way of writing that, of course, is S is plus or minus 12. The algebraic way to factor is obviously a little longer, but it really shows you what's going on. It's good to see it to understand what's happening. So if you have a quadratic, you should expect two solutions back, and there's the plus or minus. If you start with the square root, They only want the principal one, then you return just the positive number, the positive principal square root. One more, just to practice with fractions as well. If I said to you, what is the square root of 4 over 9? What number squared gives me 4/9? Again, this is just the positive number because I'm introducing the root symbol. That's what that symbol means. This would just be 2/3. Now, if I said to you, if x squared is equal to 4/9, solve for x, let's just do the shortcut. Let's just take the square root of both sides. I'll say x equals plus or minus the square root of 4/9. Notice when I introduce the square root symbol, I must put plus or minus. This is often a source of confusion for a lot of students. And of course now, x equals plus or minus 2/9. You can always tell how many answers you're going to get back based on the kind of question you're starting with. If the square root doesn't appear in the question, they're just looking for the quadratic solutions, the two solutions. If the square root does appear in the questions, like these first examples here, then you're looking for just the principal value of the square root, the non-negative number. So now let's talk about other roots. So we've seen that the positive solution to s squared equals 25 is denoted by square root of 25. Similarly, the positive solutions to something like s to the fourth equals 25 is denoted as the fourth root of 25. In general, if n is even, the positive solution to x to the n is some number, let's say 25 as well, is denoted as the nth root of 25. That's how you read this. You read this as the nth root when you're talking about roots in general. The number n is called the index, and just note when you write square roots, n equals 2 is implied. So when there's no number that appears, it's assumed to be a square root. It is not written. It's assumed that the index is 2. Let's see a simple example of this. If I said to you, find x such that x cubed is equal to -8, what I'm looking for is the cubed root of -8. If I want the positive solution, so what number times itself 3 times is -8? What times what times what is -8? So in general, we'd say that the cube root of -8 is in fact -2. So in general, the odd root of a negative number is a negative number. This is okay to have an answer here be a negative number. Notice I'm no longer restricting myself to the principal square root because I've left the world of square roots and now we're talking about cube roots. Another example, what would the fourth root of 16 be? Again, without a calculator, I have to ask you nice numbers, but this is just to understand the symbols and the notation. What times what times what times what is 16? What number raised to the fourth is 16? Just remember, behind these roots, I'm asking you to solve the equation, what number raised to the fourth is 16? Can you figure it out? Well, of course, in this case, this is equal to 2. Positive 2. One more, just to play around with it. What if I said -16? What's the fourth root of -16? To understand what this expression is asking, write it as an equation and say what number raised to the fourth is -16. In this particular case, I can't take a real number, raise it to itself 4 times, of course, because if I have positive, I'm going to get positive. If I have negative, 4 negative is going to be positive. I'm never going to get a number when raised to the fourth is going to give me negative. Never. So in this particular case, we'd say no real solutions. This will have complex solutions, but we'll save that for another time. If we're restricted to real numbers, which we usually are, we'll say no real solutions. Some square roots are rational numbers. We saw before that the square root of 16 is 4. It's very nice. The square root of 4, of course, is 2. Maybe you can even talk about the square root of 1 being 1. Some square roots are just nice, rational numbers. So friendly reminder, a rational number is one that I can write as a ratio of integers, write as a fraction. But some other square roots are just not nice numbers that you're not going to solve these. You're going to need a calculator to do these. For example, the square root of 2 we saw, this is a nice irrational number. Now this is a big claim that I make, that there's no fraction. I can't find a fraction a over b such that if I square it is equal to 2. Appreciate this for a minute. You're sort of taking this on faith a little bit, but I'd like to walk through the process. It's a nice example of sort of logical deduction or indirect reasoning. Talk about why this doesn't exist. This is a classic example. So once again, what am I going to show here? I'm going to show that root 2 is irrational and sort of ask the question like, why is it irrational? And I'm going to assume that I can write it as a fraction a over b squared. And just remember what I'm allowed to do. A over b, they're integers. Of course, b is not 0. Don't want to divide by 0. So I just have some integers, and I'm going to assume that the fraction a over b is reduced. That's a fancy way to say no common terms. So I don't want it to be like 2/4. I'm going to think of it as 1/2. They have no common factor. All right, so let's start with my equation here. A over b squared equals 2. And what I'm going to do is I'm going to bring that exponent into both the numerator and the denominator. That's all fine. And I'll move things around. And I'll say a squared is 2b squared. If a squared is 2b squared, then that means that a squared is 2 times some number. So of course a squared is even. And you can think about this, if a squared is even, if some number squared is even, then a itself has to be even. The only way to get an even number in its square, like if I start with 4, I have to start with 2. You can't take an odd number, like 3, 5, or 7, square it, you always get an odd number back. You can think about why that's true, but that turns out to be true. So a is in particular even, and from that I'm going to write a as 2 times some other number. Let's just call it 2 times t. And we'll put it back into our equation. So we have 2t, where this is the expression for a as an even number squared, is 2b squared. Let's bring the 2 in, and I get 4t squared is 2b squared. Divide both sides by 2, and I get 2t squared equals b squared. And all of a sudden from here, I could see that b squared is equal to 2 times some number. So guess what? B squared is also even. And for the same reasoning as above, if b squared is even, then b is also even. Now I claim we have a problem, because if a is even, and b is even, and I'm thinking of a fraction a over b, and remember I said from the very beginning they have no common terms, I've just contradicted myself. I've arrived at a contradiction. So when we say this, we'd say a over b is not reduced. You have an even number over an even number, like 6 over 4, you can certainly reduce it. And this is a flaw in my original assumption that there was some fraction squared that equaled 2. In particular, this means that the square root of 2 is not rational. Cannot write square root of 2 as a over b. You can use a similar argument to show that root 3 is irrational, or in general, root n is irrational, where n is some whole number, but just not the square of another whole number. This is a nice little proof, and I wanted to show you guys one of the arguments that you can do to prove things and walk through some of the reasoning behind why square roots are not rational. It turns out you can write the square root of x as equal to x to the 1/2. Let's think about why this is true. If I take both of these numbers and square them, so if we square both sides, I get x has to be equal to x to the 1/2 squared. But of course when I have an exponent to an exponent, this just turns out to be x to the 1, which is in fact x. So we're going to write sometimes our roots with rational exponents. The square root would be written as x to the 1/2. The cube root of x will be written as x to the 1/3. The fourth root of x will be written as x to the 1/4, and so on. In general, the nth root of x is written as x to the 1 over n. These roots have nice properties because they're related to the properties of exponents. So for example, if I have x to the y to the 1 over n, I can bring in the exponent to both pieces. So I have x to the 1 over n times y to the 1 over n. But if I convert all of that to square roots, or nth roots in this case, I know that the nth root of xy is going to be equal to the nth root of x times the nth root of y. So roots distribute over multiplication. For all the same reasons, if I had a fraction x over y to the 1 over n, I can bring this in as x to the 1 over n to the y to the 1 over n. But just using similar but different notation, this says that if I have the nth root of any fraction, I can bring the nth root in. This is true for squares as well, which is the most common case that we'll probably work with. But you can bring the nth root in over a fraction or a product. One more property that we're going to use comes from the algebraic fact that if I have an exponent to an exponent, I get to multiply the exponents together. In particular, if I have one of them be a nth root, what if I had x to the 1 over n raised to the s? Well, this becomes x to the n over s. So therefore, if I replace x to the 1 over n with its nth root, something like this, I can bring the exponent inside right on the s. This is going to allow us to simplify and write our exponents using roots. Whenever you want to simplify roots, maybe it's easier just to convert it to exponents and work it out. But the big three properties that I want you to come away with is that roots distribute over multiplication, roots distribute over fractions, and if I have powers of an nth root, I can move that power right inside. Let's do some examples for a second. So 16 to the 1/4, if I see this as a fraction, again, let's try to do these without the calculator. This would be the 4th root of 16. This we know what number to itself 4 times is equal to 16. Well, this is of course 2. Let's do another one. What if I had 16 to to the 5/4. Now, it's more complicated, but I want you to see this as 16 to the 1/4 raised to the 5. So break up that fraction, focus on the denominator, which is really acting as a fourth root, and then raise this to the 5. And all of a sudden, the fourth root of 16, well, that we know, that's just 2, and we're raising 2 to the 5. Now, that's much simpler. You can check that is, in fact, 32. So 16 raised to the 5/4 is just 32. Let's do another one. How about 125 raised to the negative 4/3? How would you solve this? How would you think about this without using a calculator? Now that negative, don't let it scare you. Remember, one way to think about this is throw this in the denominator and answer the same question now with a positive number, but just work inside the denominator. Let's once again take the same approach as before. We'll just keep working downstairs. 125 to the 1/3 raised to the 4 is, of course, the cubed root of 125 raised to the 4th. Again, all still in the denominator. What times what times what is 125? What number raised to itself? What number times itself 3 times? Well, that's just 5. So really this question is asking, what is 1 over 5 to the 4th? And you can check. That's 625. So our final answer is 1 over 625. Again, we're in the denominator because the original exponent was, in fact, negative. Let's do one more, see if I can trick you here. What is negative 16 raised to the 1/4? Pause the video for a second, see if you can solve this. Remember, this is asking for what number raised to the 4th is negative 16. Well, let's just say there's no real solutions. So it is okay when working with exponents, when working with roots, to come back and say, sorry, I can't get you an answer. There's no real solutions here. If you want to get fancy, you can start going to the world of complex numbers, but we'll save that for another day. Let's do one more. What if I had 2 root 3 equals root x? Solve for x. Again, pause the video, see if you can solve it. Let's think about this for a second. How would I solve for x? X is trapped under a square root, so why don't I square both sides to get rid of it? So let's see. So we have square both sides. We get 2 root 3 squared is equal to square root of x squared. That's, of course, just x. Now let's bring the 2 in to both pieces. We get 4 times 3. Root 3 times root 3 is just 3, and that's going to equal x. So x, of course, is equal to 12. Let's go back and actually check that just to see why that's in fact true. If I look at the square root of 12, by the rules of exponents, I can think of this as the square root of 4 times 3, because 4 splits as 4 times 3, but now I can break this up as the square root of 4 times the square root of 3. Remember, roots split over multiplication. Square root of 4, well, hey, that's just 2, and I'm left with, as promised, 2 root 3, the thing I started off with. So you can use these to solve for numbers, you can use these to solve for equations. We're going to see them all over the place. So practice these, and again, try not to rush over to your calculator. Try to understand how the exponent is manipulating the root or vice versa, and how to solve and understand what these exponents are actually doing. All right, great job on this video. We'll see you next time. All right, hi everyone, and welcome to our lecture on the Pythagorean theorem. My guess is this is not the first time you've heard of this theorem, so I'd like to go into not just the basics, but a little bit more about why it's true and some of the more interesting applications. But maybe it's been a while, so let's just do a little friendly reminder. Pythagorean theorem is a statement about a right triangle. In particular, with a right triangle, you have to have a right angle. Friendly reminder, right angle means that you have an angle of 90 degrees or pi over 2 radians. Either one is fine, of course, but you must have this. So you can't apply the Pythagorean theorem to every single triangle. It is only true for right triangles. The side opposite the right angle has a big, long, fancy name. It's called the hypotenuse. The two other sides are just called legs. And these are normally written as A, B, and C, but of course you can use any variables you want. And maybe this isn't surprising, but the Pythagorean theorem states that A squared plus B squared equals C squared. In terms of the descriptions, the leg squared plus the length of the other leg squared is equal to the square of the hypotenuse. Now, a lot of people know the statement of this theorem, but let's see who knows why it's true. If someone came up to you and said, what's the Pythagorean theorem? My guess is you could tell them what this is. But if someone said to you, why is this true? Would you be able to answer them? So let's look at why this is true. Now, there are websites devoted to proofs of the Pythagorean theorem, and I think there are at least 320 different flavors of proofs. I'm going to show you one of them. If you're interested in the many different techniques to prove this amazing theorem, please go and search for it on your own. The one thing I like is I just want to start with a square inside of a square. So we'll draw a big square. All right, my picture is not going to be perfect in terms of drawing a square inside a square, So please do your best to imagine that we have a square inside of a square, and we're going to label the sides of the inner square that I colored green here as C. Now remember, square has all four sides equal, so all four of these sides are equal to C, and we're going to label the parts where the square breaks up the outer blue square as A and B, and A and B, and A and B. So because it's a square, it breaks it up in a symmetric pattern, and we have A and B. So if you want to be really fancy, draw this the best you can, draw a square inside of a square. Okay, so they're both squares. Now we're going to find the area of the blue square two different ways. The first way is using the good old formula for area of a square. It's side squared. So the side squared is A plus B, the length of the segment of A, plus the length of the segment of B, and then of course square that. So we have A plus B quantity squared. You can also think about it as putting together all the pieces that make up this inner square, like a tiling on a floor. So we have the green square in the middle, so that's just area is C squared. This is the inner green square. And then we have these four triangles that go around it, 1, 2, 3, and 4, but they're the same. Why are they the same? Well, they have the same base A and B, so their area would be, now there's four of them, so let's do 4 times 1/2, base times the height, whatever triangle you look at, is AB. So stare at this for a second, because this is key. We're looking at the large thing as one single object, this big blue square with a side A plus B, plus the green tile and then four triangles around. So 4 times 1/2 AB, 1/2 base times height. So this is the area of the triangle, and of course there's 4 of them. Convincing yourself that these two things have to be true is key to understanding this proof of the Pythagorean theorem, because now we simplify. What is A plus B quantity squared? Let's FOIL that out. We get A squared plus 2AB plus B squared. On the right side, you get C squared plus 4 times 1/2, well that's just 2AB. Now subtract the 2AB from both sides, and you get, of course, A squared plus B squared is equal to C squared. This is a nice, really pretty, simple proof of the Pythagorean theorem. These are one of your life proofs. These are things like the square root of 2 being irrational, is things that you should, next time you're on a beach, write this in the sand and convince yourself that it's true. This is one of the great truths of humanity. Understand why this is true on a flat surface. Why A squared plus B squared must equal C squared. All right, let's do some examples. We'll do one easy, one medium, and one hard here. So what kind of questions could you see with the Pythagorean theorem? I think the classic sort of easy example is given any two sides of a right triangle, find the missing third side. So let's call one leg x, one leg 5, and the hypotenuse 7, and of course solve for x. If you want, pause the video quickly, just make sure you can do these basic kind of examples. Because it is a right triangle, we're going to set 7 squared equal to x squared plus 5 squared. Cleaning that up, we get 49 is x squared plus 25. Subtract 25 from both sides, and you get 24 equals x squared. Now remember, here's where we're going to use our roots. X is equal to the square root of 24. We don't put plus or minus here because x represents a distance. If this didn't represent a distance, and I just said find all solutions for x, sure, we put a plus or minus. But because it actually has a meaning, a geometric interpretation, we're only going to use the plus. Square root of 24 is perfectly fine. If you want to clean this up a little bit, you can. This is, of course, 4 times 6, which would be the square root of 4 times the square root of 6, which is 2 root 6. If you wanted decimals, it's about 4.9. One more sort of straightforward example. If I give you a right triangle with a side of 18 and another leg of 24, and I said, what's the hypotenuse C? Can you solve for C? Let's use the Pythagorean theorem, of course. So we have that C squared has to equal 18 squared plus 24 squared. Clean that up a little bit. 18 squared, of course, is 324 plus 576. That gives us that C squared is equal to 900. So C would be equal to the square root, the positive square root of 900, which is 30. All right, pretty straightforward applications. Let's see another one. If we wanted to move into the world of 3D objects, usually after you talk about triangles, you start talking about pyramids. Let's use a very famous pyramid, the Pyramid of Khafra. Never been to Egypt, never been to the pyramids, on the wish list. Maybe you've been, maybe you've seen this. But you can imagine one of the things they like to know are the dimensions of these pyramids. So we're going to find the height if the base has a length of 215 meters, so the pyramids have a square base, so 215 meters, and this is also 215. So how high are these pyramids? And the slant height is 173 meters. So friendly reminder, what is the slant height of a pyramid? The slant height measures from the top to the bottom, but along the sides. And you can move this along any side you want. Particularly, you can come right down the middle. So this is 173. So you can imagine they send up someone who's good at climbing to the top. They run a measure, string down or something. They measure the slant height at 173. You can measure the base. But the question is, how do I get the height, especially if I can't go inside and get right to the center? Well, you can use Pythagorean theorem. But now you have to be careful, and this is a little challenging. You might want to think about this one for a second. Pause the video. How can you get the height? There's no right triangle that I'm looking at. So what's missing is, of course, the height. And if you draw the height, you actually do get a right triangle, one that goes right into the middle of the pyramid. Let me redraw this picture a little better, if I can. You have your square base, you have your pyramid, and if you want to know the height, and you know the slant height, there is a right triangle that appears. Put a dot right in the center and drop a line down for the height. The right triangle that appears is one that's not obvious in the picture of the actual pyramid, but you use the slant height, which becomes the hypotenuse at 173, and you use the base of 215. Now be careful here. The base of 215 is the entire length. So half of this triangle, the one that we want, is 215 divided by 2. That will get me my height. I'll call it h. And so the equation that I get is 173 squared is equal to h squared plus 215 over 2 squared. It's important here, the setup. The right triangle is not obvious, and then using half and only half of the length of the base is also a key step. And so h squared is equal to 173 squared minus 215 over 2 quantity squared. Grab the calculator to get 18,372.75. Now remember, that's h squared. You don't want the square of the height, you want the actual height. So take the square root of that answer to get about 135.5. Now because this is a word problem, units matter. When students leave off the units in problems, I usually write cats per donut, just to sort of stress that the units do matter. Here, our units are meters. So we're going to say 135.5 meters. And if you want to go look up the actual height of the pyramid, this is pretty darn close. Now in math, there are a couple special right triangles that come up just due to the symmetry of the objects of which they are born. Let's look at the first one. I want you to imagine a square. Wait a minute, you lost me. No, a square. Take a square. A square is a nice object. It's got beautiful symmetry. All four sides are congruent. All four right angles are at 90 degrees. And I want to take this beautiful thing and I want you to cut it in half. Cut it in half. When you cut it in half, you get a nice right triangle that forms. Nice right triangle that forms. And in particular, its two legs are congruent. When you have a triangle with two legs that are congruent, it has a fancy name. Do you remember this name? This is called an isosceles triangle. And so whenever you hear of an isosceles triangle, just realize that it's half the square. And because it's got half the square, it inherits a lot of symmetry. So let's give these things a side. Let's call these sides S for side. But it's not just any isosceles, it's an isosceles right triangle. So the Pythagorean theorem would kick in and say that s squared plus s squared would equal c squared. Clean that up a little bit, some things start to happen. You get 2s squared equals c squared. And you can solve for c. Let's switch things around a little bit and take a square root. You get 2s squared. Now break off the square root of 2 and take the square root of s squared. In this case, you get 2 and then s is more commonly written as side times root 2. So this is pretty amazing. If you have a right isosceles triangle, let's just appreciate this for a minute, where the two legs are equal, so side, side, you know the hypotenuse immediately, side root 2. There's a nice relation between these three sides, and it comes in with a factor of 2. Let's look at another most beautiful object. How about we look at an equilateral triangle? All right, so friendly reminder, what is an equilateral triangle? An equilateral triangle is one in which all sides are congruent, and that also forces all the angles to be congruent as well. Now there's no right angle that appears in here. For equilateral triangle, you have 60, 60, and 60, but what you do, same as before, you sort of cut this thing in half, and you draw a height down from the top, and that creates a right angle with the base. And all of a sudden, you have a very special right triangle that appears. Because the original triangle is an isosceles triangle, let's give these things some names. So how about A? We'll call this the height. We'll say B. And then we'll call the hypotenuse C as before. Remember, because it's an equilateral triangle, the angles are all 60, 60, and you cut this one in half, so now you have 30 and 30. You may know this one as the 30, 60, 90 triangle. It's really 30 degrees, 60 degrees, and 90 degrees triangle. That's corresponding to the angle measurements. The other one I also should have clarified, because I cut a right angle in half, I got a 45 degree angle on both of them. So sometimes this is known as a 45, 45, 90 triangle. And just because, again, when you see them, just realize they're part of a bigger object, so you get a lot more information than you might realize. If I start putting things together, what do I know? Well, A has to be 1/2 of C. A is 1/2 of C. Now, why is that true? Because remember, it's equilateral, so they have the same lengths. I cut C in half to get A, so A is 1/2 of C. So this tells me, remember, I usually start with A squared plus B squared is equal to C squared by the Pythagorean theorem, but A is 1/2 of C squared, and I have a nice relationship between two of the sides. So now, really given one side, I can find all three. This is better than the normal condition where I need two sides to find the other third side. So B squared and C squared remain the same. Let's clean this up a little bit. The 2 hits both C and the 1/2, so I get 1/4 C squared plus B squared equals C squared. Let's subtract the 1/4 C squared from both sides. You take 1 and subtract 1/4. You get B squared is equal to 3/4 C squared. And oftentimes we're trying to solve for the height. It's the thing we want. We use it for area formulas. So in that particular case, we get B is the square root of 3C squared over 4. Now square roots break up over fractions. So you hit the 3, the C squared, and the 4. Square root of 3 is what it is. It doesn't change. Square root of C squared is just C. And of course, the square root of 4 is 2. So there's a little cleaning up that you get. And normally you see this as root 3 over 2 times C. Putting C in the numerator or next to the number, those are the same, by the way. It doesn't matter, just a matter of preference on how you write it. So the big takeaway here is if I have a 30, 60, 90 triangle, let's sort of summarize our results here. So we have 60 down here, we have 30 down here, and we have a 90-degree right triangle. Then whatever my side is, let's call this side C, I can take the other side to be half of C, and then the height has to be root 3 over 2 times C. So if you know one side, you can go ahead and solve for any of them. This is kind of amazing, but again, that comes from the symmetry that this is half of an equilateral triangle. If you've seen a little bit of trig, you know these angles also come up in trig and sine and cosine. Again, you'll see that in a future class. If you ever take the precalculus class, we start to get into the trig behind these, but we take advantage of these values to start finding values of trig functions, sine and cosine. Just to let you know that you're going to see these again if you start to take more math. One of the nice applications of the Pythagorean theorem is that the distance formula just automatically appears. You almost get it for free. So just a friendly reminder of what it is. If we're on the real number line R, and I draw some distance, let's say I have a point A at 2 and B at 5, if I want the distance or the length of the line segment that connects A to B, sometimes they write this as the distance, it's the absolute value of B minus A. You can think of this as the distance from B to A, so we subtract inside the absolute value, but of course you can also go the other way. If I go from Baltimore to New York, it's the same distance from New York to Baltimore. That's why we use the absolute value. And we have 5 minus 2 is 3, so however you want to do this, the distance of course is 3, but just notice it doesn't matter as you subtract as long as you use absolute value. What if I want distances on the xy plane? So now imagine you have the xy plane and you have some point that's A in space, and some other point B in space, and I'm like, what is the distance between them? How do we find them? Well, let's get some information here. What does it mean to actually be a point? It means that you have an x-coordinate and some y-coordinate. So A is the point x1, comma, y1. And then, of course, what does it mean to be a point? Another point in space, well, B, let's give it the point x2, comma, y2, and we'll drop those down and find those. So we have x2 and y2. And I only drew these points, of course, in the first quadrant, but if we were to draw them in any other quadrant, they'd be exactly the same. And whenever you have this distance, what's hiding in the background, of course, is a nice right triangle. And the length of the leg, is x2 minus x1. And the length of the other leg, the difference in the height, is y2 minus y1. So to find the distance between the 2 points that I want, call it d, the Pythagorean theorem kicks in as well, and I get d squared is equal to the leg squared, x2 minus x1 squared, plus y2 minus y1 quantity squared. I'm not usually interested in d squared. I often want d. So because it's a distance, I'm going to take the square root and only the positive square root. And when I solve for d, I get the square root of parentheses x2 minus x1 parentheses squared plus parentheses y2 minus y1 close parentheses and square. Again, solving and plugging in numbers into the distance formula to actually get distances is not very hard. I trust you can subtract numbers, square them, and plug them in the calculator. What I'm more interested here is reminding yourself what the distance formula is on the xy plane, and then more importantly, how did I get there? Why are these things true? They say math is easy until I start asking why. Did you realize that this is just an application of the Pythagorean theorem? And when you understand where things come from, it helps to recover the formulas in case you ever forget. If you just blindly memorize something and it comes up on a test, you can forget it and there's absolutely no recovery. But if you understand why it's true, why that there's a plus sign right here instead of a minus sign, you don't have to guess, or should it be squared or cubed or something weird? No, it's the Pythagorean theorem, so of course it has to be plus. Of course it has to be squared. You can put these pieces together, and then these formulas start to make sense, and you understand them versus just memorize them. I'll ask people, what's the Pythagorean theorem? They'll tell me that, and I say, what's the equation of a circle? And they have no idea. So let's remind ourselves what a circle is. It's you pick a point, you pick a center, and for whatever reason, the center is often denoted by the point h comma k. So we're in, somewhere on the xy plane. And then around that point, you look at the set of all points a fixed distance away. Often the distance is called the radius. And you imagine what is it like to be a fixed distance, the radius away from this point. So here's the world's worst circle, but you get the idea. Any other distance from the circle to the center is fixed. It is a fixed distance. If you let the distance vary, you get an oval. Some distances are longer or shorter. But here, you get a circle when the distance is always the same. So a circle really is a statement about distance. So what does it mean to be a point on the circle? What does it mean to be x comma y that lives on the circle? It means that my distance is equal to the radius. It's equal to r. Well, now we know the distance formula. So all of a sudden, this becomes r squared is equal to x minus h. Remember, h is a fixed constant. So h is some known number. Quantity squared plus parentheses y minus k quantity squared. Any x and y that satisfies this equation, remember r, h, and k are all given. These are all fixed numbers. If x and y satisfies this equation, then I'm done. And this is the equation of a circle. One circle that comes up in particular, the nicest circle, is the unit circle. This one has a name. Again, maybe you've seen this before, but you should know what this is. Out of all the circles I could possibly draw, the unit circle is extremely nice. It has a radius equal to 1, and its center is at the origin, 0, 0. When you plug in 1 to our equation, 1 squared is just 1, and when you plug in h and k for 0, you just get x squared plus y squared. This unit circle comes up, I think, in every single class from precalculus onward, so you should know the equation of the unit circle. You should know it when you see it. Again, unit circle means two things. It means the radius is 1, and it means that the center is the origin at 0, 0. Its equation is extremely nice. X squared plus y squared equals 1. If you're trying to remember where you saw it, you probably saw this in trig, however long ago that was. Let's just do a quick example and play around with our circles. If I said to you that the center is at 2, minus 5, and the radius of 3. Let's find the equation. Let's see if you can memorize the equation, understand the equation without having to go back and look for it. R squared equals, I'll write it one more time, x minus h squared plus parentheses y minus k squared. R squared is 3, so 3 squared, of course, is 9. X is my variable, so that stays. H is my 2, so minus 2, quantity squared. Now you got to be careful here. Y is the variable, so that stays. K is minus 5. So when you negate k, you actually get plus 5. Be careful right there. It's minus 5, which is, of course, plus 5. They just want the equation, and so guess what? You're done. That's it. There you go. As one more example, sometimes they give you the equation, and they ask for you to pull things off of it. So let's do y squared plus 6y equals 0. Find the center and the radius. A couple things about this that you just have to be careful why this is a little bit of a trick question. This is not in the same format as this. This is not well, this part's okay. X squared is like x minus 0 squared. But the problem is you have y squared plus y. They've done some foiling on the general equation, and you have to put it into this form. Do you remember the skill? This is called completing the square. So watch out for that. If they don't do this, you have to complete the square. So what does it mean to complete the square? We're going to add a constant to both sides. So I can write this as y, well, minus something, or y plus something squared. That's the key. X squared as it is perfectly fine. Sometimes you got to complete the square on the x side. It doesn't matter. But in this particular case, I must complete the square. I can't look at this and tell you exactly what k is. Nor can I say the radius is 0. That would be kind of weird. So what do we add to complete the square? Remember, this would be like our b term. This is the coefficient on y. So to complete the square, you cut b in half, and then you square the whole thing. So 6, half of 6 is 3. Square 3, you get 9. So we're going to add 9 to both sides. Realize because I added 9 to both sides, I did not change the equation. This is perfectly legal. And I get y squared plus 6y plus 9. Stare at that for a second. That's the same as y plus 3 squared is equal to 9. Convince yourself this is true, that I have just rearranged the equation in a more useful format so I can look at this and pull off that the center, the thing being subtracted off of x, is 0. So h comma k is 0 comma minus 3. Notice I'm grabbing the opposite sign. And my radius is 9, but this of course is r squared from the formula. Watch out for this. I have to take the square root of 9. So my radius becomes the square root of 9, which is just. So my center is at 0 comma minus 3. My radius is 3, and I of course can go off and graph this if I want to, but you might need to complete the square, skill we've seen before when working with quadratics, to get some information off of the circle. All right, so hopefully you came out of this lecture with just more than knowing the Pythagorean theorem, which you may have known already, but I want you to know why is it true, and of course 2 formulas that pop out for free, the distance formula for 2 points in the plane, and the equation of a circle, which really is a statement about distance. Understanding these formulas and how they relate to the Pythagorean theorem, as well as 2 nice special right triangles, the 45-45-90 and the 30-60-90, are really great things to come out of this with, things that you should never have to memorize anymore because you already probably have the Pythagorean theorem embedded in your brain. So from that, derive all these other equations, understand where they come from, and of course use them, do well on any questions, and be successful in all your future math courses. This stuff comes up over and over and over again. All right, great job on this video. We'll see you next time. Hi everyone, welcome to our lecture on exponential functions. We're going to be modeling with these functions, so I thought we could just take a quick minute to review what they actually are. So exponential functions, what do they look like in general? They are of the form y equals. Normally we'll put a number in front, then we'll put some base, we'll use any letter we want here, raised to the x. So x is our variable, a lot of letters going on here, so c and a, these are just some real numbers. X is our variable. We call a the base of this function, the base of the function. C could be 1, C could be whatever you want. We tend not to have a equals 1. The reason for that is that if a is 1, then 1 to the x just is 1 for any number x, and so you just tend to get a constant function. That's a little boring. So we like exponential functions to actually look like an exponential curve. And you've probably heard expressions like things grow or decay exponentially. So let's draw a nice example here. So how about y equals, we'll just do it like a generic one, y equals a to the x. We'll just make c be 1 for now. This is the case, this is exponential growth. We've seen this before. This is when a is bigger than 1. When a is bigger than 1. A couple things about it. It goes right through the y-axis at the point 0, 1. Stare at that for a minute. Make sure you convince yourself that that is true. When you plug in 0 for x, you get a to the 0, that's 1. And you never quite touch the x-axis. We say that as x gets small, so as x goes to negative infinity, then the function will tend towards 0. This is asymptotic behavior. I'm going to use arrows here. I'm in particular not using equal signs. This is exponential growth. Start off low, and you get nice and high. On the flip side of the world, you have exponential decay. This is when you start off with more things, and then you have less. Think of this like radioactive decay or something like that, or some population that is shrinking. So in this particular case, same function, same format, it's exponential, so let's just do y equals a to the x, but in this particular case, my value of a is less than 1. We also want a to be positive, I should probably say that. So a is between 0 and 1. Once again, y-intercept goes right through the origin, 0, 1. That's something that both decay and growth have in common. Again, I'm assuming here just basic function a to the x. If you start moving functions around and it's plus 7 or whatever, sure, you're going to move these intercepts. But just get to know the parent function, y equals a to the x. What else do we want to say about these functions? What else do they have in common? Their domain for both of these functions. Can you see what it is? It's all reals. Plug in any number you want. The domain is all reals. The range is interesting. The range of these functions, stare at it for a minute, is 0. So I got to use parentheses here because of the asymptotic behavior. 0 to infinity. I use parentheses on infinity always, always, always. And for growth, I guess I should put it down since I did for the last one. As x goes to infinity, then the function itself, y will head over to 0. So that's the asymptotic behavior as x gets large. All right, so this is our exponential functions. Let's do a couple of examples, things that we're going to see. Just some examples of exponential growth. We've seen like y equals 2 to the x, perhaps. Nice exponential growth. Up it goes. Exponential decay. How about y equals, let's do a nice base here that's less than 1. How about 1/2? 1/2 to the x. Just as a heads up, you often see they often bring the exponent in. So if I bring the x to the numerator and the denominator, I get 1 to the x, just 1. So you often see this as 1 over 2x. You have to realize that no matter which form you get it in, you're staring at a function that's exponential decay, and then it goes from high to low in that regard. One just word of warning here. Again, this is the speed up version of exponentials. If you need a review, you might want to go back and watch that lecture. These are not functions of the form, say y equals x squared. These functions are called power functions or polynomials or something else, but they are not exponential functions. The biggest difference with exponential functions is that the base is constant and the variable appears in the exponent. With a power function or polynomial function, the base is the variable and then the constant appears in the exponent. So depending on where the location is will dictate the type of function that you're working with. Everything we do in this video and the next one are about exponential functions. This is where I have a constant base and then my exponent is the variable. Now let's talk about the number e. It's a little weird to say, right? Like e is normally a letter. E is a number. I've seen this before. E is about 2.718 and change. It goes on and on and on forever and ever and ever. It's an infinite decimal. We call these guys irrational. Good vocabulary word there for you. It's an irrational real number. And it's, 2 and change, whatever it is. When you work with E, I wouldn't replace it with the decimal form. I would just use it in the calculator as E. That's stored in the computer's memory as a lot of decimals. And if you call it 2.718, you can introduce rounding errors. But it's probably, it's best to think about it as 2 and change. It helps just give some intuition about what this is. To really understand where and why E is 2.718 and to really appreciate E as a function, you're going to need some calculus. It's been argued that E is the most important base for exponentials in calculus. So you will see this thing over and over again. The thing that I can sort of talk about now is that a lot of times when you write out any exponential function, right? So if I write out like y equals a to the x, you can always, always, always write to this or rewrite this with a different base. Sort of like you could change the base for logarithms. You can also change the base. You can always write this with a base e to the k and then put an x in here. And for your appropriately chosen value of k, you can just say e to the k is equal to a. That's a basic algebraic expression. So since there's no harm or foul of writing any base just at the cost of just putting this coefficient k in your exponent, we tend to write functions with e to the x. So it's very common, the root function is going to be y e to the x, but perhaps a more complicated one is going to be y c e to the k of x. When I think of an exponential function, like this is the default that I go to. Some coefficient in front, e to the kx. And one thing about this coefficient in front, if you plug in x equals 0, so if we look at y equals 0, then you get c e to the k times 0. K times 0, of course, is 0, and e to the 0 is just 1, so this turns out to be like c times 1, which is just c. So C is your initial value. So C is your initial value. But specifically in modeling, it's usually like the variable will be time. And it's like, what's your first data point? That's usually what we care about. So that's just some interpretation of this coefficient front. And then this K upstairs, this will be your growth rate. This will help determine how fast or how slow. And so this growth rate will help determine how fast or slow this function is growing. I leave this as a calculator exercise or maybe even a spreadsheet, but you can numerically approximate E. It's not obvious why, but just trust me that you can. If you with the expression 1 plus 1 over n raised to the n. 1 plus 1 over n, you can almost define E to be this. If you take n to get really large, this will approximate E. So try it on a calculator, plug in 100, plug in a million, plug in a billion, whatever you want. This will approximate E, and you start getting closer and closer to 2.718. And then if you want, you can actually type in E and see how close this gets. So the numerical way to do it, if you ever need E like 5 decimals, 6 decimals, whatever, you just plug in larger and larger values of n. The reason why I'm showing you that is for the piece that's going to follow. This expression comes up when we do interest. So let's talk about interest now. So what is interest? Interest helps value time. $1 today is worth more than $1 yesterday in the past, and money changes over time. The idea is you could invest that amount, and then you will accrue interest on that investment. And so the times that the investment receives interest is when it's compounded. And so if we have some particular value, so let's look at like an interest rate, we'll call it R will be our interest rate. If I have some amount, after a certain period of time, I get 1 plus my rate. And the nice thing about interest, let's say my rate's like after 1 year. The nice thing about interest is that the interest accrues interest. So this is after year 1. After year 2, maybe we'll write like a function. After year 2, I have the initial amount that I deposited, and then I have my interest from year 1, and then I get my interest again on that interest. And you clean this up, and you get, not surprisingly perhaps, squared, you get a nice exponential function. And this continues, right? This continues. So maybe after year 3, I have my initial amount. Again, I'm assuming I'm not withdrawing anything from this. I have my rate, and it's cubed. And then it goes on and on and on. The longer you leave the investment in there, then the more interest it accrues. Some people, if you have a savings account or something, or a checking account, maybe you get interest monthly. Maybe you receive dividends on a piece of stock, on some stock quarterly. You can receive money at different times. It doesn't have to be just yearly. So in particular, you can do things that, like if interest is compounded semi-annually, right, twice a year, then half the interest is paid over that period, but the number of period doubles. So let's do that for example. So for example, like the amount now after half a year will be whatever your initial amount is, and then it's going to be your rate, but half the rate. You're only getting half the interest. And the amount after a full year is going to be the amount you start with, and then the rate, half the rate you get, and then you get it again. So that starts to take a square power. And this is after 1 full year. So after like t years, we're going to use t as our variable for time. You always have your initial amount and the interest that accrues per year, and then time raised to the 2t. If you had monthly compounding in a similar format, you would get, this is what I have in a checking account, you get a little interest once a month. So not a ton, but it is what it is. We'll take it. So that amount, now you're getting whatever rate, but you're getting 12 payments. So that means you have to take the interest and divide it by 12. And it takes a full year, takes 12 compounding periods, and then times t. And if you had daily, you could replace the 12 with 365. If you had some other weird thing, whatever you want, you can just keep replacing it in general. So our general formula would be a to the t. So the amount after a certain period of time is whatever your initial amount you deposited. That's called the principal. 1 over the rate to the n nt. and n is your how many times the interest is compounded. Okay, and t is in years. You can start to see that there's an expression in here that's starting to look like that expression for e. And if you are compounded continuously, and this is bad if you are, this is usually what you pay if you are the receiver of a loan, right? The price changes, you get compounded continuously. That is basically saying, like, I want the number of compounded continue to go to infinity. In that particular case, we have a new formula, and it's the amount that we deposit. Here comes the e, e to the r, which is our interest rate, times time. So this is our formula, and perhaps not surprising, the base here, e, is our good old, our friend, this is Euler's number, 2.718. So we have two formulas here, and this is going to be used to compute interest. Once you have the formulas, going through problems is just plugging in for the variables and being mindful perhaps of the units. But let's just do an example. Let's say that you deposit $1,000. Why not? And you want it to sit for 6 years, so we'll let t be 6 years. And let's say that the interest rate is 5%. Let's let the compounding be annually, so that's going to be m equals 1. And what I'd like to know is, I'm trying to do some financial planning here, what is going to be my amount at the end of this investment? So I want to know the amount a of t, but t is 6 years, and then we just plug in the formula here. So I told that m equals 1, so this is going to be my $1,000 times 1 plus 5%. It's typical to write it as a decimal, so we'll write 0.05. My compounding period is 1. I'll write it in anyway. And then we have 1 times 6, of course, which is just 6. Clean that up, work that out. I'm expecting, this is a calculator exercise, of course, but you get 13, 40, 10. Units are in dollars. That's nice. I get more money at the end than what I started with. Perhaps not surprising. And you can change what m is. For example, if you wanted this thing to, say, compounded daily, so daily would be like m is 365, well, then your amount at the end of 6 years, again, I leave this as an exercise to plug in, would be 1349.83. And last but not least, of course, if you plugged in and you wanted that the interest is compounded continuously, you would plug in all your numbers at the end of 6 years, and you would get 1,000 e to the 0.05 times 6. Running out of room here, so I'll just put the number down, but you can check this is 1349.86. So there's very little difference between the amount produced by daily compounding and continuously compounding. But it's good to know if you see these things, especially if you're going to get a loan or who knows for what, you should know what they work. One nice thing about these formulas is that oftentimes they give you have like an end goal, like I have $1,000 today and I want to save up for something, and then you can use these formulas to solve for t. Or you can solve for r, and you say, well, what rate do I need? Or how long at the given rates do I have? How long do I have to wait until this investment accrues enough money for what I want? So these formulas are really nice for financial planning. All right, so compound interest or continuously compounded interest is for exponential growth. Let's do one example here, a last example of exponential decay. So the remains of a prehistoric man, which is now called Ötzi, also called the Iceman, was found in September 1991 near the border of Italy and Switzerland. It was actually found by some tourists. Imagine walking by and finding that. So what do? You go get your local scientists, and then they start to analyze it. And if you want to read about it, definitely search the Wikipedia article on this thing. It's pretty fascinating. But one of the things that you can do is you can find out how much carbon-14 is left or remaining, because it is a radioactive isotope of carbon. And you can calculate how old something is. So this is how they do carbon dating, as you may have heard. So we'll give you that the half-life of carbon-14 is 5,730 years. A half-life, remember, this is a time that it takes for a mass to decay to get to exactly half of what's left. So what we're going to do is we're going to set up a model for this equation. We're going to switch variables here a little bit, called q of t. And this will be the amount of carbon-14 present t years after death. So this is the amount present This is an exponential decay function, so we are going to set it up with our initial quantity. We're going to set up our base to be e. We have some decay rate k that we don't know, and time that's left. Okay, so we got to find a couple things. I don't know the initial amount, and I don't know k, although I can get k from the half-life. Whenever they give you half-life, they're always giving you k. Why? So let's use the half-life for a minute. So the quantity left after the half-life is 5737. Okay, so what does that mean? Whatever my initial amount is, I have half of it left. Half of it left. I don't know what the initial amount is, so we'll just call it q naught. And then I set it equal to the other side of the formula, q naught e to the k, and the time here is 5730. Everything's in years. And you say, well, wait a minute, I don't know what the initial amount is. That's okay, because it cancels. Completely don't need it. And then that allows you the nice cleaner equation that you have 1/2 equals e to the k 5730. So we got to solve for k. This allows us to solve for k. How do you solve for k? Well, k is trapped inside an exponential. Why don't we take log of both sides? In that case, we get log of 1/2 is, log and e cancel, so k times 5730. And you can solve for k. So k gives you that log of 1/2 divided by 5730. This is all a calculator exercise. Obviously, you're not supposed to know what log of 1/2 divided by 5730 is, but your calculator, you should know how to plug in a calculator. I would not introduce it as a decimal here, even to 3 or 4 decimal places. Hold off on that urge. You're going to introduce a rounding error. Let the number live inside the memory of the calculator. Store it somewhere, or just use like second answer. But you want to, I don't want to call it a decimal at this point. If you want to make sure you're plugging it in right, just so we can check, it's about negative 0.000121. That's about k. So that number will be used right in our formula for radioactive decay. Now, since we know that 47.590% of the carbon had decayed, remember I want to know what's left, so I have to subtract that from 100% or subtract that from 1. So that is, in calculator you can do 1 or 100 minus 47.59, and you get 52.41%. So here we go. Let's use that. So whatever the initial amount is, maybe I'll switch up colors. Whatever the initial amount is, we have, let's do it as a decimal, 0.5241. So remember this is equal to 52.41% remaining. As always with word problems, you just got to be very careful. Notice I'm not using the number that's decayed. I want the amount that's left. So you just subtract. You subtract the number from 100%. So that is remaining of my initial amount, whatever that was, and that's going to equal, by the formula, q naught e to this k value. I'm just going to write k for now, but it's some decimal that's known, times t. And once again, the initial amounts, which we don't know, cancel, which means I don't need to know this. A lot of students get stuck here. They say, but I don't know the initial amount of carbon-14 inside the person. Doesn't matter. Don't need it. Doing the same sort of things to solve for, remember the goal is how old were the remains. We want to find t. So we have log of 0.5241 equals, log and e cancel, so you get k and t. And now it's just a nice calculator exercise where you have log of 0.5241 divided by k. So in the calculator, here's what I'm going to do. I'm going to do, first let's get k. So let's do log of 1/2, log of 1 divided by 2, divided by 5730. I hit enter, and I get this small number. I'm just going to leave it. Okay. Now to find time, I'm going to do log of 0.5241 divided by second answer. When you do that, I'm going to round here just because it's years. I'm going to get 534, I'll say 1. 5341. So 5,341 years, give or take. So by this method, the skeletal remains of this prehistoric man, they're over 5,000 years old. That's amazing, right? Like that means this person was from about 3000 BCE. Pretty cool. So just imagine taking a hike and finding this thing. So go read up on this person. It's pretty amazing. But more importantly, I guess I care about the math and the use of the exponential function as an application to do radioactive carbon dating. So next time you find a dinosaur bone, they can use this model to see how old it is. All right, keep that calculator handy. Great job on this video. We'll see you all next time.